Thank you very much. And it says on my notes, the first thing I should do is introduce myself, but I've been kindly introduced. So I'm an Earth System Scientist here at UCL, which most of you, because of your medical background, would go, what's that? So I study climate change in the past, the present, and the future. But Sanjay, bless his heart, has made sure that this year, the 4th year, I will not be talking for the 4th time about the depressing nature of climate change. Luckily, we have some excellent speakers, including Dan, who are going to depress you instead of me. So I'm going to be the one looking good. Now, for the speakers, where is Jessie?
Jessie will be on.
Jessie's online. Oh, okay. So the great thing is that you will get 15 minutes. I'm going to be sticking my hand up with 5 minutes to go, so you actually have some timing. The reason being is because we like these meetings to be really interactive, and I'm going to pop back up and try to actually get a couple of questions, and we'll keep to time. So I'm going to introduce, is she around? We got her online? Excellent, that's fine. So Jessie is an inclusive design specialist and researcher with a professional background in architectural design. Her work operates in the critical intersection between health, neuroscience, climate impact, and the built environment. Currently, Jessie serves on the advisory boards of the London City Airport, East West Rail, the British Standards Institute, and the International Bureau of Epilepsy. Echo. Sorry. Jessie is completing a PhD in architectural design here at UCL, titled Seizing Space, Epilepsy, Climate, and the Built Environment. And she is our lived experience speaker because she has generalized epilepsy, so she draws on that as part of her understanding and therefore how she's going to actually understand how we design a climate resilience and brain health of the mind. I'll pass over to Jessie.
Thank you so much, and thank you so much, Mark. So as Mark highlighted, I live with generalized epilepsy, and today I'm joining you via screen as I'm navigating the ebbs and flows of a willful epileptic brain that requires constant adaptation. So for me today, it was attending online rather than in person. And that's why conferences such as these are so important. It creates a space where we can discuss how the environment must adapt to the reality of diverse neurological needs. I was diagnosed at the age of 19, and this was a really pivotal moment for me. I'd recently returned from taking a gap year and was about to start my architectural education at university. And at the point of diagnosis, navigating environments became disabling and a sensory minefield, and the binary divisions between disabled and non-disabled people became strikingly real. And this was also true for academia and workplace practice. So, as many do, I mapped my seizures using a seizure diary and began noticing patterns between my seizures, environments, and architectural variables. So architectural design variables are physical design elements that describe architectural features such as building shape, orientation, sensory stimulation, patterning, and materials. And I realized that actually my surrounding environment was a silent partner in my experience with epilepsy. And one really defining moment for me was in 2023. I travelled to India for a friend's wedding, and whilst travelling through an airport in Mumbai, I had a spontaneous influx of seizures. And contextually, we must observe that this was the longest period of time that I'd ever been without seizures. The only defining alteration was the built environment in which I was in and the conditions in which I was residing. And upon reflection, although the architectural design of the airport was beautiful from a design perspective, inclusive design was not considered at all. So to give you a few examples as to why features of this environment contributed to the lowering of my seizure threshold. So one example was patterning. So regional patterns and textures were integrated into the airport's architecture at all scales. From the articulated coffered treatment on the headhouse roof columns and roof surfaces to the intricately pierced window screens that filtered dappled light onto the concourses. So patterns can contribute to seizures or lowering the seizure threshold, also migraines, and also those who experience sensory overload. It essentially causes our nervous systems to go absolutely crazy, and this is applicable to everyone, whether you have epilepsy or not. Another example was intense lighting and light sensitivity. These were overwhelming features present in the design, as well as glare and shadows caused by the pattern structure. Again, these contribute. And although I don't have photosensitive epilepsy, this contributed to the overwhelm to my body. And this is also applicable to multiple other conditions and disabilities, such as people who are blind or experience sight loss, and people that live with dementia and Parkinson's. And lastly, one of the other impacts from this environment was temperature, which is the most applicable to this conference today. And this increased my body temperature and caused temperature shock. And despite the associated context, so the 50-degree heat outside, these were always present. And again, this applies to multiple conditions and disabilities, including MS, spinal cord injuries, Parkinson's, and menopause. And there were so many other factors that contributed to this as well, such as poor air quality and acoustics. I always think of the epileptic brain as a balanced scale. On one side, we have protective factors such as medication, lifestyle limitations, and on the other side, we have precipitating factors which gradually tip the scale and lower the seizure threshold. Now, this seizure threshold is also now colliding with the reality of a warming planet and is creating a fundamental shift in the physiological load placed on the human brain. Now, this experience prompted further research when I got home, and a shocking statistic which surfaced from the National Library of Medicine highlighted that actually there were more than 12 million people living with epilepsy in India, and this accounts for 1/6 globally. And we must note that this number only accounts for diagnosed and recorded cases, so it was at this point that my PhD research was born. So, as Mark mentioned, I'm doing an architectural design PhD at UCL. However, the PhD is multidisciplinary. And the thesis is titled Seizing Space and is structured as a fragmenting unfolding of the relationship between the epileptic body, climate, and the built environment. It basically demonstrates that they are an inseparable continuum, and to address one without the other ignores the physical reality of how bodies navigate space and highlights the opportunity we have to impact health and climate change. Now, a unique element of the PhD is that I live with the condition that I'm researching. I'm essentially a real-time case study. And currently, architectural design and climate change policies are tethered to a reliance on standardized metrics for non-disabled bodies. Lived experience is really at the heart of the PhD, and by centering disabled bodies and voices as a primary site of spatial knowledge and production, it enables the thesis to establish an original collective framework that reframes existing knowledge in this field. It employs a phenomenological autoethnographic approach to frame spatial interaction as a preemptive, situated and reflective process. So other methodologies I'm also using are qualitative and quantitative methods, such as interviews and questionnaires, critical analysis, co-design, and there were two types of questionnaires, one targeting people with epilepsy and the other targeting those who support people with epilepsy, such as loved ones, colleagues, and healthcare professionals. And this was really important, I think, highlighting that the experience of epilepsy is also experienced by the collective support network surrounding that person. We've had some really interesting primary data collected via the questionnaires already. So, for example, it reveals that 80% of participants believe that adequate resources regarding the lived experience of epilepsy and how to live with epilepsy are currently non-existent. 90% of participants highlighted that there's not enough awareness about the connection between climate change and epilepsy. And also patterns have been identified. So these extend way beyond photosensitivity, which acts as a singular reductive representation of epilepsy in current design standards and care. I know that I certainly experienced this within my lived experience. And the primary data highlighted that participants recorded a prevalence in seizures and symptoms caused by environmental factors. So examples included lighting, so it's 74.5%, patterning 56%, temperature 41.8%, and sensory overload 52.8%. And with other multiple participants noting air quality, climate change related events, and climate anxiety in the qualitative responses. And these are only a few examples. So I think it's really important for me to highlight what day-to-day measures and home adaptations I employ day-to-day within the climate that we are in currently. So I live in a new build flat in Brighton and Hove, and although the EPC rating is extremely positive in terms of energy efficiency, highly insulated new builds with large windows which lack cross ventilation can pose a significant risk for someone with epilepsy. So for many, including myself, extreme heat is a direct trigger, and research from the Epilepsy Society indicates that over 60% of people with uncontrolled seizures report an increase in seizure activity during unusually hot periods. So causing things like sleep deprivation, which was me last night, as our home is consistently warm regardless of the time of day, which can then disrupt the REM cycle and lower my seizure threshold, as well as things like dehydration, shifting the balance from electrolytes like sodium in the brain, which are critical for stabilizing electrical activity and faster metabolism of anti-seizure medication. So in terms of management, we use things like blackout blinds inside the windows to enable windows to be fully opened, cooling aids, etc. However, homes like this are becoming increasingly common due to the housing crisis and climate crisis. The design of our home, for example, using natural light as much as we can and avoiding any intense lighting, avoidance of repetitive geometric patterns with high contrast, which again can trigger the nervous system, and visual stress can increase cognitive load. Implementing things like natural materials and colours, so attempting to ground the sensory experience that can lower my heart rate and blood pressure, improve air quality and reduce visual noise. Furniture which are curved and mimics nature. So firstly, obviously this is beneficial in terms of safety from falls from seizures. I've had many injuries, as you can imagine. So curved furniture preempts that slightly. Natural shapes as well within my home can reduce visual stress and calm the nervous system. And lastly, biophilia. So I think everyone that's visited our home jokes that it's like a greenhouse because we've got so many plants, but this is really important because it reduces cortisol levels, provides less visual stress, and improves air quality. So I think it's really important to note here that by implementing methods such as these, we're not just improving an environment for one body or one epileptic body, but actually for everyone. It creates a really calming environment which our nervous system thrives off. Also, if we're designing inclusively, we're actually designing for the planet. And by bridging the gap between neurological volatility and environmental volatility, we can design a future where the world supports the body and all bodies rather than the environment seizing it. Yeah, I've tried to keep to time, but thank you so much. And if any of you would like to contribute to the PhD research, please reach out via Marissa.
Would you like to take some questions?
Go for it.
Okay, in the audience, are there any questions from Jessie? I know it's early in the morning. One in the middle.
Thank you. Hi, Jessie, can you hear me okay?
Yes, I can.
Fantastic. My name is Nina. I'm based in Cambridge. I've got a part interest in chronobiology, although I mainly work on brain temperature. And my question was around time of day variation in seizure incidence. I just wondered if you'd experienced an association between when your seizures happen and the time of day that they happen.
So I think with epilepsy, it's one of those really unusual conditions that is so sporadic and spontaneous. But I think there's definitely a correlation between either late at night or early in the morning. I guess this is probably attributed to sleep deprivation or exhaustion from the day. So I've definitely noticed a pattern then. It's also really interesting how it attributes to my menstrual cycle as well. So certain times of the month, because certain levels are lower. But yeah, I think again, very spontaneous, but I would say there are patterns there for sure.
So I've got one final question, which you probably hate me for. UCL, how would you rate the new buildings in UCL for based on your research?
So I think we are very lucky at UCL without bolstering them too much, but you know, we've got an amazing team that are really driving inclusive design forward, which is great. And that's one of the reasons why I decided to return to UCL following my master's to do my PhD, because there was such a big focus on inclusive design. And I was also a patient at UCLH for my neurology. So I had quite a good personal connection with UCL. I think they're doing the best they can. No one's perfect. There's definitely things that I think could improve across all, you know, universities, whether it's architectural design or the management structures themselves. But I guess this is why in research like this and conferences like this are so important.
Thank you very much. And by the way, we did not practice that question, okay? So can we take one more time to thank Jessie?
Thank you so much.
I'm so badly organized. Right, now, okay. So on to our next speaker, Dann Mitchell, who's at my alma mater. He's at the School of Geographical Sciences at Bristol University. So he leads the Bristol Climate Group and is leading the UK government climate change risk assessment on human health. He pioneered a new field of climate science, which allows us to formally detect the human health toll of past and current climate change. He's the director of the Wellcome Trust-funded International Consortium on Integrating AI and Climate for Impacts on Society, and has won many prestigious awards in this area, including my favorite, Royal Meteorological Society's Adrian Gill Award. Dan, all yours.
Thanks, Mark. Can you hear me okay, everyone? I've got the mic on. So I'm really delighted to be here. As Mark's already pointed out, there's very few of us, I think, in the room who know less about neurological disorders than me and probably Mark. So I think we'll compare notes on that.
Yeah.
What I would say is the problems at hand really require multidisciplinary expertise. So I lead the Climate Change and Health group at Bristol. I'm formerly a physicist by training, and all of my PhD and work has been in climate science. Around 8 years ago, I started building a climate change and health team. And my team, aside from climate scientists, consists of epidemiologists, medical statisticians, which I soon learned was different from an epidemiologist, and people with clinical expertise. And at Bristol, we've got a really good partnership with the NHS, so we have quite a few clinical academics. And I really believe that you need those sorts of teams to address these climate change and health problems. Great, so I thought when we talk about climate change, there's really two parts of the problem there. There's the weather part. So recall, weather is what we see every day. It's the wind, it's the rain, it's the heat. And there's the climate part, which is the long-term statistics of the weather. And this was a paper that I published a couple of years ago. And actually, this was a paper very outside my comfort zone, because normally what we do is we use mathematical models or statistical models to find relationships between weather and health. But actually here I was using something different, something called structured expert judgment, which is where we go out and we ask a bunch of experts, which included many clinical experts, how weather affects health in the UK. And we came up with a list of health outcomes linked to weather hazards, and that's what you see on the x-axis here. And the really strange thing about this paper is it's the first and only paper I feel I've ever written which I almost wanted it to be wrong. I wanted it to be incomplete, and I wanted it to start a conversation. And I think you in the audience are really going to help me here, because I know there's a lot missing there. Really, what we put in here was what's based on the literature. So the y-axis here shows the number of studies which links the health and the environmental hazard for the UK, which leads to mortality. Red is heat, blue is cold, slightly darker blue is storms and floods, yellow is wildfires, and then there's a slightly strange complex category at the end, which I won't go into. The big bars on each side are the all-cause mortality, and you can see, for instance, heat has the most, and then there's very little. What I will say, because I can see him sat in the audience now, is the heat-related renal disorders. Shaq, your paper came out about a week after ours, so there is now a 1 point in there as well. So this is already out of date, and this is, again, I don't normally do this, but this is a result that my group came up with this week. I normally don't share things this new at all, and so please actually don't take too many photos of this one until we publish it. And this is showing from ONS data and looking at death certificates, any death certificate which mentions on there that either Parkinson's or dementia or Alzheimer's are an underlying cause. And we use some temperature statistical models, and we controlled for a bunch of variables. And we looked at the change in relative risk of people with those conditions versus those without those conditions. And so here, to interpret this, relative risk of 1 is normal, a relative risk of 2 is a doubling of risk of mortality as you have that condition. And you can see Parkinson's is over double during heat waves, and dementias is about 1.5 times. Now, I haven't run this past our clinical neurologist that we work with in Bristol, Liz Coulthard, and I've come up with some of the things I've discussed with her in the past as to what might be mediating factors, but this is very much a slide to project to you guys to come and have a chat with me over coffee about where you might see this. And I would say these are very preliminary. These are likely to change when we look more into the analysis. So that's the weather part, but how do we take that weather relationship and look at the climate change burden? This is actually a very difficult area, and it's an area called detection and attribution of climate change. And linking that to the health aspects is extremely new. This is a report published by the Wellcome Trust a couple of years ago, and it shows a timeline of every single paper which has done this formal climate change attribution to a health problem. It started in 2013, which was a sort of trend attribution, looking up in Northern Europe of heat-related mortality. The next paper was one of my papers in 2016. That was the first one which looked at specifically extreme events. And there's been a few others since then. It's worth mentioning Wellcome Trust are putting a lot of money into this. So they've just funded around 20 million pounds worth of grants in this specific area to really build this evidence base. And as far as I'm aware, there's not a single paper on neurological disorders within this context. So there's a hint towards future funding there for you guys. My paper, just to quickly sum up what I showed here, was I looked at London and Paris. I looked at a very extreme heat wave which occurred in 2003, and we calculated what the mortality would have been without climate change and with climate change. So the full bars there show the total mortality during that heat wave, and the darker red shows the heat, just the heat related. Sorry, they're all heat related. The dark red shows the heat related mortality that was just due to climate change. So these allow us to do some interesting things. I'm not going to go too much into the science of why doing this in climate science is hard, but a lot of it relates to scale. So our global climate models are extremely complex. They are millions of lines of computer code, and they require extremely large supercomputers to run. And this model here on the left shows a heat wave over the UK, and you see those grid boxes are quite typical of climate models. So we really need to get down to more local levels. You heard in Jessie's talk there, actually you need to get down to the building level to understand some of these things. And with global climate models, we absolutely cannot do that yet. We can embed different models and we can start looking perhaps at neighborhoods. In fact, UCL has a very strong team which does that here. But in general, we can't do this for global models. We've developed a technique using diffusion models, AI diffusion, which downscales, what we call downscales the resolution. And what that's really doing is it's pattern matching using video diffusion. It pattern matches what the large scale climate looks like with what it expects the weather should look like. This temperature evolution at the bottom shows the solid line, which is the AI enhanced model, and the dashed line, and it's showing the heat wave specifically over Kensington Palace. It was Kensington Palace because I was introducing this to some members of the royal family, and so I thought this would be a really nice way to show what would the heat look like over Kensington Palace in an AI enhanced model versus a non-AI enhanced model. You can see you gain around 5 degrees there. We've applied this to Brazil, and we've used this attribution method to Brazil, again looking at heat mortality, and that's all cause heat mortality. And we found that climate change is causing 4,500 additional heat deaths per year in Brazil. Another way of looking at this, and I'm not going to dwell too much on this, is using a weather forecast model and running it in climate mode. This is extremely difficult to do, but weather forecast models are really good. You see them every day on the weather forecast. They're very well validated. There's a lot of money that goes into them because there's a lot of interest in getting the weather right. We don't have that amount of attention in the climate problem because you don't have the same financial backing of it. So I won't talk too much about this one, but we looked at a heat mortality weather forecast for a particularly extreme heat wave in Canada, and there were some interesting things that came out of that to do with cause-specific mortality as well, especially schizophrenia. Why is this useful? Why is climate change and attribution for health useful? Well, it allows us to separate what is happening because of climate change and natural variability in the climate system. So it allows us to talk about the mitigation. If we reduced climate emissions, how would we reduce our burden? But it also allows us to test adaptation solutions. So if you were to cover, say, London in 50% more trees, you would change the local climate of London, and we can do an attribution experiment of that. But finally, and the reason, 5 minutes, yeah. The reason we talk about this is, the reason it was developed was actually because of this guy, Miles Allen, and his house got flooded in Oxford, and he suddenly realized it may well have not been flooded without climate change. So we asked this question, who could he sue for climate change? And that was the initial paper for this climate change event attribution. Miles is a bit of an interesting character. He's also my former postdoc advisor. It worked though, and these cases here are some of the really big influential climate litigation cases that have worked. Most of you will be familiar, at least with the one on the right, which is the European Court of Human Rights. And this was a group of individuals, elderly Swiss ladies in this case, who successfully sued because they saw that their health was adversely affected more than the general population. And that's a really important point here in climate litigation, is that if you can show that your health is affected more than the general population, you have a case like this. And I think this is where people living with certain conditions, especially neurological conditions, could really have a case to make here. We find ourselves a lot as climate scientists, especially attribution scientists, in court. We find ourselves a lot having to write these expert statements to say this contributes, this is being enhanced by climate change. So we think a lot about these things. So just to summarize my points there, more on the climate side of things, we need to be able to represent weather and the processes really accurately in our climate models. that is especially important for you guys in the audience thinking about neurological conditions, because a lot of what you're thinking about is very local scale. It may well depend on things like persistence of heat, humidity of heat, combinations of heat and air pollution coexisting. So we need to get those mechanisms right. It's not good enough for us just to be looking at the statistics of weather and climate, which I hope you'll probably agree with me here, Mark. We do too much in climate scientists. We just look at the statistics, not the processes. There's lots of good work linking environmental exposures and health data now. I'll resist the urge to talk about UK Biobank, considering how much it's been in the news, but data sets like ELSA, for instance, which looks at sleep. There's some really great work combining the environmental exposures with that. We have a really amazing data set in Brazil called the Brazilian 100 million cohort, which links a lot of GP data records to the Brazilian population. I talked a lot about the applications of climate change in health, so I won't discuss that anymore. What I haven't talked about, and my final point, which I think is perhaps one of the most important things I'm thinking about at the moment, is how we scale this up to the global level. So how do we look at the total attributable health burden of climate change? That number's been calculated once in all of history. It was an amazing study, but it is wildly out of date and wildly wrong. And I think we as a community can do more about that. In that study, neurological conditions were not mentioned once. So thanks very much, and I can take some questions.
Thanks, Dan. Tim Malone from Royal Devon Exeter Hospital. A couple of questions. One is, are you, in your attribution, are you actually working with some of the big actuary companies, global actuary companies like Chubb or WTW or something like that, who seem to know a lot more about this kind of thing than, for longer than perhaps is made public? And the other thing is, the other point of your question was, it's worth looking. It's not just the weather, the heat events, the flood events, the cold events, but the climate, the loss of seasonality. I remember having a conversation with my neighbour who's a farmer about 20 years ago, and he commented that what was really bugging him was the loss of seasonality. And I think that has a bigger effect on health and particularly mental health, but other neurological health as well. So I think that the climate area is worth studying.
Yeah, thanks for the questions. Both very good questions. I mean, to your first one, personally, I'm not working with actuaries. A lot of my colleagues do it. It's where we find some problems there is normally when you work with them, you're working quite exclusively with them because there's quite a lot of private data. So it's great for problems related to, say, country level, especially in America, we see a lot of that. I guess if you then wanted to sort of scale it up or compare with another country, then often you're working with different companies. So yeah, great wealth of data there. On your other question, seasonality, we're thinking about that a lot as a community. You mentioned crop growing, absolutely. There's good evidence in especially Australia of mental health within farmers because their crops are failing. So farmer suicide, not so much evidence for that in the UK, although it's mentioned. Seasonality in terms of things of pollens as well. So we often think of this tree as this amazing thing for climate change, and it absolutely is. But a tree can release a lot of pollen. Those pollen patterns are changing. We're starting, well, I won't say we're starting to see thunderstorm asthma events in the UK, but we have certainly had some major thunderstorm asthma events. They're a bit too chaotic to really attribute to climate change. So yeah, just to back up your point, the seasonality is a really big part of this.
Thank you. Good morning. Thank you very much for the presentation. I am Carolina Cerrudo from the National Meteorological Service of Argentina. So I am a meteorologist. I don't know so much about neurological disasters either. My question is regarding to the results of the study of the beginning of the presentation. I would like to know about where the health database came from.
This one, are you talking about this one?
Sorry?
Are you talking about this one or this one?
This one.
This one here, yeah. Yeah, absolutely. So this this was what we call a structured expert judgment. So this is a technique used a lot in, say, the nuclear industry or the volcanic industry. And it's a way of saying we can't necessarily quantify all of what we want to know. And I think Jessie's talk this morning was a really good example. How could we quantify everything Jessie said and write a model about it? It'd be very hard to do. So the data from this is actually from a structured expert interview of many scientists in the UK, because it's a UK focused one, that included people working in the NHS, people working in government, academics, and those with lived experience. And that's why I say the results on this, I'm very happy to see them change a lot, because if I had interviewed this audience, this would look very different. Yeah.
Thank you very much, Dan. And one more round of applause for Dan.
What's next?
So next up, and it's interesting that the theme of extreme heat is carrying on, and Professor Ollie Jay is the founding director of Heat and Health Research Centre at the University of Sydney. He's obviously come a long way. And what he does is he looks at how the global efforts are happening to protect people from extreme heat. His work has helped shape heat wave policies, heat alerts across multiple continents. He's also advised major sporting bodies, and I love this, the Australian Open, and he was the lead heat consultant for the Australian Olympic team for Paris 2024. And I'll be interesting to grab him after during the coffee break to ask about the World Cup and impacts, particularly on the English team. So Ollie's research has been featured in leading scientific journals, as you would expect, Science, Nature, and the Lancet.
Great. Okay, thanks so much for that introduction. So Dan just spoke about the climate and about weather, but what I'm going to focus on for the next 15 minutes is predominantly physiology. And the reason this is so important is that the reason that people get sick or die when they're exposed to extreme heat and extreme humidity is because of the physiological processes that are happening inside their body that leads to heat-related mortality and morbidity. So I figured a good place to start would be to try to get a definitive answer for everybody in the audience here as to what heat stress actually is. And heat stress is actually a term that is misused quite a lot. Often people use it as a description of a result of heat exposure. But heat stress describes the interaction between the human body and the surrounding environment. And it then gives rise to heat strain, which becomes potentially problematic. So let's kind of dive into this question about heat stress by first examining the way in which the human body interacts with its environment and the way in which we're trying to strive to attain heat balance. So even right now, everybody sitting here, we're all generating heat inside the body as a byproduct of cellular metabolism. The rate of internal heat production goes up, of course, when we're physically active and we're contracting large skeletal muscles in order to propel ourselves through an environment, for example. So we're generating heat inside the body. We've got to get rid of this heat to prevent our bodies from heating up. And the way in which we do this is by exchanging heat between the skin surface and the surrounding environment via three primary biophysical pathways: convection, evaporation, and radiation. Now, I'm going into quite a lot of detail here for the purpose of demonstrating what is actually characterizes a hot environment. And it is defined by what modulates these avenues of heat exchange. So we know that convection is driven by ambient temperature. Now, we hear about ambient temperature all of the time. It's the primary forcing function that's used in epidemiological studies. But what most people don't realize is that temperature is actually measured in the shade. The temperature that you get on the weather forecast, the temperature that you have on your weather app, it's measured in the shade. And it is an aspect of the thermal environment, of course, and it's an important one, but it's not the only one that matters. It modulates our ability to lose heat or gain heat via convection, but also ambient wind, so air velocity around the body, which is impacted by the built environments, by a variety of different things in the environments, also determine heat exchange via convection. There's also radiation. So if the temperature is measured in the shade, we need to characterize the thermal load for people that are exposed to direct thermal radiation. So I live in Australia, and it's often above 35 degrees Celsius in the summer. And if you're out in the sunshine in the middle of the day in January, which is the middle of our summer, of course, we measure mean radiant temperature with a tool called a black globe thermometer. And that black globe thermometer takes into account the additional thermal load that is imposed on the body due to direct and reflected radiation from the environment. And that black globe thermometer, it wouldn't be unusual for it to be 15 to 17 degrees Celsius higher than air temperature in the shade. It's a quick aside, so we deliver the extreme heat policy for the Australian Open every year in Melbourne. And this year, ambient temperatures in the shade reached 45 degrees Celsius. Black globe temperature reached 60 degrees Celsius. So that gives you an idea of this additional thermal load that we're exposed to, but we're not really accounting for it if we're just thinking about air temperature. And the next speaker is going to talk about humidity, so I won't go on about it too much. But when air temperature exceeds 35 degrees Celsius, the only way in which we can physiologically cool our body is through producing sweat and enabling that sweat to evaporate. And ambient humidity is an incredible driver for that evaporative heat loss. And it's also coupled with air velocity as well. So right now, I've transitioned from having one environmental parameter that defines how hot is too hot, which is temperature, to now 4 environmental parameters: air temperature in the shade, mean radiant temperature, humidity, and wind. It also matters what you're doing, because that determines our rate of metabolic heat production. Also matters what you're wearing as well, because features of the clothing that we wear really determine how well that heat can dissipate from the skin surface. There's a characteristic of clothing called the evaporative heat transfer coefficient, the evaporative resistance of clothing. And that is the definitive characteristic of clothing that determines heat stress risk from a clothing perspective. So we've got 4 environmental parameters, 2 personal parameters that define what heat stress actually is. So how does this all come together? We can define the hazard using these 4 environmental parameters, pair it with these 2 personal parameters of activity and clothing. Often that hazard is amplified by features of the built environments, such as the urban heat island effect. And then this now translates into physiological heat strain. And so often what we think about when it comes to extreme heat exposure and the body's responses, we automatically think that, well, people are just going to get their core temperature up. They're going to get hypothermia. Of course, that's an important risk factor. But it's not the only risk factor, particularly when we're looking at people with different comorbidities, with different chronic diseases. So the heat strain that evolves from this heat stress exposure is rising body temperature, which is your risk of hypothermia, cardiovascular strain, so how much work your heart has to do in order to maintain central blood pressure, and also the rate of dehydration. There are other things as well, but those are 3 characteristics of heat strain. And then the question is, well, how much heat strain is too much for a particular person? And that then translates into health risks. Now, how much heat strain is dangerous for one person is different relative to another based on a variety of different personal characteristics. So if you've got heart disease and your body is trying to keep cool by redirecting all this blood toward the skin in order to maintain blood pressure, your heart rate's going up, that cardiovascular strain becomes very problematic if you've got an underlying cardiovascular disease. For a relatively healthy young person, it's not a problem. So we need to think about all of these different modulating aspects when we're deciding how hot is too hot. Now, there are also things that we can do from a behavior perspective. Through behavior, we can alter the amount of exposure that a person experiences. And it can also modulate the level of heat strain for a given combination of hazard and exposure. So when it comes to how hot is too hot or what is heat stress, it gets pretty complicated. So we've got these physiological models and biophysical models that enable us to feed in weather data to enable us to estimate what heat strain is. And I can talk with people, anybody who's interested about that afterwards. I've been asked to talk about the mechanisms associated with extreme heat exposure. And much like a few of the other speakers today, I'm not a neurologist, I'm not a neurological expert, but I'll talk to you about the basic fundamental factors that we see happening inside the body when it comes to extreme heat exposure. So this figure that was published by Tracey in our Lancet series that we published back in 2021 summarizes the three of the main ways in which extreme heat can kill people. Now, this is not the only three ways. There are many other ways as well, but this is a pretty good summary of these three different ways. And the thing I want you to take home from this is that the mechanisms are different, and therefore the solutions are potentially different as well. So let's start off with the obvious one, which is heat stroke. This could be classic heat stroke or exertional heat stroke. And the underlying mechanism for that is that in an effort to keep cool, we redirect blood towards the skin surface. This deprives the gut of oxygen delivery via the bloodstream. This results in a translocation of bacteria from the gut into the bloodstream that enters the circulation and sets off a cascade of effects that results in multiple organ failure. We have a world leader in this mechanisms in the audience with Dr. Bouchama over here, and so he'll be able to give you a lot more definitive description of those mechanisms than I will. That's a decent summary, I think. So that's driven by the redirection of blood towards the skin surface and high internal body temperatures. From a clinical perspective, if you're trying to diagnose heat stroke, you're looking for a rectal temperature above 40.5 degrees Celsius, coupled with central nervous system dysfunction. If we're looking at people with cardiovascular disease, now this is an entirely different mechanism. So again, in an effort to keep cool, we're redirecting blood towards the skin surface. But in order to maintain central blood pressure, we've got to increase cardiac output because you're redistributing that blood around more and more tissues. So stroke volume is typically preserved or might even go down when we're exposed to extreme heat because a lot of blood is sitting in the skin. Consequently, you have to increase heart rate an awful lot. Sometimes I show, to describe this response, I show some data from our lab where we've got a person where we're measuring their heart rate and they're exposed to extreme heat condition. And the heart rate is resting at 70 beats per minute. Then it goes up to about 120 or 130 beats per minute. If I don't give you the context, you'd think that person was running on a treadmill. In fact, they're just sitting there. It's an 84-year-old person sitting in a room, 45 degrees Celsius, and low humidity in that particular case. So that gives you an idea of the level of cardiovascular strain that evolves from extreme heat exposure. It's allied to the fact that your body's trying to keep cool, and through that process of trying to keep cool, it induces this physiological strain. Now, that mechanism is not necessarily directly driven by in lockstep with rises in core temperature. The mechanism is different, and therefore the solutions might be a little different as well. Then we know that people with renal disease struggle as well in extreme heat. With dehydration, this places a lot of strain on the kidneys, particularly with low blood flow as well to the kidney beds, which results in an increased risk of renal collapse in people with renal disease. Now, we've talked about today already about heat-related mortality, and that is the thing that gets the headlines. And indeed, we know that more than 500,000 people die of extreme heat every year. The number in our Lancet Countdown report for 2025 was 546,000 deaths annually due to extreme heat. So if you want to think about that in terms of context, because often people struggle with numbers like that, that's one death every minute of every day due to extreme heat. And that number has increased by 60% since the 1990s. If we account for differences in population growth, it's about 23% increase. But I urge us to think about other things, not just heat-related mortality or morbidity. We count the deaths, but that's the tip of the iceberg, much like the hospitalizations that we count with our health systems. But below the surface, there's a variety of other impacts that affect people across the board, that cost money and cost livelihoods and impact people's lives in profound ways. So we might want to think about this in terms of the way in which extreme heat impacts human health and well-being across the human lifespan. Very briefly, we know that extreme heat exposure during pregnancy increases the risk of preterm birth by 35%. We know that children exercising, playing sport in hot conditions have a much greater risk of exertional heat illness. We know that kids in hot classrooms, teachers trying to teach in hot classrooms impairs people's ability to learn, which have lifelong impacts. In the occupational realm, we know that extreme heat costs the global economy more than $2 trillion a year in lost productivity. As people age, we know that age-related decrements in the ability to sweat render them at a much greater risk of heat-related mortality and morbidity, and particularly, but that is accelerated when we look at the upregulation or the greater prevalence, beg pardon, of other chronic diseases. From a neurological perspective, multiple sclerosis is probably the most prevalent condition that is directly impacted through extreme heat exposure due to the effects of something called UTOS phenomenon, which is a temporary worsening of MS-related symptoms when MS patients are exposed to extreme heat. About 80% of MS patients experience this. When we're thinking about solutions, we need to think about sustainable solutions. We can't just be giving everybody air conditioning. We should prioritize it for the most vulnerable, but it's not the solution for everybody because it's just not environmentally sustainable. We need to think about the way in which these hazards and solutions are interacting with other features of the environment. In Australia, we have to cope with bushfires every summer, which is a big problem that we consider. There are certain parts of the world that are becoming too hot and too humid to become survivable throughout the year, or certain parts of the year, and this is getting worse and things are broadening with climate change. And also we know that extreme heat serves as a secondary aggravator of the risk of mosquito-borne diseases and waterborne diseases. So it's all pretty grim. So I guess we didn't get any more optimistic. I was going to finish off, that was a lot of information. So I'm going to finish off with a bit of reference material for you. As I mentioned, Dr. Bouchama is here. He wrote the definitive review on exertional heat stroke and classic heat stroke, which is published in Nature Reviews Disease Primers 2022. Rob Meade's here. He's going to be talking later on. He did a really nice review on the way in which aging impacts our physiological ability to thermoregulate. The QR codes link you directly to the papers. Dan Gagnon's team from University of Montreal did some great work looking at the cardiovascular aspects, which was published in Annals of Internal Medicine a couple of years ago. And then Davide Filangieri, I don't think he's here. He's at University of Southampton. He does some really great work looking at extreme heat and multiple sclerosis. And so he wrote a really nice review, which is linked there as well, which was published in Temperature a few years ago. I think I went a little over time, but I'm happy to take any questions at this time. Thank you.
Okay, thank you very much. And no, you didn't go over time. I have to say my speakers in my session are fantastic. They've all stuck to time. Questions for Ollie? Oh, one right at the back.
Hi, Ollie. Tom Addison from the Physiological Society.
Hi, how you going?
Yeah, good. Good to see you. Be good to meet you in person later on.
Yeah.
I wondered selfishly if you could talk a little bit about the productivity stat that you used in your presentation and talk specifically about that in a UK context. Is there is that something that is doable, or if not, could you talk more generally around where that loss of productivity is most acutely felt?
Yeah, so I can't give you any statistics specifically to the UK, I'm afraid. We can look them up though, I suppose. In an Australian context, there was a paper that was published in Nature Climate Change back in 2016, I think, and they put the cost of heat on the Australian economy alone at $6 billion a year of lost productivity. That's primarily through presenteeism rather than absenteeism. So this is not people getting sick at work and then not coming to work the next day. This is people turning up and not being as productive. And I think that's seen across the board. There was a report released by the UN, I think, in 2019, and they estimated that the cost of heat to the global economy by 2030 would be $2.3 trillion a year. Again, predominantly through lost productivity. Jason Lee's here from Singapore. He does a lot of work in the occupational sector, and he'd be able to give you some good stats on that as well.
And to add to that, if you look at the last Lancet countdown report, they use the physiological limit of the ability of a human to work outside. And Ollie, thank you for mentioning relative humidity and humidity, because I bang on about this to every medic I ever talk to, because they're all, as you can see from this, just talk about heat. And for that, it's then using climate models to work out how many days around the world it is literally physically impossible to work outside.
Yeah, so I chair the working group 1 for Lancet Countdown. So that's in our working group. And so there's if you look at the Lancet Countdown report, it's indicator 1.1.3, which is changes in labour capacity, and that works with working group 4, which then translates that into economic impacts. And so we're probably going to be changing the model that's being used for that indicator in maybe in the next couple of years. But yeah, happy to talk about that offline.
Question there, sorry.
Thank you. My name is Zaid. I'm from the University of Sussex. I'm a PhD student. Yeah, so you talk about a lot of physiological something. What about, and there is also variability when it comes to the response from
Of course.
person to person.
Yeah.
Is there any way in which, or like, have you kind of like looked at the degree of variability between people? There must be a factor influencing that kind of adaptability.
Yeah.
Is
So,
there
yes,
anything that can be incorporated into lifestyle that can, from that kind of information about the variability of people response?
Okay. Sorry, I just feel like there was multiple questions. Let's just maybe I'll just talk about the variability. So these personal characteristics here, they play a big role in the individual variability. So we've got, I don't know, 80 people, 100 people here. So if we've got everybody to do exactly the same thing in the same environment, we'd have 100 different responses. And we'd be able to predict what the boundaries of what that response would be with quite a lot of confidence, but the confidence increases based on more information we know about those individuals. So for example, aging is a big one. So we know above the age of 60, some data suggest even younger than 60, that there are age-related decrements in the ability to sweat. This is because it's not so much that we send less signals. It's just that at the end, the sensitivity to the neurotransmitter, acetylcholine, which is responsible for sweating, is blunted with age. And so we know that that is an issue. We know that body morphology matters, what you're doing, so how much heat you're producing, factors like this. And then there's also roles of different conditions. There's also, so one of the previous speakers, so Dan, I think you talked when you were trying to describe the difference between the risk ratios for people with Parkinson's, and there was thermoregulation medication. So there's a lot of talk about medications impairing thermoregulation. But our group did a systematic review that we published in eClinical Medicine a couple of years ago. We tried to synthesize all the data that's available that tries to show whether, well, the first thing is that there's hardly any data out there looking at this question. So, but we often default into thinking that things like medication impact thermoregulation, but the evidence base isn't there yet. So there's lots of work to do in understanding the various sources of individual variability, but we can do a pretty good job right now if we know some fundamental things.
Brilliant. Thank you very much, Ollie. We had to move on. I'm very sorry. Catch him at the break. So our next talk is online, and Lina is joining us from the School of Tropical Medicine and Global Health at Nagasaki University in Japan. She serves as the course director for the joint PhD program there between the London School of Hygiene and Tropical Medicine and Nagasaki University. Her research focuses on the health impacts of climate change, including temperature-related mortality, seasonality, and infectious diseases such as diarrhea. She evaluates the health alert systems in Japan and projects future health outcomes under climate change scenarios.
Thank you very much. Thank you very much for the introduction, and also many thanks for inviting me to talk at HotBrain 4. And I'm an environmental epidemiologist from Japan, and I often hear people telling me that after they attend a workshop or seminar on climate change, they feel anxious or worried. But I hope today the HotBrain 4 conference instead will give you a sense of some hope of possibilities and some directions. So for my topic today, it's about the mechanism of humidity impacts on human health. So we already know that humidity has been linked to various health outcomes through various pathways. However, for today's talk specifically, I would like to focus on the role of humidity on heat-related health impacts and health risk, although we understand the humidity can also be linked with infectious diseases, and too dry air is also can link to adverse health outcomes. So first I will discuss why we should care about humidity, why it is so important, and then I will introduce a little bit about the various indicators that have been used to measure humidity. And then I will move from the physiological evidence to the population level epidemiological evidence before discussing the mixed signals from physiological evidence and the population level epidemiological studies. So from Ollie's presentation, we already understand that the mechanism by which heat impacts human health is very complicated. It is actually a result of the interactions between temperature, radiation, wind, and humidity. And with this warming temperature, it's possible that the atmospheric moisture capacity will increase and the humidity in the future will also change, with some regions becoming more humid, whereas some other regions become more arid. Despite of these strong evidence from the physiological perspectives, there is some inconsistency from physiology to epidemiological evidence. So if you look at the figure here on the right, this is a figure from the publication by Baldwin et al., which I believe Ollie is also one of the co-authors of this paper. So in this panel A, you can see that it shows the risk of heat from the past to the future. And then before considering the humidity, from the epidemiological perspective, the association is quite linear, which is represented by this red line here. And if we consider the humidity, when we talk about the impact of heat in the future, which is represented by this blue curve, it's clear it's a non-linear association. So when we want to talk about how this warming climate may affect population health in the future, with and without considering the humidity from two different perspectives, it may give you quite different results, which is represented in this panel C. So Ollie already talked quite a lot about the mechanism of how heat impact health. So when it comes to the role of the humidity on heat-related health impact and risk, is quite straightforward. Under the normal conditions, the body loses heat through three main pathways: evaporation, radiation, convection, and all this process depends on the temperature and humidity differences between the skin and the surrounding air. However, under the extreme heat, evaporation becomes the only effective cooling mechanism. This is why the humidity is crucial. So when the humidity in the surrounding air is really high, the difference in the humidity between your skin and the surrounding air actually reduce, which means your body won't be able to lose the heat properly, and it will result in various adverse health outcomes, such as heat stroke. So before I move into the epidemiological evidence on the role of humidity, I think it would be important to talk a little bit about the different exposure matrix that have been used to measure humidity. Relative humidity first, it represents how saturated the air is. The strength is that most of the researchers and also the public, they're more familiar with relative humidity, and it has been widely used. However, relative humidity is strongly dependent on temperature, which means when we would like to use some statistical models to look at the association between heat and various health outcomes by considering humidity in the model, it may become a bit tricky and complicated. And there is also absolute or specific humidity. It represents the actual atmospheric moisture, and then the strength is that it's physically consistent and is not dependent on temperature strongly. However, it's less intuitive. And if we look at the recent publications, more and more studies, they are using these composite heat indices, which means they combine the temperature and humidity into a single indicator, and it's closer to the physiological experience. However, the difficulty here is that it's challenging to separate the mechanism how humidity and heat affect human health. So there is a really nice review that is published by Davis et al. In 2016, where the authors reviewed the the studies published on the role of humidity on heat-related health impacts, and they have identified 260 literatures between 2030 and 2050 September. And you can see from this table here, from this publication, that around 62% of the publication, they used relative humidity when they look at the association between heat and various health outcomes. And then the other studies use quite different exposure indicators for humidity. And all these studies, they have considered various health outcomes, including all-cause, cardiovascular, renal, mortality, morbidity, and also infectious diseases, such as respiratory infectious diseases. And then the finding or conclusion from this review suggests that although the physiological theory suggests that humidity should amplify the heat-related health risk, the epidemiological studies often show weak or inconsistent independent effects of humidity, which means the evidence from all these 260 literatures is inconsistent and cannot make any clear conclusions. And then after that, in 2019, there is a group, by using the data from multiple country and multiple city research network, which is MCC. They collected all-cause mortality data from 445 cities in 24 countries, and then they look at the role of humidity in the association between heat and all-cause mortality in summertime. And then the left panel here, this figure forest plot, it shows the association between relative humidity and all-cause mortality in these countries. And from this figure, we can see that there is no clear or strong evidence for a positive association between humidity and mortality in summertime, which is quite counter to our expectation from the physiological studies. And then the authors, they have also they repeated the analysis by replacing the relative humidity with the absolute humidity and also apparent temperature. And they also considered humidity as a confounder in their model, and also considered the humidity as an effect modifier of the heat effect in their model. However, they did not find very clear or strong evidence to say anything about the role of the humidity in heat-related health risk. And in 2024, the same research network, they expanded the data set. They collected more data from more countries, and then they used a different approach to look at the role of humidity in heat-related all-cause mortality. And the previous study in 2019, they used the classical time series regression model. However, in this study, they also used a machine learning approach, and then they used 9 indicators for heat and humidity. And then they did this machine learning approach, try to find out which indicator can best fit the mortality in summer season in all these cities. So the conclusion, mainly 2 conclusions. First, humid heat may play a more important role in influencing human mortality in coastal and large lake areas of the United States, Peru, Thailand, Korea, and Japan, where the best fit indicators tends to have a high sensitivity to relative humidity. However, the other regions, such as Argentina or southern Spain and South Africa, dry heat is more closely associated with mortality. So the conclusion is the best fit indicator for heat-related mortality in summertime varies for cities in different regions. And then the authors also use the traditional time series regression model, try to look at the exposure response association between temperature and all-cause mortality in summertime. And then the results is presented here in this panel at the bottom for 4 selected cities: Miami, Ho Chi Minh City, Bristol, and Taipei. And then here, this black curve in this 4 panel shows the exposure response association for ambient temperature and all-cause mortality, whereas the red curve shows the association of all-cause mortality with the best fit indicator for these 4 cities. And among these 4 cities, the 3 cities, except for Bristol, the best fit indicator is actually the wet bulb globe temperature we call WBGT. And just by comparing, eyeballing these 2 curves, black and red, you can see that there are differences between these exposure response associations. Again, it suggests that before and after considering the humidity when assessing heat-related health impact, the results can be quite different depending on which indicator you're using. And then these are the 2 studies that are more on the global scale. Next, I would like to zoom in to East Asia, Japan. In recent years, the interest in assessing the role of humidity in heat-related various health outcomes in East Asia have been increasing quite a lot. I think one of the reasons is perhaps for this region, the summer is always hot and humid. So here on the left side, this is a pamphlet prepared by, published by the Ministry of Environment, Japan, to warn people that be careful of the summer heat in Japan, which is usually hot and humid. And in Japan, the summertime, the relative humidity most of the time is above 70 to 80% in major cities. Let's take Nagasaki, where I live, as an example. During summertime, the relative humidity for most of the time is always above 80%, sometimes can be above 90%. And then here, this panel, the bar plot here, it shows the annual cases of heat stroke ambulance dispatch from 2015 to 2025. So you can see over the years, the numbers have been increasing dramatically. And in 2025, it is more than 100,000 already. And here in 2018, when there was a extreme and very long heat wave in Japan, the numbers are quite high as well for heat stroke ambulance dispatch. So because of these reasons, in 2021, the Japanese government changed the indicator that they use to issue the heat alert from ambient temperature to wet bulb globe temperature, WBGT, reflecting the growing concerns about the escalating humid heat stress. So, and then this figure here is from a work by our colleague, where he used 9 indicators, temperature and humidity indicators, and used a machine learning approach to predict the ambulance dispatch by all cause, circulatory causes, respiratory causes for different age groups, and also specifically for heat stroke ambulance dispatches, which is in the 3rd row here. And then the brown bar, the bar in brown color, shows the results for the WBGT. And the higher the bar, that means the performance of this indicator is better. So for heat stroke ambulance dispatch, and also for all-cause ambulance dispatch, as well as for non-external ambulance dispatch in Japan, the analysis demonstrate that the distinct advantages in using this WBGT for predicting these daily heat stroke and non-external all-cause ambulance dispatch cases. So as you can see that the evidence are quite inconsistent. Due to the limited time, I was not able to show the other recent evidence from, let's say, South Korea and China. The results, again, is not consistent. So there could be several reasons to explain this inconsistency. First of all, you can see that there are various metrics that we can use to represent the exposure to humidity. Myself, I am still trying to learn the differences between all these indicators in our epidemiological studies. And second, I think the selection of the health outcome are also quite important. Although heat can be linked to various health outcomes, a range of health outcomes. However, those health outcomes that are specifically or more sensitive to heat and humid, especially humid heat, may be different. And most of the epidemiological studies, they use all-cause mortality or morbidity to look at this topic. That might be one of the reasons. And then another reason, it could be also the temporal resolution of the exposure and health outcome. Most of the epidemiological studies at the population level, we use daily or even weekly number of cases or average exposures. In that case, it may lose some of the, may mask some of the association between the humidity and heat-related health outcomes. And last, as an epidemiologist, I have to say that some of the studies, their assumptions on causal pathways are quite unclear between humidity, heat, and health outcomes. Some of them consider the humidity as a confounder, some of them consider as an effect modifier. I think the clear clarification and assumption on these causal pathways may be helped to answer some of these mismatches. And at the last, I have to say, when I was trying to search for them evidence for the other regions on humidity, heat, health, I noticed that the evidence from the low middle income countries are quite limited, such as Southeast Asia and Central Asia, for example. I think this could be due to the limited evidence or limited data on exposure assessment and health outcome measurements. So take-home messages. First, humidity affects how heat is experienced physically, and we have strong mechanisms, but the epidemiological signals are still inconsistent, and understanding the humid heat requires interdisciplinary collaboration. So I hope this will give us some direction for future studies and collaborations. Thank you very much. Sorry, I'm too long. Thank you.
Thank you, Lina. I have to say you were absolutely dead on 15 minutes. I'm incredibly impressed with everybody. And also, by the way, you're my new hero, okay? Because relative humidity or humidity has been the drum that I've been banging for many years. So we have questions. We've already had a question from him. Are there, no disrespect, are there other people? Otherwise, yes, there. Sorry, I'm just trying to spread the love.
Thanks very much. Josh Foster, King's College London. It's just more from the physiological side, really, and perhaps it sparks some discussion. It's more of a statement, really. But in terms of the human response to heat stress, it's really fundamentally the absolute humidity in the ambient environment that determines how much sweat can then be evaporated. So do you think, so really from our perspective, you know, the relative humidity means almost nothing in terms of the human response to heat stress, because at least in the morning, the relative humidity is going to be substantially higher, approaching 100%. So we clearly can't take, you know, maximum relative humidity during the day. So how is, in many of these studies, what metric are they using to determine the humidity? If it's the maximum relative humidity in the day, then that's going to be in the morning. Do they take the maximum absolute humidity?
Thank you very much for this question. This average, usually. Most of these studies I discuss or introduced here, they take this average. They don't take the maximum.
Yeah, so it might be a consideration and a talking point then, because it should be really the combined absolute humidity in conjunction with the maximum temperature, from my perspective at least, anyway.
Exactly. So I think one of the motivation for using the daily average, perhaps in most of these epi studies, the outcome is the daily counts. for example, heat stroke cases or daily count of all-cause mortality or hospitalization. It represents the health outcome within the 24 hours. So perhaps that's why we try to use this daily average instead of using the maximum. But I think if we can have the hourly health outcome, for example, especially heat stroke, we may be able to find more stronger signal by linking the daily maximum or even daily hourly humidity index with the hourly health outcomes.
Brilliant. I think that is an incredibly important point, Ollie. I know, but I'm out of time. I apologize. This is where I believe we have a coffee break.
To introduce the first speaker, who is Dr. Bouchama from the Experimental Medicine Department, King Abdullah International Medical Research Center. And he is going to speak on the lived experiencing of managing responses to mass heat illness. So you're very welcome to come up.
Well, thank you very much for inviting me to share my lived experience of managing response to mass heat illness. And this is my disclosures, according to the Federation of the Royal College. But before Mecca and mass gathering, there was Constantine. This is a 3,000 years old Mediterranean city. And I had to cross this suspended bridge 200 meters high every day to go to the hospitals where I get trained in internal medicine. In 1977, I moved to Claude Bernard in Paris to learn intensive care, and I practiced there for around 8 years before going to Saudi Arabia. So this is in a capacity of intensivist. So when I arrived to Saudi Arabia as a consultant, in the summer of that year, they told me, well, we need you to work in Mecca and to help the pilgrim. And they do that for many physicians because they open field hospital around the holy site. And I end up in a small hospital behind the bridge called Mina al-Jasr. Al-Jasr simply means the bridge. And so we went there for 4 weeks to prepare, and I was preparing the ICU, the respirator, the cardiac monitor, and people were asking me, my colleague, have you ever seen a heat stroke patient? I say, no. Have you treated heat stroke patient? No. And actually, it was in Paris after 4 years of intensive care, we never studied heat stroke. We knew everything about hyperthermia due to malignant hyperthermia, neuroleptic malignant syndrome, recreational drugs, thyrotoxicosis, but not heat stroke. Now, day of the patient arrived to this Mina, you see this, this is one of the main sites for the pilgrimage. They stay here 3 days out of 5 days. And you can see that Mina is a really narrow desert valley where the temperature can really exceed 45 degrees. So when the pilgrim arrived, around 9:30, 10 a.m., we start to see patient coming, very sick. Patient in coma, patient with seizures, in respiratory failure, in shock state. And so I was a young intensivist, but solid training in intensive care. I was used to see this sick patient, but never so many patients in the same time. Now, we cooled them in this bed created by Weiner and Khogali in the 80s. And you can see the patient here is lying in like a net. He's in lateral decubitus to protect his airway. And it's a net because this patient has severe diarrhea. And the diarrhea is due to the injury to the gut. The jejunal mucosa is extremely vulnerable to heat. In addition, they are cooled by spraying cold water, and this is in this water in this tank here and here. So they spray 45 the water at 15 degrees all over the bodies. At the same time, they blow hot air around 45 degrees, which arrive to the skin around 32, 33. And the reason is to maintain the skin temperature at 32, 33 degrees. This allows the circulation to be optimal. So there is no vasoconstriction induced by the cold, and there is no shivering. Now, the year after, this paper came out from Dr. Ghaznawi. Dr. Ghaznawi is the medical director of the Mecca region. And this is 6 consecutive pilgrimage. And I want you just to concentrate on this August 1985. So this is the year before I arrived, there were 852,000 pilgrims, and you see 2,134 heat stroke, of which 50% died in 5 days. In addition to heat stroke, you can see there were 5,560 heat exhaustion. Exhaustion is a mild to moderate illness. Temperature is usually less than 40. They have no neurological alteration, but they are hypotensive, they are dizzy, they have syncope. They need to be rehydrated in the emergency room. So it's easy to understand if you have 8,000 people coming to the emergency room in 5 days, very sick, that the system gets overwhelmed. So for us, when in 2003 in France, when the system was overwhelmed, it's not a surprise, because you have an epidemic scale of patients that are extremely sick. Now, so I went back to the hospital and to see what exactly this heat stroke, why the patients are so sick. And at that time in the 80s, they just consider heat stroke as a part of what they call the thermic stress syndrome, part of this 5 disease, and including malignant hyperthermia, which the only one has a treatment, which was the dontrolene of sodium. Malignant hyperthermia is a calcium channel disorder of the muscles, and in healthy people, but when you give them anesthetic, it induces very sustained contraction of the muscles, irreversible, leading to death. The advent of dontrolene sodium changed the outcome and allowed to improve this or reduce this sustained contraction, so mortality went down to 5%. And at that time, they say, well, heat stroke is malignant hyperthermia, but triggered by the environment, not by the anesthetic drugs. And there was some case series, as usual, given to this patient and show improvement. So we went the next year with a double-blind randomized study. That's the first study we conducted in Mecca was a double-blind randomized study, and actually is only one in this field. So we did not see any difference. There was no difference in cooling time between treatment and control group, but we learned a lot of things. These are 52 pilgrims that we recruited prospectively there in 5 days. And you can see here, the heat stroke is defined by the triad of hyperthermia and CNS alterations, such as convulsion, coma, delirium, textbook definitions. Of course, indeed, we confirmed the hyperthermia, but it's very severe. The median temperature was greater than 42. Then the CNS alterations, we quantified that using the Glasgow Coma Scale. The Glasgow Coma Scale, for those who are not familiar, range from 3 to 15. 15, you are normal. 3, it is the deepest coma you can have. And please note that 38% were in coma. So severe hyperthermia and severe neurological alterations. But in addition to that, we could see that they have hypotension, shock state, 25%, respiratory failure requiring intubation and mechanical ventilation. This means that these patients were near respiratory arrest. And then you should trust me, I will not show you the data and biochemical data because of the time's sake. They also renal dysfunction, liver injury, rhabdomyolysis, hyperglycemia, hypophosphatemia, a storm in the body. the point here is that the definition of heat stroke is misleading. Heat stroke is an early multi-organ injury. Now, but the most important point that we learned is that after we normalize the temperature, we expected this organ dysfunction to improve. Yes, it did improve, but not in everyone. 25% in this series continue to, not only did not improve, but continue to deteriorate. So the question for us is that if it is not the heat only that is killing them, what else? And this question, to answer this question, is almost took us, at least took me 40 years. Now, we went back to Mecca, looking at mediator of this injury, and heat stroke looks like a sepsis, septic shock. Especially that there was in the 70s some case report showing that there is endotoxin leaking from the gut in the circulation. Endotoxin is very toxic for us. So we confirmed that. This is the LPS here, lipopolysaccharide. This is the wall of the gram-negative roads, toxic to us, toxic to animals. And you see massive release of endotoxin in the circulations. Another time also, we start to see the cytokine coming in the I would say in the market. So the TNF was central to the pathogenesis of septic shock, and we show that the TNF is high, the IL-1. We know now this is not the answer. So it took us 10 years to rectify the definitions that we proposed in England with my colleague from Texas, James Knockel. We say that while heat stroke is a form of hyperthermia associated with a systemic inflammatory response, leading to a syndrome of multi-organ dysfunction in which encephalopathy predominate. Encephalopathy predominate. That's extremely important here. More recently, in a systematic review, we confirmed that in 2,632 patients in Mecca, that, I think you can see the multi-organ failure. We see them an hour to half an hour when they collapse, so very, very early. And again, so you see the mean Glasgow coma score of 4.7, which means that the brain injury is really out of proportion of the other organ dysfunctions. Now, this was a population level. When you look at individual level, and this is a very important paper by a neurologist. So he examined these patients over 2 consecutive pilgrimage, and he shows something very striking, this brain death-like picture, which means they have no reflex, no cornea, no peripheral, the pupils are constricted, 70% not reactive. This is a definition of brain failure. So we don't use these expressions. We use heart failure, liver failure, but never brain failure. For me, that's a brain failure. And then what is also striking is that from the data, I will say 86% recover. But the one who don't recover go and die or keep sequelae. So it's very important to answer this question in order to have a brain preservation strategy. What's the mechanism? Now, this picture I took myself from the roof of that hospital, and you see that Mina now. And so the Saudi government implemented a lot of mitigation measures, and you can see that individual structural system, but look at the tent, modern tent, fire-resistant air conditions, modern transportation with AC, train transportation, greening, walkway, and that's translating improvement. So when you look at the incidence of heat stroke and the case fatality rate between 2 hot cycles, this is, I was here in the first hot cycle, and you see that the reductions. This is the cold cycle. Of course, there is no heat stroke or heat exhaustions. But Mecca is warming. So when we look at the temperature over 40 years, we can see that there is an increase of 0.4 degree dry bulb temperature per decade and 0.2 wet bulb temperature. So Mecca is warming higher than the global average. Now, in conclusion, I think heat stroke is a neurological emergency. the encephalopathy-defined syndrome. MACA is a real-world reproducible model because the dose is outdoor temperature. Is not a heat island, is not a small building at the 5th floor of a suburb. These are all exposed to the same way because of the strict ritual. The response is also very accurate because this is not the black box of heat-related death. These are heat stroke. So there's a very strong phenotype. Now, for the last 10 years, I mean, it's not just a lived experience, clinical experience, but it's also a lived translational research. I think the paradigm is going to change again. We think that this is a proteotic stress, a bioenergetic crisis, and it goes along with the brain failure. The inflammatory response appears tardy at the time we saw the dontoxin, but then meanwhile we demonstrated that dontoxin play a minor role. This merely is a sterile inflammation due to this damage-associated molecular pattern. And then MACA is warming, the mitigation measure works, but not for a long time because the predictions are not very good. So the next horizon will be, we think, is a precision public health response as ambient height continue to rise. Thank you.
Thank you very much. That was a fantastic talk. I've always been curious about the core temperature thresholds that we use for heat stroke. And from your perspective, do you think that that's actually much more dynamic and variable in the sense that in a young, healthy individual, that threshold of around 40.5 is probably very accurate for my impending doom. But if we take a frail older person with comorbidities, is it likely that they could have that same sequence of events at a much lower core temperature? And if that's the case, do we need to redefine heat stroke risk in some senses?
Yes, I think I get. Yes, I get this. Yeah, actually, this. Thank you for the question because until now, the heat stroke definition is based in the temperature. And then we see, Ollie Jay and the group and Robert Meade and many people working the threshold temperature, which means that we restrict the heat stroke to a thermoregulatory failure. We know now that because we're doing a lot of molecular research, we know that there is another defense mechanism, which is the heat shock response or stress response, heat stress response. There is a different appellations. This is a conserved mechanism that protects the cells from the effect of heat. And what did they protect exactly? They protect the macromolecules, which means protein, the DNA, the lipid. So this protective mechanism exists before humanity. Actually, it exists in single cells and is conserved for 2 billion years. When we put volunteer in a sauna, young, and we could see that we activate this heat stress response and is exactly conserved like the yeast, like C. elegans, like the Drosophila. So the temperature is just physiological stress. What determines the health is the biology, is whether this defense system protected your cells or not. So I think the paradigm will change. So the heat stroke will be a failure of both thermoregulation and the heat stress response. If you agree with that, this means that this will explain why we have this variation between people. In addition, of course, to comorbidity, the age, the sex, etc. But the difference probably is in that in this heat stress response, this inner protective mechanism.
But do you think the threshold for triggering that it might be lower with age, with higher age, like if you have an 80-year-old person or a 20-year-old person?
Yes, we looked at old and young who developed heat stroke, and we looked at the whole genome transcriptome. And you can see that, yes, we activate induction of heat shock protein and the enfolded protein response, which means that we have a severe proteotoxic stress. And we compared the old to the young. And we see both of them activate this stress response. But the elderly terminated very quickly, prematurely. And so we think that one of the mechanisms, the difference is because of this, yes, the protection of the cells. In addition, of course, to the limitation, the cardiovascular, the kidney, and
okay, great. Okay, I think in the interest of time, we'll move to the next talk. But just to thank a great talk once again. Thank you.
Yes.
So the next talk is a recording from Sanjay Sisodiya, because as mentioned earlier, he was unable to attend because of a family emergency. Sanjay has been doing a lot of work on mechanisms and in particular genomic vulnerability to effects of temperature. So we're going to just put the recording on. So hopefully Sanjay will keep to time.
In this session, I want to talk about a different type of mechanism of impact of climate change on people with neurological disorders, and that's genomic vulnerability. Innate vulnerability to, for example, high temperatures. Now, genomic vulnerability to environmental factors is, of course, a well-established concept. For example, any of us might take an antibiotic and we might happen to carry a genomic risk variant that would mean that we would react badly to that antibiotic, for example, with a nasty skin rash or with disease affecting the liver or other organs. In this session, I'd like to propose that there may also be genomic variants, which we're calling calotypic variants, which may also make people vulnerable, for example, to heat. My interest in this whole area arose from the experiences of people that I see in clinic and of their families during the recent heat waves we have had, the more intense and heat waves with higher temperatures that we've been experiencing in the UK. In my clinic, I see a lot of people with complex epilepsies that are often genetically driven. One example of that being Dravet syndrome, which is one of the more common rare epilepsies with a very characteristic phenotype, one aspect of which is a sensitivity to temperature. And families of adult children with this condition were reporting that during our recent heat waves, people with this condition were experiencing a worsening of many aspects of their condition. For example, seizures, but also lethargy, irritability, behavioral difficulties, and loss of appetite and thirst. And here you see the some of the people who are members of the Dravet Syndrome UK charity. I'm grateful to the charity for the use of this picture. And below you see some comments from family members. So, for example, during a heat wave, one family reported that in the hot weather, their child's body temperature climbs. She then has a tonic-clonic seizure, which 9 out of 10 times becomes status epilepticus, resulting in respiratory arrest. Another family reported that on days of extreme heat, my husband and I moved our son into my husband's parents' house, which was marginally cooler. We borrowed an air conditioning unit, kept curtains and windows shut during the day, and purchased dog cooling pads for him to sit on. And you can see that people with this condition, their families, are already having to adapt to the impact of heat waves. And actually, once you start asking people, you find that they are already doing things. This is not just in rare epilepsies, but across different neurological conditions. Quite often as clinicians, we don't ask people about this. We don't have the time or the experience or maybe the confidence to discuss this. But once you start asking, you find that actually people are already doing many things to try and keep themselves and their loved ones safe during heat waves in particular. And there are other conditions in which temperature has an effect on the phenotypic manifestation. So, for example, here we're looking at a condition called mevalonic aciduria, in which the enzyme mevalonate kinase may be affected. So this is an autosomal recessive condition. Biallelic loss of function mutations in the gene that encodes this enzyme leads to a metabolic defect, for example, with abnormal prenylation, and this leads then to subsequent phenotypes such as recurrent fevers, neurological features, and systemic inflammation. And people with this condition already experience a worsening of their condition during heat. In this animal model that was created, it was clear that even with a small rise in external temperature here from 37 to 40 degrees C, there was a worsening of the metabolic defect, as you see cells moving from this phenotype to this phenotype, which was reversible when the normal temperature was restored. And you can see that the activity enzyme fell from less than 20% of residual activity in this model to less than 2% of the residual activity at this higher temperature. This was also associated with a higher rectal temperature change in the mutant mouse compared with the wild-type mouse. And you can see that the enzyme activity, already low, fell significantly with a significant rise in mevalonic acid with all its consequences. So there are many examples where already we know that a genetic change leading to a disease can be aggravated with increased ambient temperature. Here's another example. This is back to the gene SCN1A variants in which can lead to Dravet syndrome and other epilepsies, including GEFS+. And here there are two variants being studied. The one in green leads to the milder epilepsy phenotype of GEFS+, and the one in purple here leads to the more severe phenotype associated with changes in SCN1A, which encodes this sodium channel, which is of course Dravet syndrome. Now there are complex changes going on as a result of these two variants. At normal body temperature, changes in the gating function of the encoded ion channel. What's interesting is that when the temperature is changed from 37 to 40 degrees C, you see complex changes in that gating function with perhaps new abnormalities emerging. And there are significant changes in these gating variables associated with this change in temperature from 37 to 40 degrees C, which differ between these two variants. So you can see they're at the same amino acid, but you have different changes with the different mutations leading to change in behavior of the channel, which is quite different at different temperatures. There are now some models available that enable you to look at the structure and eventually the function at different temperatures. And of course, if we could apply this systematically across diseases, this would be a very important way of understanding what different temperatures might do to people with different neurological disorders driven by genomic change. So what's clear is that genetic variants, of course we know, can alter protein function. And altered or alteration of protein function may be differentially sensitive to ambient temperature. So if you change the temperature, the function of the mutant protein may also change. It may become more extreme, or it may change its characteristics. There are some reported variants that can change from loss of function to gain of function with a change in temperature. So these variants are already known to exist, and we've grouped them together and termed them calotypic variants. And we were interested to try and determine which variants across the genome might be calotypic. What's the universe of such variants? So this is an active project, and this first study, which was led by Ravi Shankar, here shown here, looked at just manually curated data from the literature and identified a set of genes, all shown here, in which there are variants which we would now term calotypic. That is to say that the function of the encoded mutant protein changes with ambient temperature. Now we of course know that if you change the temperature enough you can denature any protein, but here we're talking about functional changes that are reversible and that are seen with different temperatures. And in fact we identified, we categorized these into four different groups. Variants where, for example, function might deteriorate with an increase in temperature, which we call heat intolerant, and shown here in the red. And in fact, the majority of these calotypic variants are heat intolerant. So most variants that we identified in which function is changed by the temperature of the experiment show a sensitivity to heat in particular with worsening of function. But there are other variants which are heat tolerant or cold intolerant or cold tolerant. And if you then look at the temperatures at which these changes in function occur with respect to the temperature of the human or animal brain, you can see that there is a significant overlap for those that are heat intolerant or heat tolerant, whereas you can see obviously that the cold intolerant and cold tolerant variants will be showing their changes in function at quite different temperatures, often much lower than brain temperature. And some of these are involved in diseases, for example, of the peripheral nervous system. So we have this basic set of calotypic variants. This is just through a manual search of the literature. There are bound to be many, many more calotypic variants that we have not yet discovered. And we are now embarking on a project to systematically curate these variants. Eventually, we hope to have a tool that produces an ongoing updated list of such variants, which will be broadly useful, we hope. Now, if you look at the diseases which are associated with these calotypic variants and the groups they fall in, for example, cold intolerant or heat intolerant, you find that most of the diseases are heat intolerant, and the vast majority of them are associated with neurological or neurodevelopmental phenotypes or metabolic disorders, which is of course common clinical experience. And here we've just listed some of the particular conditions that these diseases are associated with. And you can see, for example, that inherited epilepsies are one of the most common set of conditions to be prone to the effects of calotypic variants. When we searched for this small set of about 150 calotypic variants that we identified initially in the Genomics England Rare Disease cohort, we found that about 1% of people carried these variants. But as the numbers of calotypic variants increase, we will find many, many more. So if you look at how the genome, the expression of the genome changes with temperature in a very simple experiment undertaken here in fetal astrocytes, which were cultured at just 2 degrees C above 37 degrees C for 6 or 24 hours or 48 hours, you can see that about 10% of the genome shows significant differential expression. So some genes are expressed less, some genes are expressed more, even after a short period of incubation at just 2 degrees C higher than the normal incubation temperature one might want to use. And if you look at the pathways that these genes fit into, you can see there are a variety of different pathways that are affected. And what's particularly interesting is that if you look at the spatial pattern of expression and look particularly to see where which of these genes is expressed in the hypothalamus, which we know controls temperature regulation in the human body, then you find that there's a significant overlap of genes whose expression is changed and of genes which are associated with epilepsy in the hypothalamus. So in fact, 97% of genes that are now associated with epilepsy are expressed in the hypothalamus, and you can understand how a genetic variant that causes a significant change in the associated function would lead to a change in the function of the hypothalamus and therefore potentially disordered thermoregulation, even without any changes in the ambient temperature. And 22% of epilepsy genes expressed in the hypothalamus in fact show a significant change in expression with that simple 2 degrees C rise in that fetal astrocyte experiment. So if you expand this across neurological disorders, you can see how many, especially rare neurological disorders, might be vulnerable intrinsically to changes in ambient temperature because thermoregulation will be disrupted. So global temperatures, we know, we've heard earlier in the session, have changed by about 1.4 degrees C or more already compared with historic averages. And the concern is that this will bring out functional changes associated with calotypic variants leading to disease effects. So this might be an aggravation or worsening of symptoms, as we see, for example, in Dravet syndrome, or it might be the emergence of a completely new phenotype in association with an increased ambient temperature, what we might call thermolatent phenotypes. And these are, of course, of significant concern because we might be seeing whole new conditions emerging from variants that previously have been innocuous. And temperature matters. So in some elegant experiments undertaken by Yves Marder and a team looking at the crab enteric system, you can see that at various temperatures the crab enteric system might still maintain a rhythmic behavior, which is what it should do, but at certain temperatures that rhythmicity is lost and the system, as Yves Marder calls this, crashes. And what's interesting is that the temperature of crashing might actually be dependent on how that crab has been exposed to various temperatures in the North Atlantic in the first place. So if the North Atlantic is higher, then actually that crash temperature might be higher. If the North Atlantic temperature is higher, that crash temperature might be higher, suggesting that there is some memory of exposure to ambient temperature. And this is potentially something that we could use in terms of conditioning, for example, of people with neurological disorders to an upcoming heat wave. Now, it's going to be a complex and difficult thing to do, but actually not necessarily that impossible, especially with more widespread use, for example, of saunas. And this is something that has already been explored for various other conditions, and we might consider also for neurological disorders. Temperature, as you can see, clearly matters. And one of the things that we were very interested in is, can we learn something from existing neurophysiological experiments? Can we look at the temperatures at which these experiments were done and see if this tells us something about these neurological disorders? So what we did was to look back at experiments. This was the work done by led by Emre here and Medina and Seamus, and they looked at a year's worth of literature of neurophysiological experiments in epilepsy, to see what sort of temperature ranges cause what sort of disorders. What was really concerning in their study was that in 33% of neurophysiological experiments in epilepsy in 2022, the publications did not report the temperature at which experiments were done. There was no information or insufficient information in order to be able to reproduce that experiment. So having hoped to learn a lot about what temperature change might do to neurological disorders from this review, what we instead found was that actually for a third of publications we had no idea what the temperature was, or it was stated to be room temperature, which of course is meaningless. And what's also important to note is that the temperature at which these experiments were undertaken, shown here for example for human studies, were often significantly below recorded brain temperatures in humans, or indeed for rodents, for rodent experiments. So not only is the temperature not reported at all in a third, but in many of the other experiments where temperature is reported, it's actually of little relevance to human brain function in vivo. Temperature matters. So overall, what we can say is that temperature influences functional consequences of these variants, which we're calling calotypic variants. The set of calotypic variants is likely to be large and will continue to grow. This may be associated with the emergence of thermolatent phenotypes as temperatures worsen and heat waves become more intense. Temperatures can also change gene expression, and given that many brain disease-related genes are expressed in the hypothalamus, you can see how there can be complex feedback loops where calotypic variants and other variants disrupt thermoregulation, and where the expression of these genes can be altered by heat, so that actually the behavior in a heat wave can become really complicated and may also have emergent properties, something that we've never seen before. I think what's critical also is that too many studies do not pay attention to temperature. So overall, we can see how genetic vulnerability might be an important mechanism of vulnerability to the impacts of climate change. And that temperature alone, not even considering other factors like humidity, temperature alone has a multi-layered risk profile for human brain health. And there's really much more that we need to do to understand this better. I'm sorry I can't be there for questions, but please feel free to get in touch if you do have questions, and I'd be very happy to discuss this further by email, for example. So I'd like to thank the whole of my group who've really contributed hugely to all the work that I've presented here, and especially, of course, in the blank square, all the people that I see with neurological disorders, from whom I continue to learn so much, and for whom I think there is so much still that we need to do. Thank you very much.
Okay, so just to thank Sanjay, he only ran slightly over time, so we'll let him off. So clearly some links between the first and second talks in that there's going to turn out to be a range of genes that determine vulnerability, perhaps relating to the pathways that were discussed earlier. So I think we're going to move. Delighted to welcome Institute of Pharmacology, Heidelberg University, Germany, and it's going to cover the topic neuronal and network plasticity.
So thank you very much. Pleasure being here. Sort of a first to this breadth and this focus with neuro. I myself neurophysiologist, biochemist, physiologist working at universities. My just here just to present them. I think I should disclose that we work. The great privilege to do this is also a big risk. I think one thinks about complex interactions, how temperature in our interacts with the nervous system and how that drive. Okay. How temperature affects nervous system function and how it drives behaviors. That cannot be done. Still be done yet by organoids and other systems. So I can still instrument this. So my background is really starting from this when sensory physiology, essentially, when we touch a hot plate, how those signals, how those temperature signals drive in the brain to cause a painful sensation. And
hear this now on.
Okay. So sensory physiology. So this is quite well established, culminating in another trip ion channels that play a central role in translating physical impact of temperature in the nervous system to give rise to a painful, noxious sensation. But how these intricate signals, more subtle signals, really drive temperature regulation and how particularly long-term changes in ambient temperatures drive adaptation and heat acclimation is something that is much less known. So we can adapt to rising temperatures. Sanjay just mentioned that already. So you can condition yourself. There is, of course, a limit to this. But one hypothesis that we, or my lab also focuses on is, can neural plasticity, can that be a key driver of heat acclimation? So trickling down from the thermoregulatory system to peripheral organ systems to help adapt to long-lasting temperature changes. So just to start off a little bit with how thermoregulation works and in our favorite model organism, mouse. So you can see here, if it's too cold, for example, the mouse can recruit the brown adipose tissue to generate heat. It's an important thermogenic organ in the mouse. If it's too cold, it can shiver. If it's too hot, as we heard before, also for us, it can dilate blood vessels, particularly in the non-furry part in the tail to dissipate heat. It cannot sweat. So Ollie pointed out sweating is a very important point for us to cool down. The mouse can spread saliva, but it's not very efficient because the fur is there. So mice are actually not as good as we are to cope with heat. But then there's, of course, also behavioral thermoregulation. Mice can move to cooler places into the shade. So who is orchestrating all this? One critical component, as Sanjay also just mentioned already, as Ollie mentioned also, the hypothalamus, the preoptic area in the hypothalamus can drive signals. It is a little bit you can think of as a thermostat, not as static as a thermostat. It's much more flexible and adaptive. It drives sort of peripheral changes based on temperature inputs that it receives from the periphery. And it's believed that in the human, of course, we don't know as much, particularly on mechanistic detail, something similar happens. And I mentioned temperature signals from the periphery. What is interesting is that the preoptic thermostat is intrinsically temperature sensitive. So also deep brain temperature is sensed there and integrated to make sort of a concerted output to maintain temperature, core temperature homeostatically. So why does that matter to deep in the brain? Is there any temperature change? And yes, it is. So here we recorded temperature at different brain sites, implanted tiny thermocouples into the mouse brain. And you can see here that temperature fluctuates actually across the day, and it depends also where you are in the brain. So this is a mouse freely moving, actually, no anesthesia here, and you can see at room temperature the cortical temperature is actually lower than the preoptic temperature. The preoptic temperature quite nicely tracks core body temperature, and that's probably because of the blood flow that is distributed first, coming from the heart via the arteries to the hypothalamus. So the take-home message here is brain temperature is not static. It fluctuates, and at normal ambient temperature, the deep brain centers seem to be hotter, at least in a mouse, and there's also data for humans for this, than in the cortex. There's not much insulation here, so if it's cool outside, cortex actually is rather cool. So if you then look, or we looked at the time at different physiological states, how the preoptic temperature, the deep brain temperature changes. So each dot here is an individual mouse where we recorded body temperature and POA temperature. You can see mice here in light yellow during the day. That's the sleeping phase of the mice. It's a bit cooler than when they wake up at night. The body temperature rises a bit, so does the POA temperature. If you look at fever, body temperature, of course, rises. That's sort of one aspect of fever, but also the POA temperature rises. If you look at metabolically compromised mice, which are known to have a lower body temperature, also the POA temperature is lower. So there is a strong correlation between body temperature and deep brain POA temperature. And here the main point is, physiologically speaking, the brain temperature varies almost like 5 degrees Celsius along different physiological sort of paradigms. And that has also been suggested to happen in humans, healthy. So there are many studies, several studies by now using MRI and other mechanisms suggesting that in healthy participants during different times of the day, different conditions, body temperature, brain temperature also fluctuates. Why could this be also important? Well, one aspect is that this temperature can be detected in the hypothalamus. As I said, they are intrinsically temperature sensitive cells. This is what they look like. So they are known since many decades. So these neurons, they fire, and they fire finely tuned to temperature changes in vivo and ex vivo. So many studies use brain slices for this. And when I entered the field coming from the peripheral temperature sensing neurons, which respond quite differently to the central temperature sensitive neurons, I was quite interested in also understanding what is the mechanism that allows these neurons to fire in such a way. And most of all, is this actually important for temperature regulation? Because these neurons are sitting in what I call here a little bit simplified the thermostat. So would these neurons, when they fire more, would this be the information, oh, it's getting too hot, we need to cool the body? To test this, Hong Wang, at the time postdoc in the lab, we used the rich repertoire of neuroscience tools that you can use in genetically accessible organisms like mice. So we implanted a switch that essentially don't have time to go into the details how this works. You can switch these neurons on either by light or by chemical. It's called chemogenetics. And you can mimic what these neurons would do when it's hot, when they fire. And we asked a simple question: when we turn these neurons on, what would happen to body temperature? So, and this I show you here in this infrared experiment. So it's an infrared camera on the top. You see the mouse down here. Here's the tail, which is at this point at room temperature constricted. The mouse conserves heat because room temperature is slightly cold for mice. And now what happens in this movie? First, again, the controlled condition. The switch is not yet on. You see the mouse moving around. Tail is quite constricted. But now we switch these neurons on. you can see immediately the tail of these mouse lights up, dissipate heats to the surroundings so much that the surrounding lights up, with the effect that the body cools dramatically, almost 10 degrees body temperature drop that these mouse experiences. And when the switch is flipped back off, the mouse come out of this torporic state and is fine and walks around. So this is, of course, an extreme condition, but it clearly shows that activating these thermoregulatory neurons can drive cooling of the body. But this is, of course, artificial. We don't have switches in our brain to do this. So we asked what conditions really can do this maybe naturally. And of course, heat, we know, activates these types of neurons. So can heat stress and long-term heat acclimation have an impact on these neurons and affect their function? So what we did is, or most of us who work with rodents and animals keep, and I was very happy to hear that Sanjay just mentioned this, we need to report temperatures when we do our experiments. Room temperature is classically, at least in our vivarium, 22 degrees, 23 degrees. So we expose these mice to up to 36 degrees. This is really hot for mice. Like I said, they cannot sweat, so they don't have an active cooling system. So we slowly adapted them to be able to live in these repurposed incubators, light controlled. We measure their body temperature telemetrically, humidity controlled. We had the talk this morning. In this case, we have 30–40% humidity. And we asked the question, what would this do to the animals? Physiologically, this is quite well established. If we or mice adapt to heat, and given the time, doing it subtly, not like a heat wave, but really slowly and subtly, it reduces heart rate. That's also known in humans. It's not what happens under heat shock when the heart rate goes up. It is more conditioning like an athlete. You reduce the heart rate. The mice switch off their fat metabolism. They lose actually brown fat. They eat less. They change their fluid balance, and also they change behaviors. And many of these aspects are there to accomplish that the body temperature don't spirals out of control. So all these things work together to do this. And this we can measure. So we measured heat tolerance. Sarah, former postdoc in the lab, she established this heat tolerance assay. So essentially what we did in this reductionist approach, we acclimatized the animals for several days, up to 30 days, up to 36 degrees, and then did a heat tolerance assay, a really high temperature challenge, measuring online their body temperature. And this is what this experiment looks like. So you see here time versus body temperature. Maybe you can first pay attention to the control animals. If you have a cold acclimatized mouse, a normal vivarium mouse, you can see it can tolerate heat for up to 6–7 hours before the body temperature reaches this cutoff here. So this is the end of the assay. We take the animals out and let them, of course, recover from this. If you do this for 24 hours, not much changes. It actually gets worse because the conditioning, it's like an athlete training. The training program is taking its toll, so to speak. And of course, then to strain the animal even further, it doesn't do much better at all. But if you do this subtly over a long time, you can see here these mice tolerate heat more and more. And we can quantify this. We call this the endurance time or tolerance time. And you can see it goes up if you acclimatize animals for a longer time. Key question for us, this gain in heat tolerance, does that depend on our favorite POA neurons at the thermoregulatory center? And we started very naively in some ways and asked, okay, if a strong signal, sensory signal arrives in the hypothalamus, we should potentially see, that's classic neurophysiology, some form of plasticity. And so Wojciech at the time recorded neurons from the hypothalamus. We had a way to visualize them that I don't have time to go into here, either control or after several days of up to 30 days of acclimation. And what he found, this is boiling down a lot of experiments, is essentially these neurons become intrinsic pacemakers. The heat transforms them. They are not silent. under controlled conditions. But if you look at these neurons, they become very tonically active, actually temperature sensitive. They become temperature sensitive neurons. Again, we can quantify this and suggesting that plastically this strong, long-lasting input really changes their excitability. So it's a form of plasticity, and it's unusually slow because it takes several days up to weeks to really fully develop. The key question then, and that's the last data slide I'm going to show, is does this neuronal plasticity, which curiously has a similar time of development of heat tolerance, has anything to do with each other? Is there a causal link that the neurons and their firing changes helps the animal to become more heat tolerant? So, and to test this, we again had the luxury to tap into a rich repertoire of tools. In this case, we used the opposite what I showed before. We used a switch, chemokinetic switch that switches the neurons off. So again, anybody interested in the tools, I'm more than happy to discuss afterwards how they work. Essentially the same neurons, we put this off switch in and ask what would happen now if we expose animals acclimatized, so they are good, becoming good at heat tolerance, but then switching off these neurons. And the result is shown essentially here. So each line is body temperature of an individual mouse, control mice. Now, after heat acclimation, they become very good in this and they can tolerate heat very long. But then if we inhibit the neurons, really it's almost black and white. They fail, and the gained activity of these neurons is important for establishing heat tolerance. So one more slide, we tried to do the opposite, and we asked, okay, is it sufficient if we activate these neurons artificially using what is called optogenetics? So we can dial in a frequency into these neurons over several days, that mice that have never seen heat could become heat tolerant. So in this case, we used frequency, and there was a lot of optimization here, and then tested these mice afterwards in a heat tolerance assay. And when we do this just for a day or two, not much happens. You can see these mice, even though they are now conditioned optogenetically, they fail fairly early. But if we do this for longer times, it seems really that the activity, long-term activity, trickling down likely via the sympathetic, parasympathetic system, changes, and that's some ongoing research now. What does this neural activity really do? Probably cardiovascular function, very likely changing metabolic, energy metabolic aspects like brown fat and so on, switching it off, helping these animals to become more heat tolerant. And with this, yeah, I'd like to discuss with you also maybe during the break, as Sanjay mentioned in his talk just now, is it possible to condition also humans, if one does it in a subtle, very, very controlled way, to become more tolerant to heat? Of course, as we discussed this morning, there will be a ceiling. There will be probably a very hard ceiling and probably not enough to cope with the heat waves we get, but still, could it contribute to something beneficial here? So this is sort of the summary, what I showed you, the people involved, and with this infrared image, I'd like to thank you and happy to take questions.
Great, so we've got time for maybe one question. There's a question there.
Thank you, that was super interesting. I was just curious, so you tested the sensitivity to how long they're exposed to high temperature. How long does that adaptation, do you know how long that adaptation would actually last after?
Yeah, that's a very good question. There's a lot of physiology in humans and mice on this without the neuronal context, but just the physiology. So we find it goes back to, it's sort of like I see that like a trainings program, like really conditioning. So it's about a week you see it dwindle. And actually what's interesting, if we do the neuronal recordings also, they come back down within a week. But what is really interesting is, and that actually athletes who go to competitions use, there is a memory of it. So when we put the mice, so you acclimatize them for 3-4 weeks, bring them back down over a week. But then when you put them back in for just 1 or 2 days, activity is back up. I must admit, I don't know now how long the physiology takes, but there seems to be some sort of memory, if you have been exposed to this type of paradigm, that you can retrieve it quicker.
Great. Okay, I think we better stop there. So thank you for a really excellent talk. Thanks very much. So the fourth talk in this session is a live talk, but online, I think, and it's from Kai Wan from the London School of Hygiene and Tropical Medicine, which is on epidemiological aspects of heat and neurological disease.
So I'll talk about temperature-related dementia in England in terms of the epidemiological evidence on mortality and emergency hospital admissions. So some quick background: dementia is the leading cause of death in England, and the number of people with dementia in England is likely to increase further in the future. People with dementia are exceptionally susceptible to harm from low and high temperatures, and dementia is one of the leading causes of heat-related deaths in England. So previous speakers have already introduced a range of potential mechanisms from behavioral, physiological, societal, and maybe even genetic. Surprisingly, the epi-evidence in England is quite limited. Although we didn't conduct a full systematic review, but a quick search using key terms including dementia, England, temperature, or heat, we only identified 4 relevant epi-evidence. So the first important one is on the current and future burdens of heat-related dementia hospital admissions in England. And then they used ambient daily temperature as the exposure and daily counts of emergency inpatient admissions with a primary diagnosis of dementia as the outcome. So they studied the period more than 2 decades ago. So the right figure is the key finding of their study. So we can see that there is an evident increase in emergency admission when the daily mean temperature is above around 17 degrees Celsius. And once the temperature is above that, there was a 4.5% increase in risk of dementia admission for every 1 degree Celsius increase in temperature. So again, this study used daily counts of emergency admission with a primary diagnosis of dementia. However, something we observed quite interesting is that dementia itself is seldom the primary reason for an emergency admission. So in this figure, it shows the annual admission from dementia as the primary diagnosis, which is the red bar, and with dementia as the secondary diagnosis, which is the blue bar. So we can see that dementia emergency admission, which is the primary reason, they remained relatively constant in the last 2 decades. However, the admission with dementia as the secondary diagnosis almost doubled. And it can also be seen from this percentage of dementia as the primary diagnosis among dementia as the primary and secondary combined, so which decreased from around 10% to 5%. So patients are usually admitted for more acute conditions rather than dementia. We have several speculations on this increase in dementia as the secondary diagnosis. For example, it may be due to improvement in diagnosis. So milder dementia might have been diagnosed more and more. Therefore, the count increases.
And then it can also be due to improvement in recovery from other conditions. Therefore, they are more likely to be readmitted due to those primary conditions, whereas the dementia is an underlying contributory cause. So therefore, we think it's quite important to consider dementia, which is the secondary diagnosis, so that we don't underestimate the risk. And then another existing evidence in England is on annual growth rate of the incidence of dementia. So they studied heatwave episodes using annual incidence of dementia as the outcome. They found no significant association in England. So these two studies are for morbidity. And then for mortality, before this conference, we didn't identify published evidence. And then I just saw Dann's slide, which shows a mortality and heat relationship. So what we found from existing evidence, one important one is by the ONS and UKHSA. They publish excess mortality during heat waves annually. And they compared the number of deaths that occurred before, during, and after heat periods, as opposed to the 5-year average. So in this report, they didn't exclude COVID deaths. And they found that dementia and Alzheimer's diseases are the leading cause of excess deaths in England and Wales during the 2022 heat periods. And then a following report, they used a very similar method, but they excluded COVID deaths in this method, and they identified dementia and Alzheimer's diseases as important cause of excess death during heat periods in 2024 again. So these are the existing evidence we identified, and there are some key research gaps. One is that there is a lack of England-specific time series study that model continuous exposure-response relationships of daily temperature and dementia-specific mortality. And the existing evidence by the ONS and UKHSA are for excess death during heat waves only. And secondly, for morbidity, there is a need for analysis using contemporary data sets, as the previous evidence used data from more than 2 decades ago. And then there is also a lack of studies that jointly and consistently assess temperature-related risks from both mortality and admissions within the same people and analytical framework. And then lastly, there is a need for greater clarity and consideration on the lagged effects of temperature on dementia-related health outcomes. So based on these research gaps, it leads to our study. So the aim of our study is to investigate the association between daily temperature and mortality and emergency hospital admission related to dementia and Alzheimer's diseases in England. We used population-weighted daily mean temperature as the outcome, as the exposure. As for the outcome, we used daily mortality with dementia or Alzheimer's diseases as the underlying cause of death. And then as for daily emergency hospital admission, we used those with dementia or Alzheimer's diseases as the primary or secondary diagnosis. And then in the current study, we used all ages combined due to data limitation, but we will consider subgroups in future studies. And then the period we considered is 2007 to 2019. I will not go into details of the method, but just to quickly mention that for confounders, slowly changing time-varying confounders. So for example, those changes in underlying dementia prevalence, socioeconomic changes were controlled intrinsically by adjusting for long-term trends and seasonal variation of the outcome. And then we considered cumulative risk of temperature, and we considered maximum lags of 7, 3, or 14 days. So just firstly, we can have a quick look of the raw time series data. Firstly, so this is a time series in London for 2019. The blue line is for emergency hospital admission due to dementia, and then the black line is mortality, and the gray bars are daily mean temperature. So in 2019, there were 3 heatwave periods, and then there was a record-breaking heatwave at that time. And we can see that there was a spike in hospital admission at that record-breaking heatwave. And then something interesting is there was an exceptional warmth in winter in February 2019. And then we can see that there was a spike in mortality. So I think this is quite important as global warming, and then there can be even warm or heat events outside summer months. So of course we can't draw any conclusion from this those single events and the raw time series. That's why we conducted that time series analysis using distributed lag nonlinear models. So this is the main results from that model. So on the left-hand side is the result for hospital admission, and then the right-hand side is for mortality. And then we can see a typical U-shaped curve for the temperature and health outcome association. So if we look at hospital admission firstly, we can see that for heat, the effect is quite acute. So when the daily mean temperature is above around 16 degrees Celsius, there is an increase in admission risk within the 3 days of heat exposure. And however, the risk decreased, the cumulative risk decreased a little bit when we consider a lag of 2 weeks. However, for cold, the risk is more delayed and sustained. So if we look at the acute effect within 3 days, there was a minimal cold risk. However, the cold risk sustained and accumulated more as we consider a lag of 14 days. And the y-axis values are different for hospital admission and mortality, but mortality has a higher risk for hospital admission. And we can also see this U-shaped curve and more acute effect for heat and more delayed effect for cold. And we also explored regional variations. We didn't see any particular pattern. So I will just skip this slide for now. And then this is a summary for the heat effect at the 99th percentile temperature, and then cold effect for the first percentile temperature of annual temperature distribution. And again, we can see that for the 3 maximum lag length, we can see that for heat, the effect is more acute. And then there was around 14% increase in mortality risk due to dementia at the 99th percentile temperature. And then for cold, the effect was higher. The cumulative effect was the highest at a 2 weeks lag, and there was a 20% increase in mortality risk. And then the risk for hospital admission was around half of that for mortality. To summarize, extreme heat is associated with a 14 degrees Celsius increase in dementia-related deaths within 3 days, with effects diminishing to minimal levels by 2 weeks. And the short-term mortality and admission deficit may occur 1 to 2 weeks after extreme heat. As for cold effects, they are less acute but more prolonged, with a 20% cumulative increase in deaths over a 2-week lag. And the increase in temperature-related dementia emergency hospital admission risk is approximately half of that observed for mortality. There are some important public health and policy implications. So firstly, rapid health and care responses are needed during hot weather, as risks rise immediately, even at moderate heat levels. And cold-related impacts are less immediate, but more sustained. So it requires ongoing health and care support. And then as most deaths from dementia occurs in care homes and hospitals, improving thermal environments in these two settings is essential. And then lastly, for future research, we will consider other neurological outcomes and their impacts due to temperature. In addition, we could also study comorbidity by studying particular combinations of primary and secondary diagnosis of admissions. We will also consider subgroups, including age, sex, and socioeconomic status. And something we could consider is the duration of admission, so that it can support better economic assessments. And then we would also like to consider alternative temperature metrics, especially heat or thermal indexes. As Lina presented, humidity can be quite important. However, previous EPI study also show that it might not that important for heat effect in the UK. But it's also important to consider it considering future climate change. So that's my presentation, and yeah, I'm looking forward to any questions or comments.
Great, thank you very much. So we have a question from the front row just here.
Actually, is a comment because this finding are not surprising to us, and actually it aligns with our work. You know, when we do this whole genome gene expressions, the transcriptome of heat stroke patients, as I mentioned in my talk, we have this proteotic stress, which means that a lot of protein that are denaturated, unfolded, aggregated, and it affects actually all the organelles, you know, the endoplasmic reticulum, the mitochondria. We have also mitochondrial dysfunctions with all the OXPHOS for the production of energy is shut down. Now, and then we could see that it all the pathway, like the Parkinson, Huntington, amyloid beta formations, neuroinflammation are activated. So in patients with dementia, Alzheimer's type disease, they have already an altered proteome. So they have abnormal proteostasis. So when you add, you know, the heat stress and the further, you know, proteotic stress, so it is not surprising that they deteriorate. Now, I think in the research gap, and this is a good example that epidemiologists should collaborate with biologists, is look at biomarker. So we do have some explanation that needs to be validated. I'm not saying because we are looking at the blood, we are not taking sample from the brain, right? But with the combination with, I think, the biobank, you can identify biomarker in proteostasis that help you stratify, identify those that are more susceptible than others.
Yeah. So, okay. Thank you for that comment. Okay. There's one question at the very back. You know, on that. Okay. So this lady first. Oh, sorry. This lady was first. Oh, yeah. Then the back. Sorry.
Thank you. Thank you very much for your presentation. So I thought that, as we can imagine, these people are elderly people. They have dementia, Alzheimer's disease. Probably they will be spending much more time at their houses, or flats or homes. So I think, as we know, the duration of exposure to extreme heat or humidity is important. I think their house architecture, design, if they have air condition, if they are using, or how their behavior is for reducing the effects of extreme weather, it should also be important. Do you have any data about this, or what do you think? What's your opinion? Thank you.
Okay, thank you. Did you get that question? Yeah, yeah. I think
that's a very critical question. Thanks for asking that. So one challenge, so it is correct that it's important to consider indoor environments and people's behaviors as well. However, it is a limitation that we don't really have widespread indoor air temperature measurements. However, I'm aware that UCL, they are trying to model some indoor air temperatures so that we could study this indoor impact.
Okay.
Thank you.
So then one final question, then we'll have to stop. Okay, thanks.
I'm a neurologist, and I wonder, is there any studies on...
It's all right, I'll forgive you. No, go ahead, I was just joking.
Yeah. I'm a neurologist, and are there any studies on in-hospital mortality? Because in Britain, there is a big variation in often extraordinarily poorly designed hospitals that then have some heat mitigation plans of a bit of water and fans. But then maybe in countries like in Mecca in Saudi Arabia, they have hospitals with good air conditioning. So is there anything on in-hospital mortality? It wouldn't be popular to study, but I think it might be then an impetus to have the necessary changes in British hospitals, because I think you're going to find extremely increased rates of in-hospital mortality during heat waves.
Yeah, so that's a very good question. As far as I know, for dementia-related mortality, around 50% of them occur in care homes, and then around 20% of them occur in hospitals. So yeah, it would be great if we can study these outcomes separately, whether the location of the mortality is in care homes or hospitals or in their own homes. However, we don't have this data at the moment, and I'm not aware there is existing evidence, but we'll look into that. Thanks.
Okay, great. So thank you for that excellent talk. I think we have to end the questions there, but thank you for your talk. Thanks very much.
Hello. So I'm very pleased to welcome Tracey Maitland from Myaware. Hello, Tracey. Could you tell us a little bit about yourself and Myaware as a charity?
Yeah, so I've worked with the charity for about 10 years now. We look after, we're the only charity in the UK that look after people with the myasthenia condition. So that's all of the myasthenias, so include CMS, LEMS, ocular and generalized myasthenia.
And can you say a little bit about myasthenia and how it affects people?
Yeah, so there are different sorts. There's an inherited genetic myasthenia, which is known as CMS. There's also an acetylcholine receptor antibody myasthenia gravis and/or ocular myasthenia. So there are differing types, but basically it means grave muscle weakness. That's what myasthenia interprets as, and it can present in different ways too, depending on different people and how they're affected. It can affect everybody very, very differently.
And Is it something that people are generally diagnosed with young or any age? I just wondered if maybe you could share some experiences with yourself or other members about how they came to be aware of this condition.
Yeah, of course, and it depends. The stats say that women are mostly diagnosed between their 20s and their 30s, and that was certainly the case for me. I was diagnosed in my early 20s, and most male members are diagnosed in the 50 to 60 category, which is classed as late onset. Having said that, we have lots of female members who have been diagnosed in the 60s, 70s and 80s, and likewise we have men who have been diagnosed in early teens and late teens, and in the congenital setting from birth, so with both sexes. So there is no kind of hard and fast rule. Unfortunately, we don't tend to conform. We like to be a little bit different.
Yeah, sounds quite a diverse set of circumstances.
Yeah.
So we're interested in climate and particularly hot weather and heat waves, and we've been getting quite a lot of those recently and recent summers. Can you tell us how hot weather and heat waves affects people with myasthenia?
Yeah, and again, there's a general rule of thumb, but we also have variants of that as well. So a lot of members will struggle with any of the myasthenias in the heat because it affects the nerve muscle junction, and the heat means that the nerve muscle junction has to work harder. So if you already have issues in that area, to have them then try and work as hard can cause muscle weakness to be sooner, last longer, more intense. Some people thrive in the heat. There, as I say, there's no kind of hard and fast rule. But one thing that most of our members have in common is that warm weather can affect them, but these heat waves and heat spikes can have huge impacts on their symptoms, the medications that they need to have, and how well they are during these months and these times.
I wondered if you had any examples of some of the consequences for people of what happens when a heat wave hits.
Yeah, so some members will have to double, sometimes even triple the amount of medication that they take. We've had people that have been in for routine operations and have had quite well managed myasthenia symptoms, along with the anaesthetic and the hot weather. That can have a huge impact on whether they need intubation and mechanical ventilation after the procedure for a longer period of time, whereas had the operation been in the cooler months, they may not have had the same impact and may have had a shorter recovery time. But we know that the anaesthetics can have an effect on those with myasthenia, but if you then add heat on top of that, it can have a significant impact on people. And we've had members who have had to have rescue remedies and rescue treatments because they have been in an ICU setting, whereas previous procedures they weren't as affected for such long periods of time. So one member in particular had a routine operation. They needed a rescue remedy, and their 2 or 3 day stay in hospital ended up being 3 to 4 weeks. And some of it was obviously due to the anaesthetic and the trauma on the body, but actually a lot of it was also down to the heat, which again wasn't necessarily factored in at the start of the when the procedure was booked.
I see. So, would you say that the heat factor's not that well understood, or is it something people know about as a risk?
I think myasthenia itself is little understood in the medical setting. We find that anaesthetists are quite well versed because obviously bringing people around is a huge part of their job. In fact, it's their only job. And some of our members are diagnosed actually when they are coming round from an operation, because they don't come round as somebody without myasthenia would. And if things take a little bit longer, they tend to look into why this happens. I'm not so sure that the heat side of things is as understood in the medical professional as it is with the patients. And I think as members and patient advocates, we do try and explain that to medical professionals to help them understand a little bit more. And certainly when we're in a clinic setting, we can, when we're describing or we're looking at our score, if you like, we have what they call a quality of life score that neurologists and consultants will do with their patient, depending on how they are. You can look at a quality of life score being quite different in the summer to very different in the winter, and actually nothing at all has changed in how they how they work, stress levels, all of the sorts of things that can impact somebody with myasthenia. But the one thing that is completely different is the weather. And as I say, that can have a huge impact and cause people to not be able to work during the summer months. The increased medication can cause, obviously, then more side effects, causing people, significant issues. So it's more understood amongst the community, but not quite amongst the healthcare professionals at the moment, which is something we're obviously trying to educate them on.
And is cold a factor for some people?
Yeah, absolutely. And as I say, we do not like to conform, as I say, but we do also have some that thrive in the heat. Some people find that their summer holiday is something they long for because it really helps with their muscles, and others then can be, affected in the cold. So it's no one of us are the same. And it can take a little bit of working out, and certainly in the early stages of your diagnosis, when you're trying to understand your symptoms and your conditions and how your medication affects you and how to best manage these things, to then have to consider not just stresses in your life and other things that can make the condition worse, but to have to take into consideration the weather is quite unusual. And actually it doesn't actually necessarily have to be on the day when it's hot. It can have, a couple of days later, it can be all of a sudden your symptoms can reappear, and they can be, fatigable symptoms, swallowing, chewing issues, drooping of the eye, ptosis, speech issues. All of these things can be a factor when it's been warm, even a few days beforehand, and not even necessarily on the day. So it can take a lot of weighing up and kind of noting down and trying to understand your condition.
And is climate change something that you think about at Myaware and your members are thinking about?
Interestingly, it's always been the forefront of my mind because I struggle most in the heat and in warm days. And in fact, I'm sitting in a room with an awful lot of fans and air conditioning units around me to be able to combat the struggles that I have. But even I can, like many can struggle. We can only do as much as we can to kind of try and avoid these things, but it can be inevitable. Interestingly, it is something we started talking about, but I think it came to the forefront of our minds a little bit more once we were in touch, because I think actually as members, when we're representing our members, we have to represent them all, and it's something that affects the majority of people, the weather, whether it be hot or cold. But I think a significant portion of our members have more issues, certainly in the warmer weather that we're aware of. And I actually think it's something we need to prioritise a little bit in our thinking and on our way going forward. And so we're looking into producing some literature that will kind of hopefully help educate medical professionals, but also help educate our members to help them educate their medical professionals as well.
Yeah, that sounds really good. Do you think there'll be any sort of coping strategies you could suggest in that, things that maybe have worked for you and other people you know?
Yeah, absolutely. We have hints and tips on the website already of how people can manage their condition and how other members have given hints and tips of what has worked for them. So that's something we kind of share with our members, and it's available. There's lots of chat on all of our Facebook groups, and people are often offering each other support, which is lovely. I think what we don't have specifically at the moment is material or any evidence to show that people with myasthenia can struggle with fluctuating temperatures and particularly with these heat waves. So that's something that we're looking into as a charity to try and get hopefully some documentation that will hopefully look to doing some research at some point, but certainly some knowledge and some information from the specialist neurologists at the moment will be helpful for other medical professionals to kind of understand it more, and obviously our members as well.
Yeah, certainly. And if people listening to this want to find out more about myasthenia or get in touch with you about this, how can they do that?
So our website is a great font of knowledge. It is www.myaware.org. All the information that people can need on there is on there, and if anybody wants to contact the support team or any of the other research and partnerships manager or any of the different departments, all of the information is on there. And there's a great resource on there from medical professionals, written by medical professionals. So it's nice to have that. If you are in the medical setting, it's nice to have lay terminology and also terminology that the medical professionals understand. So there's a huge amount of information on there, and we're always happy to educate.
That's fantastic. Thank you so much for talking to us today, Tracey.
You're welcome. Thanks for having us.
I'd now like to invite our second speaker, who's Anthony Shepherd. So And Shepard gained his PhD from the University of Exeter and is based in the School of Psychology, Sport and Health Sciences at the University of Portsmouth. He serves as Deputy Director of the Centre for Integrated Health and Wellbeing Research and leads the Clinical Health and Rehabilitation Research Team. An Associate Professor in Clinical Exercise Physiology and focused on improving metabolic and cardiovascular health, physical function and overall quality of life in clinical and at-risk populations. So, over to you.
Thanks very much. Yeah, so thanks very much for the invite. Sanjay asked me to come down and have a chat about what we've been doing in our labs. So we've heard an awful lot of information today about how extreme heat events can be detrimental for people with different clinical conditions, and in particular people with cardiovascular disease, neurological diseases, etc. But there's a dichotomy out there within extreme environments. So when people are exposed to extreme environments for long periods, we get these negative effects. However, there's also some therapeutic benefits that can be seen with acute exposures. And I'm going to talk a little bit today about what we've been doing in our lab around this, and my conflict of interest from industry funders are down here on the bottom. So the two major conditions we work with within our lab is one, type 2 diabetes, and then the older adults. So very brief explaining about why we care. You've heard a little bit about the excess mortalities that we were talking about earlier on, but by 2030, we're going to be talking about almost 650 million people across the globe that have got these conditions, and it's going to tip $1 trillion US. And the main thing we're interested in doing with treating people with type 2 diabetes is to lower blood sugar levels, because all-cause mortality improves, myocardial infarctions, strokes, and importantly, those microvascular endpoints we've been talking about, so things like eyesight, kidney function, etc., are better if we can lower blood sugar. In terms of older adults, as we age, typically, we get this increase in arterial thickness, we get reductions in brain matter, and things like muscle quality. So on the bottom here, we've got a young, physically active male, and then we've got age-matched older adults, one that's sedentary and one that's physically active. So you can see the quality of the muscle is changing. As we age, our ability to improve some of those molecular chaperones that we've been hearing about earlier from the talks get diminished. So we produce heat shock proteins that protect us from the cells and improve things like inflammation and our ability to use insulin. And in general, as we age, physical activity comes down. So by the time we're over 75, only 40% of people are hitting the recommended daily allowance of moving. And by the end of the century, we're going to have something approaching 2.5 billion adults that are over 65 years and older. So it's a group that we really need to start paying more attention to. Now, how do we treat these people? I am an accredited clinical exercise physiologist, and the answer is do more exercise. However, and there's some data on the screen showing that we can take people with type 2 diabetes and we can put them into remission after 8 weeks of doing diet and exercise. The problem we have with these interventions is that the adherence to these programs are pretty terrible. So what we try and do within our lab is look for alternative exercise mimetics, so things that will act like exercise without people actually having to do the exercise. One of those things is to warm people up acutely. So here's some data that some of you would have seen before from Jari Laukkanen's lab in Scandinavia, essentially showing that we've got sauna frequency here, so people that go once a week, the yellow line 2 to 3, and this darker line here 4 to 7 times a week, and we're looking at mortality. So the more frequently you're exposed to heat, and on the right duration, the longer you're in those sessions for, the better your mortality. This is also true of people that are in hot tubs. So if you go more frequently and use these heat exposures, this is in 30 or 1,000 people, your cardiovascular disease, or at least risk of getting it, improves. So there's something here about warming people up where they volitionally go to these experiences, have a perturbation, and then adapt. And part about what we've learned today is that when that chronic exposure is there, you can't cope with that adaptation, but these small environment may be something's going on. So what do we know from the literature? So here's some landmark papers. The one from New England Journal of Medicine from Hooper, who did the first work at exposing people with type 2 diabetes, and they got them to hop into a hot tub for half an hour a day, 6 days a week for 3 weeks. And essentially they showed a 1% improvement in HbA1c. So that's a marker of how much sugar is floating around in their blood. And if we go back to the start, you can see that 1% improvement would be equivalent to about a 14% improvement in all-cause mortality if that was true. Some of Hannah's work, who's going to come up and talk in a minute, is looked at putting people into warm rooms. And essentially, across a few days, you can see that plasma glucose concentrations have improved, and so has fasting insulin concentrations. And here's some work in polycystic ovary syndrome from Brett Eli, who's also showing after a few weeks of this intervention in warm water that people's indices of metabolic functions, their glucose and their insulin, are also improving. In terms of what we know about healthy older adults, there's some of Vienna Brunt's work at the top here, showing that we can improve the way in which the arteries functions. This is endothelial function in the big blood vessels. There's some improvements in muscle function down here. And again, over here. In terms of older adults, the evidence is a little bit more sparse about immersing people into these environments, but there is some work looking at cognitive function, suggesting that maybe there is improvements in the way in which the brain functions, and also down here in the bottom left, some young and older adult comparisons also showing improvements in the way in which the vessels function. Okay, so that's a bit of a brief explaining about what we knew. And the next few slides will be what we've been doing within our lab. Some of this was led by one of my postdocs, Dr. Tom James, and Dan Piccolo, who's soon to be a doctor. He arrives in a few weeks. This is some of our experimental setups. So within Portsmouth, we've got 3 labs. This one over here, a climate-controlled chamber, which can be hot and dry. So you can be in the desert or the rainforest. You can be up a mountain, whatever altitude you like. And we've also got the plunge tank in there, which goes cold and hot. We have 3 of these chambers, another one that's cold and hypoxic, and a third one which has a flume, much larger. It's got like a swimming pool inside it where you can swim against. So essentially, you can swim at the top of Everest in the labs. So we're very well set up to run these experiments. In terms of the stuff you're going to see and some of the mechanisms that we're talking about, or at least techniques, again, we're looking at how the endothelium of the arteries work here with ultrasound. We've got a technique called iontophoresis over here, where we are looking at infusing different drugs to look at how the small blood vessels dilate. We've got a battery of cognitive tests. We're also looking using NIRS, looking at indices of cerebral blood flow and release oxygenation. Over here, we've got muscle function and grip. We've got some markers of cardiac function, blood pressure, as you can see. Lots of different techniques to try and answer these questions. So for this slide, what I want you to do is focus on the closed black circles. So these are the active condition where we've immersed people with type 2 diabetes into 40 degrees C water. What we're trying to do in these temperatures is to clamp people's core temperature at 38.5 degrees C. There's some evidence to suggest that we release more heat shock proteins there. And the comparison to these black circles are the open white circles. You can just ignore the grey ones for now. It all muddied the conversation. And on the left here, we've got blood glucose control. So unlike the Hooper paper that we showed earlier on, from a single immersion, we're not showing that blood sugar levels a change with passive heating. But we are seeing that there are reductions in systolic blood pressure. Unsurprisingly, when you warm people up, blood vessels dilate and blood pressure comes down. Across the next few slides are our QR codes for people who want pictures or access to the papers that are there. However, we do see some exercise mimetic effects from a single acute bout. What you can see up on the left here is that we get an increase in heart rate that shoots up rapidly and stays fairly high for up to an hour after they get out of the hot tub. And on the right here, you can actually see that we're causing a statistical increase in energy expenditure. So our people are burning more calories and heart rate is driving up while they are in the hot tub. So given that we saw no effect on blood sugar control with a single immersion, what would happen if we immerse people multiple times? So for this study, we immersed people 10 times for an hour a day across a 2-week period. And you can see here that we saw, again, no change in glucose, but we did see marked reductions in fasting plasma insulin, so the main hormone that's going to put the sugar into our cells, and we also showed improvements in insulin sensitivity. So one other note here is like we reduced resting metabolic rates, so the metabolic demand of the people has reduced slightly, and it's also true of resting VO2, which is indicative of people getting fitter, but we probably need to follow that up with some exercise testing. We also showed some reductions in resting cardiac function, so cardiac output here. No changes in endothelial function, but we did see reductions in blood pressure in these people. So now onto some work in the older adults. So this is some work that was published just a couple of weeks ago. What we did is we measured cognitive function, and they had NIRS on throughout all of this, looking at brain tissue saturation. At baseline, we then immersed them in the hot tub for an hour. We measured these markers again immediately after they got out of the water, and then 3 hours again later on. Followed a 6 weeks heat intervention where they go to the tubs 3 times a week, and then we followed it up again at the end at the same time points. There's a lot of data on the screen here, but I think the headlines to suggest here, this is a time effect. So heating after they immediately got out of the tub was their throughput, so their memory was actually improved across time with heating, and then that came back to baseline 3 hours later. And there was a condition effect over here which suggests that memory and also logic at the bottom right-hand corner was improved after the 6 weeks of heating. So maybe there's a cognitive improvement that's happening here. One of the reasons what may be happening, this is probably the interesting slide, is we get this reduction in deoxyhemoglobin on the right. So maybe it's driven by oxygen extraction. Part of this wider study was a larger crossover design trial where we were also looking at muscle and cognitive function. The story is much less interesting for the muscle and cognitive, unlike the diabetes work. There's some small changes in knee extensor power and a grip strength that's going the wrong way, but largely it was a set of null findings for muscle function in older adults following the 6 weeks. And there's a similar story for the cardiovascular function, unlike the diabetes, and there was actually a change in the control group in this study. What we're currently doing, just doing a lot of the wet lab work now, is trying to look at some of those changes in heat shock proteins and mapping them across time, trying to have a look at what happens to different types of chaperones. There are different ones throughout the body who does different things, and trying to see how those interplay inside the cell and outside of the cells. And the reason why we're really interested in this sort of stuff is because there's more and more evidence coming out, at least with cross-sectional correlational work, looking at the effects of heat shock proteins and how they can protect people before they go into surgery. So when we know when these heat shock proteins will peak and at what times these happen, we might be able to design interventions where we can use heat therapeutically before people have surgery. And we're also trying to use some of these heating environments to see if we can prepare older adults for when we know heat waves are coming. Can we use them to try and adapt people before they come? And some work which has just been signed while we've been in the contract, and here, funded by Jacuzzis, we're trying to look at dialysis with people that have chronic fluid overload, where they can't go to the toilet anymore. Fluid overload backs up to the heart, the pressure builds up in the heart, and they end up with cardiac complications. So very simply, can we use hot tubs, saunas, etc., to try and get people to sweat out some of that water and reduce the strain that people are seeing in their hearts? So in conclusion, I think we're at the stage where we probably need to do some efficacy trials on people with diabetes, looking at acute exposure and can we improve cardiovascular function and metabolic function. And in older adults, at least healthy older adults, which ours were, doesn't look like we're having massive effects on muscle or cardiovascular function, but maybe there is some beneficial effects on cognition. Thanks very much.
Thank you very much, Ant. It was excellent, very interesting work. Any questions for Ant?
Thank you so much. Very interesting. I agree completely from a physiological perspective, but I was wondering about the decrease in mortality specifically. How did you take into account socioeconomic status? Because I suppose that being able to go to the sauna or take a jacuzzi bath 7 times a week could be a good indication of a higher income bracket of some sort.
No, I completely agree. Social economic status in these studies is a massive co-founder. They try and correct for it, but with all for these longitudinal studies, how well can you do it? So again, I think it's the large RCTs that are going to answer those questions. For those that have the money, I think the answer is go to the sauna often, even if we're wrong. But for now, I don't think we can answer the questions. We do need much more randomized control trials. But there are lots of small experimental studies like the ones I've been showing you today, which are showing mechanistic effects. And maybe there's something in there, but I definitely don't think we can say they're causal yet. Yeah, I think that.
Thank you.
Thank you very much. I think there might be one more question there. Just
Hi, Anne. Thanks for a super interesting talk. I was just curious, particularly in the context of what we've had this morning around kind of individual differences, genomically, etc. It looks like in some of the data that, you know, there's a lot of people seeing the trend that you described, but then there's a few people where the opposite effect is true, which I'm sure is always the case in, you know, these kind of experiments. But I was curious whether in your data or in others, whether you think there is any kind of individual effects where there might be subgroups of people for whom, you know, this is more of a harm than a help, or whether there's any kind of individual difference effects you've sort of seen yet.
It's a really hard question to answer. Yeah, I don't think we know the answer. A lot of people do talk about responders, non-responders, and all sorts of fields that we look at, but I don't think we quite know the answer. For mild exposures where we're not cooking people too hard, sorry for the term, I think what we're going to get is a bit of physiological stress. So they'll adapt, and I think that's true of much of what we do. For a long time through our history as human beings, we've been out in the cold, getting hot, climbing mountains, getting hypoxic, and I think we've lost as society a bit of that exposure to these extremes that are out there. So I think we're trying to bring a bit of that back. Are there responders and non-responders? Probably. Have we got a clue in reality about what that is and how that affects people? I don't think so, to be honest.
Thank you very much. I don't think we have time for any more questions. Apologies, but people will chat you during the coffee break. Thank you very much again. I'd now like to invite Hannah Pallubinsky. Dr. Hannah Pallubinsky is Assistant Professor and Leader of the Thermophysiology and Metabolism Research Group, ThermU, I hope I'm pronouncing it as supposed to be, at Maastricht University. Her work explores how environmental parameters such as temperature, humidity, and air quality affect human physiology and metabolism, bridging laboratory-based climate change research with real-world field studies. Hannah's team investigates how climate change and extreme weather events impact health and well-being of people, with a particular focus on protecting vulnerable populations and strengthening thermal resilience. ThermU also explores the therapeutic potential of heat and cold exposure to improve cardiometabolic health, so a good link with the previous presentation there. Dr. Pallubinsky contributes to large international consortia on heat adaptation, built environment interventions, and wearable sensor applications, and collaborates with public health and engineering partners to translate findings into actionable prevention strategies.
Thank you very much. Thank you for the invitation to talk here today. I met Sanjay last year, and we had on a committee where we were together, we had some discussions about wearables, measuring heat strain, heat stress, and also the environment. So I think this is why I am invited to talk about this today. But full disclosure, I am not a wearable device expert. This is also not a comprehensive market overview or anything like this. This is really to tell you from my experience as a researcher in thermophysiology, the type of devices that we are using and how we're using this in the context of heat acclimation research that I'm involved with. So I hope I'm not disappointing you already now, but still I hope maybe there will be some interesting takeaways. So to really also wrap this presentation in the research that I am doing at the moment, I would like to start with this, showing like some kind of media communication tools that are shown when a heat wave hits. And on the left-hand side, we see the Dutch version, on the right, something similar for the UK, where usually like acute measures are promoted for people to keep themselves safe from the heat. For example, keep yourself cool, drink enough, wear light clothing, etc., etc., and maybe also for the indoor environment to close blinds and curtains and so forth. But I hope that I will at least convince you a little bit today that maybe we can do more, and we can actually do something before the heat wave hits for our individual health. And I think heat acclimation has been mentioned already a few times today, may be an important puzzle piece in a toolbox that we can use to prepare people better for heat events. So I hope at the end of this presentation you will be convinced. So when we look at the literature for heat acclimation in humans, so we've already seen quite some interesting stuff also on mice today. But what we see is usually that the protocols are really directed at improving performance in the heat. So for example, for military or for preparing for the Olympic Games, etc. And those protocols are quite extreme. So for example, you have people exercising in heat, 35 to 45 degrees Celsius for 1 to 2 hours daily over a period of a week or more. And this is then controlled by controlling either the work rate or controlling core temperature to induce heat adaptation. And what we see is that it works. So these protocols can induce really positive effects for performance in the heat. So looking at this simple graph here, this is just one individual, and on the y-axis we have heart rate, and on the x-axis time of exercising or time to exhaustion. You can see that before heat acclimation, the curve ends quite quickly and goes up quite steeply. So heart rate increases and the individual is exhausted and has to stop. And after acclimation, the line continues for much longer and is less steep. So heart rate stays lower, and also the person is able to exercise for longer. And this is a really nice overview figure from our colleague Peria, who has looked at a lot of different heat acclimation protocols and looked at these variables and how they evolve over time. So on the y-axis is the percentage of adaptation, and on the x-axis we have days of heat acclimation. And in red here, again, you see heart rate quite steeply decreases already within a week of getting used to exercising in the heat. And this also, of course, goes hand in hand with an improved fluid balance, plasma volume. We also see that the light green line, the exercise capacity increases. But also, interestingly, we see that core temperature goes down, which is kind of a response to probably create some kind of thermoregulatory buffer that prevents from overheating. However, looking at these protocols, I think you also agree with me that we are all probably not going to do that to prepare ourselves for the heat. Especially vulnerable populations are probably not able to do something like that. So what we in Maastricht have been trying to figure out for some years now is how can we use this approach, heat acclimation, but really translate it to make it suitable for a broad population and also specifically for vulnerable groups. And when I talk about vulnerable groups in our studies so far, we've mostly looked at people of older age and with overweight, and also some pre-diabetic groups. But yeah, this is unfortunately not yet neurology pathologies included in here. And as has just been mentioned by Ant, I've done a couple of studies on passive heat acclimation. So where, as opposed to these active protocols with exercising in the heat, we've just let people sit in a warm room, and we also saw adaptation there. But now today I really want to talk about this hybrid and passive and active heat acclimation that we specifically designed to try to kind of mimic realistic real-life scenarios. So my brilliant PhD student, Sophia Papa, has come up with this protocol, or we've come up with this together. And what we wanted to do is to mimic the weather forecast a little bit. So at least for, let's say, Middle Europe or Northern Europe, what we sometimes see is that temperatures before a heat wave are climbing steadily, or like, let's say, in steps, before then actually the real heat wave hits. So we were wondering, is it possible to really make use of this slowly increasing temperature outdoors and help people to use that time to already get used to heat a little bit before then the heat wave hits and they have to go into protection mode to really prevent heat-related health issues. So what we've tried here is a 7-day heat acclimation protocol where we expose people to step increases of temperature. So the first couple of days were 29, then 32 degrees Celsius, and then 35 degrees Celsius towards the end. And before and after, we did some tests. For example, we did also metabolic testing. I'm not going to talk about that today because of time, but specifically we looked at their physiology, thermophysiology in the heat. And I should also say this was not just passive. We also did some light cycling because Dutch people like to cycle. So we thought, let's do something practical that they will have to do anyways, because if you still are active and you want to go out to do your grocery shopping, etc., some light physical activity is probably going to be part of your everyday exposure. So then our heat stress test before and after heat acclimation looks a bit like this. We expose people in a resting late on a stretcher state. You will see that in a moment. First to a thermoneutral temperature, and then we ramp up heat to around 45 degrees Celsius. There are also other protocols in the literature. For example, Ollie uses specifically also humidity ramps, and we've kept humidity as stable as possible in this situation. Okay, so I'm going to talk about a few wearables now, but also here again, a disclaimer, I'm not sponsored, unfortunately, by any of these companies, so I had to purchase them all myself. But yeah, this is from an older study, a subject or participant in our chamber, in our metabolic chamber and also climate chamber. I will show that room a little bit later. And of course, you can see we're doing a lot of different measurements, trying to capture everything that's happening. And yeah, let's dive into one of the most interesting ones. I think also here is core temperature. We are not using rectal or esophageal core temperature because for us it's not that practical. We also try to do some stuff in the field sometimes. So this intestinal pill that we can use, that people actually swallow, and then we can measure the temperature in their intestines, is quite useful here. And we can do that with this kind of like lab grade device, which, you just put the device next to the person and then we can trace their core temperature. But nowadays there are also these watches that also can be used in the field to easily capture the signal of the pill. And then what core temperature somebody has during the day. We also measure skin temperatures. We always use the 14 ISO-defined site model, which gives us a nice overview of various temperatures across the body. We use eye buttons. I think everybody who is in the field of thermophysiology is not surprised by that, because this is really used a lot. It's a small battery shape device that you can just easily stick on the body in all locations where you want it, but this is the 14 ISO-defined sites. And so we get a nice overview of the skin temperature. Of course, we also measure heart rate and heart rate variability. This is also no rocket science. We just use a normal chest belt, like for example Polar, but there are also other good belts for that. And we also look at blood pressure. Again, no rocket science. We like to use ambulatory systems so that we don't always have to press the buttons, but that they just keep running and we can just let people rest during the study. We also do skin blood flow measurements with laser Doppler technology. I don't think that there's anything like that can be used as a wearable yet, but correct me if I'm wrong. I think a good approximation is still skin temperature, because of course where there's more blood flow, there's probably higher skin temperature. So that could be translated like that. We measure local sweat rates, can be done at various skin sites. We usually do it either on the forearm or on the leg, and maybe to kind of translate that into a wearable that could be used in the field. There are these devices that can measure electrodermal activity, skin conductance. So yeah, that kind of approximates that maybe as well. And we are very lucky in Maastricht. We have these beautiful climate and respiration chambers. So climate, because we can adjust the temperature over a wide range, and we have 5 of those. So we can also do multiple conditions next to each other. But also these are room calorimeters. So we can measure with indirect calorimetry oxygen consumption and CO2 production. And so we can know what people, the energy people are actually using at a certain point in time. And also what they are using. So if they are burning more glucose or more fat at a moment. If some of you have maybe used indirect calorimetry, maybe you're more used to these kind of like, it looks like a space hoods that we can put over people to do the exact same measurements. So they, you just measure oxygen consumption and CO2 production for energy metabolism. But there's also devices like this that try to reproduce the same measurements in the field. So also there it can also be turned into a wearable device for certain settings. Okay, so far, and of course there's much more, but I had to limit myself somewhere. Also very important is to assess the environmental exposure properly. And there these beautiful, we call them kind of measurement trees exist, looking at all these different environmental parameters like the black bulb radiation, air speed, and of course temperature, humidity, and also air quality. And sometimes we kind of use this to characterize a condition, but oftentimes there's no space in the room to keep it there. So sometimes it's just a characterization, and then we move to somewhat simpler methods again to measure close to the participant, but also in like a practical way. And here we can also use a different type of eye button, which is a hygrochron that measures temperature and humidity. And we have this, so in the back here's a rendering of our climate chambers, and we just simply hang them on a strap, on a string, sorry, at these 4 different heights, and these are ISO-defined heights for measuring of indoor environmental temperature. So we're trying to reproduce it this way. And also for, again, like to kind of take this a little bit into a field setting, we've used previously simple hygrochrons stuck to name tags so that people can put them on the outer layer of their clothing. And so we can also assess their microclimate around them. There are also commercial devices that maybe do that better or not, I don't know. And also when we measure at people's homes, we can also have these stationary devices that are, for example, in the bedroom or in the living room, and assess the thermal environment at people's homes. Now, I also still want to come back to the heat acclimation study, that the hybrid study that I introduced in the beginning. And I want to show you what happens there compared to these like really extreme active heat acclimation protocols. I'm sorry, my figures came out a little bit blurry, but what we can see here after 7 days of this like step heat acclimation, we do see that the black dots are lower the post measurement of core temperature during this heat stress test than the open dots. So we see that core temperature has decreased. We also see quite an impressive decrease of mean arterial pressure, and already here at baseline. So people come in and they are still like the first hour in a thermoneutral temperature. And already here we see that mean arterial pressure has decreased quite dramatically. And this is actually my favorite figure. I hope it's understandable, but this is during the intervention. So this is during 6 hours of heat acclimation. And here we have in red day 1 versus day 7, which was a 6 degrees Celsius difference. And here you can see that these lines are more or less on top of each other, or sometimes the day 7 is even lower, which means that during the resting, the cycling, and also recovering, the heart rate was always lower on average after this acclimation protocol, despite the 6 degrees Celsius higher environmental temperature. So that's quite interesting and impressive, I think. Now, I do hope that you agree with me that this may be a very powerful tool. And of course, we need to see how this is translatable to other populations. But I also just wanted to point out that this little figure here, plan ahead to avoid the heat, might not always be really the best advice to give to people. Of course, when it gets very extreme, yes, avoid the heat. But beforehand, the weeks before you go into a heat wave, it might be better to not necessarily avoid the heat, but to limit air conditioning use and get acclimatized, because that might be actually very helpful. Now, to wrap also up about the wearables, I think they are very important and very essential, mostly for this last point, to really take the data that we measure in our lab and check if we can actually reproduce that in like a realistic real-life setting. So this is, for me, one of the most important next steps that I hope to be able to do, to try to bring this concept of heat acclimation to the field and see how people are able to deal with it. If you choose a wearable, make sure that you can access the raw data, just also as an important point. And that's from my side. Thank you very much.
Thank you very much. We might have time for one very quick question. Sorry for being late. Please wait for the mic, and just to remind you to please speak close to the mic. So, thank you.
Thank you. Thank you for this nice presentation. So the wearable systems look like very impressive, I think, but I wonder if they could cause an extra stress for the people. If you look at the structure and the parts of these systems, what do you think about, or do you have any acclimation maybe period or application on those wearable systems before the experiments regarding temperature and the other? Thank you.
Yeah. They may look very impressive, but actually most people realize they don't feel anything. Like if you have you ingest the core temperature pill, you will not feel it. It will come out in its natural course, and you're never going to look back. So that's just there. And the skin temperature sensors, of course, they are on your skin, but you will also realize people forget about them. So we've regularly people that walk out with the forehead button still attached, because we are so used to seeing it, they don't feel it, so they just walk away with a skin temperature on their forehead. And I think in the field, it's very important to kind of make this trade-off between finding something that captures the parameters that you want to measure accurately, hopefully, and in a valid way, but also not create a too high burden. So oftentimes we turn to smartwatches there, and I haven't really talked about that today, but because they can measure heart rate, etc. Then, of course, you can question, do you want to use the optical sensor that a lot of these smartwatches have, or do you again want to maybe use a belt, depending on the setup. But yeah, of course, it's a bit of a trade-off. Yeah.
Okay, thank you.
Thank you, Hannah. We might have time for one more question. You want? The gentleman at the very, very back. Please wait for the mic. For the online
I can
audience.
repeat the question through my mic as well.
Are you going to do similar work for the cold? I remember that people did experiments with people going to Antarctica, where they did these trials up to 6 weeks in refrigerated environments before. But in the Netherlands or in our climates, are you going to do the similar work for cold?
Yes, so actually in my research group, when I started my PhD, I was the first one doing work on heat, and everybody before me was doing work on cold. Maybe some of you know the name Wouter van Marken-Lichtenbelt, who is my PhD supervisor, back in the days, and he's done a lot of work on cold acclimation and also brown adipose tissue stuff. And yeah, you also see that we are also able to adapt to cold in different ways. So those adaptations that you see are slightly differently. But he's also done some interesting work in Siberia in like really extreme cold. So if you want, we can exchange on that later. I cannot give another presentation on the cold stuff now.
One more presentation. Thank you so much, Hannah. That's great. And sorry. And I'll now invite our last speaker for this session, Valeria Iodice. Dr. Valeria Iodice is consultant in neurology and autonomic medicine and associate professor in neurology at UCL. Dr. Iodice has been the clinical and academic lead of the autonomic unit at the National Hospital for Neurology and Neurosurgery, Queen Square, since 2013. She has long-standing clinical and research interests in autonomic neurology, gaining 3 worldwide autonomic centers: Mayo Clinic, Rochester, USA, Imperial College London, and the National Hospital for Neurology and Neurosurgery in London. Dr. Iodice qualified at University Federico II Medical College in Naples, Italy, in 2003, and completed the residency in neurology and neurophysiology at the University Federico II again in 2008. She was awarded a clinical research fellowship in autonomic medicine at Mayo Clinic, Rochester, Minnesota, in 2007, where she began her research on the autonomic nervous system. And in 2009, she was awarded the first Sir Roger Bannister Fellowship in Autonomic Disorders, and was awarded with a PhD in Neuroscience and Autonomic Neurology from Imperial College. Over to you.
Thank you. Thank you. Can you hear me okay? Good afternoon, and I'm really delighted. So thank you to the organizers, to Sanjay, for the invitation, and thank you for the nice introduction. So you can imagine, originally from Italy, went to Minnesota and then back to UK. I had to do a lot of acclimatation actually in terms of thermoregulation. So in the next 15 minutes, I will try to give an overview of thermoregulation and how thermoregulatory dysfunction presents clinically, why this matters for neurological disorder, and why it has implication for cardiovascular autonomic stability. And we have heard quite a lot today on this topic, and how we investigate pseudomotor dysfunction in clinical autonomic practice. So thermodysregulation is one of the functions of the autonomic nervous system, but rarely a patient then present with a thermodysregulation will not have an impairment of other domain. So we need to be mindful of that. So they might present with problem in blood pressure and heart rate regulation, bladder, bowel, GI, and sexual dysfunction. And I will discuss how that does have an implication in terms of diagnosis and treatment. So in terms of physiology, I will not go in details because you have heard quite a lot today, but the central thermoregulation integrates a very complex response between autonomic, endocrine, and behavioral response. And we have to be able to react to increase or reduction in our core temperature. And I will focus primarily on the sympathetic cholinergic system. So if our core temperature does increase, so the temperature around the vital organs, we are able to activate vasodilation and sweating output, and this is how we cool down. And the opposite does happen with if the core temperature does decrease, with vasoconstriction and shivering. In terms of pathway, as you can see, the neuroaxis for thermoregulation is a complex one. So involve a very peripheral structure with afferent fiber and from the hypothalamus all the way down the spinal cord and the very postganglionic pseudomotor fiber. So the lesion really can arise from several different structure of the autonomic nervous system, and hence you can imagine then the disorder then they present with thermodysregulation are very heterogeneous. So this is by no means a list then actually summarize all the neurological conditions and they present with thermoregulation, thermodysregulation, but just few examples. So we might have disorder, then they do primarily impact the hypothalamus function, disorder at the brain stem, like a neurodegenerative pathology, like Parkinson's disease and multiple system atrophy or dementia with the Lewy body, and to all disorder, then they impact spinal cord or the ganglia. So many autoimmune autonomic condition, they do have a lesion at the ganglia level or in the very periphery. So all the neuropathy then you can imagine. So we have had quite a few examples regarding diabetes. So we see many patients with autonomic diabetic neuropathy, but also hereditary neuropathy or other cause of neuropathy. And how the patient they present to us. So they can present with either hypofunction. So what you see on the left side of the slide, which we call the hypohidrosis or anhidrosis. And the red then you see here, so it's not blood, we are not that bad, but it's a powder then we use, then it changes color when the patient starts sweating, and we will see a few examples later on. Or they might present with hyperactivity, so increased sweating, hyperhidrosis. And the complexity is then in the same patient, the two disorders, they might overlap, and we will see one example. So there is still, among the clinicians, there is still a misconception. So pseudomotor dysfunction in reality is not just a sweating problem. There are, as we have seen today, there are significant impact on risk, on cardiovascular stability and other mortality. Because when there is a pseudomotor dysfunction, there is an impaired heat dissipation, there is an active vasodilation, there is a reduced venous return. And you can imagine if we have a patient that already does have a vulnerability of the autonomic nervous system, and you see an example on the very right side of the slide. So this is a patient with a neurogenic orthostatic hypotension. So this is a tilt on an LT control on the upper panel, and this is a tilt in a patient with autonomic failure. When the patient is upright, there is a significant drop in blood pressure without any compensatory tachycardia. So if this patient is exposed to the heat and there is a thermodysregulation, at the end of results, unfortunately, is a worsening of this drop in blood pressure, which for our patient means syncope, exercise intolerance, fatigue, and heat intolerance. So this is a paper, so please, if you could not take picture because it's under review, but this is just to show the impact of the heat in functioning, in daily functioning. So these are patients with, what you see here, these are patients with alpha-synucleinopathy, so with a neurodegenerative disorder, then they might have a thermodysregulation. And we are exposing this patient to supine exercise. So normal physiology, you would expect an increase in blood pressure and heart rate. This is what we call the riser. But if there is a baroreflex dysfunction, these patients, they have a significant drop in blood pressure. So there are two potential triggers: the heat stress, which obviously does happen during exercise, and the baroreflex dysfunction resulting in a drop in blood pressure without not much of increase in heart rate. And you can imagine in this scenario how patients they might respond with the climate change. So in terms of approach, so Sanjay did ask me to give also an overview of how we do approach diagnostically, how we can test the thermoregulation. And I find it helpful to have a simple clinical framework when we think about what is the value of testing pseudomotor dysfunction. It's about detection, so be able to answer the question, is there a pseudomotor dysfunction? It's about quantify, can we quantify the degree of thermodysregulation? It's about localizing the lesion, so where the problem is, helping a clinical diagnosis and hopefully help also with the treatment. So when we think about the diagnostic, we need to have a diagnostic that is able to map in a way and evaluate the entire pathway from pre-ganglionic to post-ganglionic testing. And this is why we combine a different methodology. So on the left side, and again, this is there are a few examples, but there are other methodology, then they use exactly the same rationale. But you see few tests, either the QSART, which was established at Mayo Clinic in Minnesota. We use the dynamic sweat test, and there is the QDIRT. And these are post-ganglionic testing. So they are evaluating the very distal part of the sympathetic cholinergic system. And then we have what we call the thermoregulator sweat test in a chamber, which gives us an entire global assessment. So expose the individual to the temperature and we measure the output. So what we measure, so if we need to measure post-ganglionic, so in this cartoon is a very simplified explanation on how we assess sweating at the post-ganglionic. So basically we use a iontophoresis machine, use acetylcholine or pilocarpine, which will stimulate a sweat gland, but antidromically will also navigate and stimulate other sweat glands. We are not interested in this output because that does not differentiate whether it's the nerve that is activating the sweat gland or just the acetylcholine then is activating the effector. But we are interested in measuring the sweating output here, which we know then is neuro-generated. And you see an example, this is dynamic sweat test. So we stimulate with acetylcholine or pilocarpine. What you see on the very left side of the slide is an LT control. Each of these dots is one sweat gland activated, and we can measure the output per sweat gland, the overall output, and the density of the sweat, how many sweat glands the patient individual is able to activate. And this is quite important because in early stage of the disease, individuals they are able to compensate. So if you're only measuring the overall output, you won't be able to capture abnormalities. Then we combine, this is our facility, our thermoregulator sweat test or chamber, and we use a 16-channel to measure skin temperature, and our protocol is the one that is mostly used also by other labs. So the temperature is maintained between 48 and 50 with a humidity of 35, 38. And we need to make sure that there is an increase of 1 degree of core temperature, otherwise impossible to analyze the sweating output. We use a powder and a change color, and you see few output here. So in an healthy individual, this is what we will be able to measure. So there is, you can see a very uniform sweating. The powder, when we use the powder, is a light pink, then it turns red when the individual starts sweating. And we can map, so here you can see a distal pattern. So this is a patient with a peripheral neuropathy. Here there is a regional. This was a patient with neurodegenerative pathology. This is a patient with harlequin, so with a very unilateral impairment of thermodysregulation. And this is a patient with a pure autonomic failure. So another neurodegenerative condition then is part of the alpha-synucleinopathy. So what we have seen, two methodology, so one for distal, one for global assessment, and we combine the two because we want to answer also the question, can we localize the lesion? So you can combine the two tests, so you can stimulate the very distal part or you can perform a thermoregulator sweat test. And this is an example of how combining the test does help. So this is a patient where on the thermoregulator sweat test, there is a very profound anhidrosis, but when we stimulate the distal part, the patient is very much able to sweat. So it means that the problem is above the postganglionic. This patient in particular was a patient with a multiple system atrophy. And this is the opposite scenario where actually the distal part, the sweating is very much reduced when we do dynamic sweat test, and the environmental chamber, the patient is able to sweat. So you can see why we combine two methodology to answer quite a few questions. Now I'll give you a few examples clinically of the impact of thermal dysregulation, also who are the patients, what are the indications for testing the pseudomotor function. So the thermo dysregulation is very frequent in all cause of peripheral neuropathy. You see a few examples here. So obviously diabetes, amyloidosis, systemic or hereditary, rare hereditary neuropathy, infection disease, and toxic. And this was a patient that was referred to us with a specific question. This patient is troubled by the increase in sweat, in hyperhidrosis. Please, can you treat? Yeah. So in this example, for example, so this individual was sweating a lot from the upper body, as you can see, but this is a compensatory mechanism because the patient does have a neuropathy and is not able to sweat from the lower limbs. So obviously, quite dangerous in a way to treat without an assessment because we could have made actually symptoms much worse. This is a study done with the Peripheral Neuropathy Unit at UCL and also the National Amyloidosis Center at the Royal Free. So pseudomotor dysfunction, I don't know why it's very blurred image. Pseudomotor dysfunction are very common in patients with the TTR amyloidosis, and now is a very is an important time for this patient group because finally we have a modifying treatment, then we can stop the natural history of the disease. And pseudomotor dysfunction, as you can see, they can start in the early stage and they progress over time. So important to capture, important to diagnose. And then we did look whether having a pseudomotor dysfunction and an autonomic failure affects actually survival. And it does affect survival. So patients, then they start with pseudomotor and cardiovascular impairment, they do worse than patients that they do not have an autonomic impairment. This is another example, patient with autoimmune autonomic ganglionopathy, a severe form of autonomic failure, but is a treatable condition. We can use immunotherapy and the patient, they do recover. And they do have a widespread autonomic dysfunction. And what I want to share with you, you can see how the thermoregulator sweat test is completely different than the one you have seen in diabetes. It's very patchy. And we use the amount of sweating as a biomarker of whether the patient does or does not respond to immunotherapy. So this is a patient, for example, that responds extremely well to immunoglobulin. And we have also demonstrated that then when they respond because they are able to re-innervate, okay? So this is a skin biopsy of patients with an autoimmune autonomic ganglionopathy before and after steroid. So if you want to focus just on the sweating, you can see then this is a sweat gland very much denervated, even though the patient was denervated all over. So these are somatic fiber, these are autonomic, and with a re-innervation after the steroid. Okay, so the very last few slides, this is an example of neurodegeneration. This was a multi-center study in Parkinson disease and multiple system atrophy in the early stage, so within 3 years of onset. And you can see then they are very much impaired in terms of thermoregulation with the denervation in the skin. And this is, I guess, the last example of even in the early stage. So a patient can present just with isolated autonomic failure, which we call the pure autonomic failure. And a third of this patient, they would progress into Parkinson's disease or dementia with Lewy body or multiple system atrophy. And now we have established which biomarker we can use to predict actually the progression. So thermodysregulation, cardiovascular failure are important biomarkers. So to summarize, thermoregulatory dysfunction is increasingly relevant in neurology. Pseudomotor dysfunction affects several systems, so heat tolerance, cardiovascular autonomic stability, exercise capacity, and daily functioning. Pseudomotor testing can provide insight into the pathology causing autonomic failure, and we can combine the test to localize the lesion. And if anyone is interested, so at the British Autonomic Society, the first conference, there will be a focus on thermoregulation and exercise physiology. So if anyone wants to attend, you would be very welcome. So this is just a thank you to the team and to the patient and the founder. Thank you so much.
Fantastic. Thank you so much, Valeria. And thanks to all speakers for keeping to time. Any questions for Valeria? The gentleman there. Okay. Please wait for the mic.
Thank you. Thank you very much for this presentation of sweating and how it's regulated also. So I was wondering with the patients with the autonomic dysfunctions early on, is that only then affecting the pseudomotor activity, or is there also, for example, vasodilation affected in those patients? I mean, how specific are these autonomic dysfunctions then to only affecting sweating?
So if I understand the question, so whether this patient, they might present just with a pseudomotor dysfunction.
Is there some that are so specific to only?
So there are disorders and they only present with a pseudomotor dysfunction, they do not progress to something else, yeah? So an example might be the Harlequin or the Ross syndrome. This disorder, like pure autonomic failure, if they start with a pseudomotor dysfunction, eventually will progress. There is no patient then remain isolated just with a thermodysregulation.
Thank you very much. It sounds like we have an online question.
Question is from Omar Tayari. Would serial acclimation achieve the same effect as immunotherapy for the postganglionic syndromes or thermoregulatory failure?
I don't think so. So for the autoimmune condition, there is an antibody blocking at the ganglia level. Yeah, so is blocking the alpha-3 subunit of the acetylcholine. So acclimatation, it might expose the patient might compensate a little bit better, but I don't think it would solve it.
Thank you. Do we have time for one more question, or because we have to finish? Okay, no more questions. So if you have any questions for our speakers, you might be.
I will be very available.
Catch them during the
absolutely
coffee break or at the panel discussion at the end. So
thank you.
A big thank you to all of our speakers. Great. Welcome back. This is the last session of the day. In case you just joined, I'm Anna Mavrogianni. I'm a professor at the Bartlett UCL. I will be chairing this session on behalf of Sanjay, who unfortunately was unable to join today. So this session will look at adaptation and mitigation strategies in neurology and neuroscience. Just to say that straight after this, the three presentations, we will move into a panel discussion with our speakers. So if we run out of time for discussions during the session, or if you have any questions on the earlier presentations, you'd be welcome to ask them during the panel discussion. Our first speaker is Robert Meade, a thermophysiologist in the Department of Epidemiology at the Harvard T.H. Chan School of Public Health and the Salata Institute for Climate and Sustainability South Asia Cluster at Harvard University. Robert's research focuses on developing and implementing large-scale studies that blend thermophysiological research techniques with shoe leather epidemiology to support the creation and evaluation of community-led heat adaptation strategies. Robert also directs multiple projects investigating how physiological determinants of body temperature regulation translate to population-level health impacts, and identifying when limits for human heat tolerance may be surpassed in regions facing the most severe increases in heat and humidity. In his previous role at the University of Ottawa, Dr. Meade designed the first day-long heat wave simulation studies to evaluate the physiological impacts of extreme heat and the efficacy of commonly recommended cooling strategies for limiting physiological strain in vulnerable populations. Looking forward to the presentation.
Great, thank you.
Thank you.
Need to shorten that bio. Title of the talk today, Evidence-Driven Heat Adaptation for Homes, Workplaces, and Hospitals. Kind of the title assigned to me, and I realized going through it that you could probably do an entire day-long presentation or group of presentations on any of these locations. So what I decided to do today was to kind of just give some examples of some of the studies that are looking at cooling, particularly in its impacts on human physiology in these locations, while also trying to build a bit of intuition with how cooling interacts with our body's thermoregulatory system and why understanding this interaction or getting a bit of intuition on this interaction helps us understand why certain strategies are more effective than others. But unfortunately, I do have to start with a little bit of a primer on thermoregulation. We covered a lot of this kind of earlier in the day, so I'm going to keep it very brief. But the one thing I didn't kind of hear mentioned, and it's worth mentioning, is that thermoregulation is an entirely negative feedback approach, more or less. Basically, the body is continuously monitoring the temperature of numerous thermosensitive tissues. That information is being integrated in the brain, and the brain, if it senses tissue temperature is increasing, is going to elicit thermal effector responses, skin, blood flow, and sweating. And the goal of these processes is to maintain a balance between heat loss and heat gain to ensure that body temperature remains within the limits of normal physiological function. This figure here is that kind of idea zoomed in a little bit. This is a very common figure in thermal physiology, probably in every thermal physiology master's and doctoral thesis. So we're going to spend a little bit of time here, but it's going to really set the stage for the rest of the presentation. So this shows the relationship here between body temperature, not core temperature, body temperature on the x-axis, and heat loss and heat gain on the y-axis. If we're exposed to a hotter environment, or if we get up and start moving around and producing heat internally, as I mentioned, what we're going to be kind of presented with is a situation where we're now gaining more heat than we're losing to the environment. This is going to cause heat to be stored within the body's tissues and the tissue temperature to rise. At some critical temperature, we call it the onset threshold, we're going to see activation of skin blood flow and sweating. They don't activate at the same temperature necessarily, but this is a very simplified figure here. And at this point, what we're going to see is core temperature or body temperature and heat loss rise in concert until one of two things happens. Either the level of heat gain can be compensated for by the thermoregulatory system. This is what we call compensable heat stress, and we attain a new state of thermal balance, or we get in a situation where the total level of heat gain from the environment or physical activity completely outstrips the body's capacity to dissipate heat. Body temperature goes up and up and up, and this is where we're at risk of heat stroke, like Dr. Bouchama showed in his presentation. Now, the reason I really like this figure is I want to point out one thing that is often not recognized, even by thermal physiologists, is that even under compensable conditions, body temperature needs to increase. And this happens because, again, thermoregulation is negative feedback. Body temperature needs to rise to the level needed to activate heat loss responses to an extent sufficient to maintain thermal balance. And so as long as we're exposed to hot conditions, even if thermoregulation is happening as it's supposed to, we're going to be under strain. And this is not just strain on body temperature, this is cardiovascular system, this is the kidneys, this is the brain. And so we really need to be increasingly concerned with these prolonged heat waves we're seeing, where multiple days of exposure leading to accumulation of physiological strain. Another thing that we can think about if we view thermoregulation in this way is we can actually kind of split cooling strategies into two main types. Ollie actually mentioned them in his talk. The first of which is cooling strategies for abating heat stress. This is very much what it sounds like. Basically, if we can in some way cool or decrease the amount of heat buildup in the environment, the amount of heat gain we have to offset will be reduced, and core temperature will be reduced as a result. Very straightforward. It's not like a extremely riveting finding or concept. But we know from the physiological literature that these strategies are often going to be the most protective. This is some data actually from my doctoral thesis. What we did was we invited a group of older adults into a laboratory on 4 separate occasions. We exposed them to 8 hours to a range of different conditions. We have 36 degrees Celsius up here, which is a heat wave in Ottawa, all the way down to 22. And you can see that core temperature, body temperature, and the same responses we're seeing for heart rate, blood pressure, all these additional variables, basically equilibrates in proportion to the level of thermal strain. We also found in kind of follow-up work here that prolonged exposure to particularly the hottest conditions also leads to a whole host of adverse impacts on the cellular response to heat exposure, inflammation, changes in eye function, changes in kidney function. So if we can prevent that heat stress, very simple, we don't get heat strain. We've also looked, though, what happens when we think about like a more brief cooling. So this is a study where we did a very similar kind of protocol, day-long heat exposure. Get used to these; there'll be quite a few of them. But halfway through, what we did was rather than expose people to a cool environment the entire time, we moved a group of older adults into like just another room that was cooled, simulate a cooling center. And as you can see in the cooling center, very, very stark and rapid reduction in core temperature. And then, interestingly enough, when they return to this heat, the heat core temperature increased again to the level it needs to be to maintain thermal balance. So, you know, just the kind of key takeaway here is cooling center is effective for limiting thermal strain, but the second you leave, if you return to a hot environment, your body's going to do what it needs to do to maintain thermal balance in that environment. But there's actually quite a bit of evidence that these two strategies are actually very protective from the epidemiological side of things as well. This is what I might call a famous meta-analysis by Dr. Bouchama, where essentially what it did was review a bunch of case control studies that evaluated prognostic factors for heat-related mortality in major heat waves. It basically found that if your home had a working air conditioner or you visited a cooled location on the day of the heat wave, you were 70 to 80% less likely, or the odds were 70 to 80% less, 70 to 80% less of dying during a heat wave. Ambient cooling, if we can prevent the heat stress, very protective. Some other examples outside of this kind of older adults, home kind of exposures, even though those were laboratory studies, came across this really interesting study where what they did was they installed radiant panels in hospitals and either assigned admitted COPD patients to a radiant cooled room or a non-radiant cooled room. The idea behind radiant cooling is that if you have a panel or part of the wall that is cooled, the body will just naturally radiate heat towards the panel and help kind of extract that, I guess kind of offset the effects of a hotter environment. This was done in Germany in the summer. And what they found was that those with a radiant cooled room, the hospital stay was 6 days on average versus 9 in the without the cooled room assignment. And you know, we also saw the kind of, or they also saw the kind of typical effects on body temperature, blood pressure, fluid intake changes, and then actual daily activities. So very interesting. Though I will note on this one that the admitted patients in the radiant cooling group were quite a bit heavier than the non-cooled room, so maybe a little bit of confounding there, but still an interesting study design. Another interesting study, actually by Ollie's group, who just walked in, and in a collaboration with Aaron Bach's group at Griffith University. What they did in this study was essentially, in a two-part project, was simulate the effect of different roof types on a garment factory in Bangladesh. So compare the kind of standard roof, which is mostly made of metal and concrete, to a simulated green roof. The idea being you have plants on a roof, it helps evaporate kind of the heat away from the factory, versus a couple different types of white roofs. The idea being if you can reflect incoming solar radiation, you can prevent the buildup of heat within the factory. What they found was in terms of air temperature, the non-cooled factory got up to about 38 degrees Celsius, but the different roof types could reduce the temperature by about 2 degrees. But what makes this kind of modeling interesting was what they did then was bring the modeling actually into the laboratory, and they simulated these conditions during a 3-hour work bout and saw what the effects that the different kind of exposure, the different interventions had on core temperature and heart rate. Core temperature on the left here, heart rate on the right. And you can see here that the roof and the roof with a fan, and we'll come to that in a second, both reduced the core temperature and the heart rate the workers experienced. But as you might expect with something that's only lowering the temperature by a couple degrees, not quite the same reductions as was seen with an active cooling approach with AC. So fans are kind of a good segue into the second classification of cooling strategies, or at least the way I like to think about them. And these aren't strategies for limiting heat stress. What they function to do is change the way our body kind of interacts with the thermal environment with the goal of limiting heat strain. So here's our curve again. And what we see with these strategies is, again, there's no change in the level of heat exposure or heat gain. But if we can push that curve to the left, then what we can do is basically have the same level of heat loss, attain thermal balance at a lower body temperature, a lower physiological input. The way a fan does this, for example, is by increasing the flow of air over the skin. It's actually quite complicated how a fan impacts heat exchange. In most environments, it will actually help kind of increase convection, but even in very hot environments, we can improve the efficiency of sweat evaporation so we don't have to sweat quite so much. Our body temperature doesn't have to be quite so high. But what you find with these strategies is that they're generally not quite as effective as the kind of more strong and energy-intensive ambient cooling approaches. This is a study at University of Ottawa we did, led by Fergus O'Connor. Exposed a group of older adults to 31 degrees Celsius, 45% relative humidity for 8 hours with and without a ceiling fan, which we rigged up with this kind of crazy contraption that we built in the lab. And you can see in both the no fan and the ceiling fan condition here. Core temperature increases from the start of exposure. Doesn't get quite so high in the ceiling fan condition, but the difference in core temperature between them at the end of exposure is only about 0.1 degrees Celsius. Kind of similar effects for heart rate, a small 2 beat per minute reduction in heart rate. Another kind of commonly recommended or is tested approach that again is meant to augment thermoregulation is this idea of skin misting. If you can cover the skin with a layer of water, then you can evaporate that water. You get the evaporative cooling benefit without having the sweat input. Core temperature can drop. This was a study done by Zach McKenna at Craig Crandall's laboratory in Texas. And control condition here in the white versus the skin misting condition, see about a 0.3 reduction in core temperature and a reduction in heart rate. You might also notice in this one, fans actually increase thermal strain. This is because in very hot, dry environments where there's no kind of impediment to a sweat evaporation, what you're doing with a fan is you're just forcing dry air over the skin and you're not getting that evaporative benefit. Even in very hot and humid environments, you often see the kind of reverse where you still get some benefit of using a fan in these environments. Another very low-cost cooling strategy that is often recommended is things like foot immersion or placing cold towels around the neck. In this 6-hour heat exposure at University of Ottawa, what we did is we brought a group of older adults into the heat. We had them rest their feet in this 22-degree water tub, and then we placed a wet towel around the neck in some trials. A wet towel, not an ice towel, the idea being these are strategies you could employ if the power went out. Really nothing going on for core temperature there, but we did see some kind of small to moderate impacts on heart rate, even though the figure here doesn't quite look like anything's going on. And, you know, as with the physiological data, the epidemiological data on these types of strategies is maybe mixed is the correct word. We don't have a lot of information on how a fan actually protects you during a heat wave, for example. But again, that same meta-analysis found, you know, on average about a 0.4 or 40% reduction in the odds of dying during a heat wave. But the confidence intervals kind of range from a very large reduction all the way up to kind of no effect. So bit of mixed evidence there. This one's interesting, taking extra showers. You often see this recommended. There's been no study to look at the physiological effects of taking extra showers. And the epidemiological data, you know, it's just basically inconclusive. So interesting that you continue to see that kind of recommended. It's one of those things that just kind of seems like a good idea. Another study, again, in kind of a more occupational context, really interesting study by Aaron Bach's group again. What they did was actually test different cooling strategies in a Thai sawmill. Really, what's cool about this study and what I really like about it is they use this kind of interrupted time series approach where it was a crossover trial, but the workers first worked without any cooling strategies, took a lunch break, and the cooling strategies were applied after lunch. And you can see when they applied either a cooling vest to the workers or allowed them to take these kind of numerous breaks in what they called a cooling oasis. So this was a room where they had access to fans and water. Just blunted increase in core temperature during the second half of that workday, and kind of similar effects on heart rate as well. And this study strikes me because it's a really interesting example of actually, you know, a real world study where the authors have gone out and actually evaluated the impacts of cooling in the actual environments where they're being applied. And I think this is really important that we kind of shift our focus to these types of studies moving forward, because the laboratory environment, I don't know if you noticed by some of the previous pictures we saw in the last session, doesn't really approximate what we're experiencing in the real world. You know, we do have these studies where we're simulating heat waves in the laboratory. They've gone from 3 hours to 8 hours, and now we're up to 3 days. But often what we see is participants kind of petition in front of the fan, directly blowing on their body. In that study where we had, you know, people with their feet in cold water, that was a 100-liter tub of water that we had to drag with a cart, fill up, and then move back. 2 students had to do that. And so you can imagine if you were an older adult trying to kind of keep that thing cool in your living room, probably wouldn't work too well. Same thing with skin misting, actually. It's usually the researchers applying it. So when you have changes in thermal sensation or perception, do people consistently apply it in the real world? Who's to say? The laboratory studies give us a really good idea of the efficacy of strategies, but we need the studies to kind of look at the effectiveness. And then running. Oh, I'll finish up quick. Just wanted to highlight this, that we are actually doing this in India. Our group is involved in a very large monitoring study where we're evaluating different heat adaptations in collaboration with the Self-Employed Women's Association, which is a large trade union of informal workers in India. I'm not going to run through this, but just want to point out that one of the things we found already is that the average heat index within participants' homes, so day and night daily average, is about 44 degrees Celsius from May all the way to September. So we're just not dealing with the level of heat exposures in real life that we can really account for in the laboratory. So just this need for kind of going into the places that cooling is going to be applied. And then, also recognizing that this is probably going to take a variety of approaches. We often study cooling in isolation, but if you were a doctor, for example, you would never tell your patients to either sleep well, eat well, exercise. Cooling is going to be applied as packages. And so thinking of ways, I'm not going to go through this, but thinking of ways that we can offset these powerful cooling approaches like air conditioning, make them more affordable, make them more applicable with these passive approaches like cool roofs and then fans as well. So the UNEP would call this a hierarchy of cooling. Ollie likes to use the term fan first cooling, but just this kind of mixed holistic approaches is how I think we're going to be able to provide the people that need it with cooling while not continuing to do damage to the planet. But I'll end there. You can read the takeaways because I'm near end of time.
Thank you very much, Robert. Such interesting work, and I definitely agree with your point about being holistic about cooling strategies. Any questions for Robert? Gentleman there. You could wait for the mic, and just a reminder to hold the mic close to you.
Rob, it's a really very good work, and thanks. And thank you for the slides and the comment about my work.
Could you please introduce yourself?
It's okay. In all this work, you are looking at the body temperature, but maybe this is not the right target. Maybe the target is a system that protects the cells from tissue damage and heat stroke eventually. The system that protects is, again, the chaperone, the heat shock protein and the heat stress response. Now, this is a suggestion if you have not done that. You show in the second, I think, slice, the temperatures goes up, do some cooling, goes down, and then when the people go back to the environment, they go up. If you look at the heat shock protein expressions when they cool down, and if the heat shock protein goes down, and then when you put them back to the environment, they increase, and you demonstrate that the heat shock protein goes up, that's preconditioning. That will protect them from tissue damage. This is one of the most classic paper is published in Science in the 70s. When they heat the cells, mild heating, you see the heat shock protein goes up, then you cool them, and if you heat them again, they become resistant to extreme temperature. You might see that in the whole body. So maybe the next target is to see what cooling duration that will create a preconditioning situation.
Yeah. So in all those studies, we do actually collect cellular responses. We've published quite a bit of it. I should say the group at University of Ottawa has. We do the heat shock proteins, but we also do autophagy and apoptosis. And in that actual cooling center paper, what we found was even though core temperature had returned, when we took that end of exposure blood pressure, autophagy was preserved and apoptosis was down. So there is, I agree. I just wanted to present the kind of thermal physiology side, but you're correct. There is this entire cellular component we also need to consider.
Your paper on autophagy, but I think the autophagy and proteasome degradations are not the first choice of our bodies, because they consume more energy than the heat shock protein refolding, repairing the. So the heat shock protein is better, I believe, endpoint than the elimination of waste. The denaturate protein that the body cannot repair because of the cost of energy is huge, just by eliminating this protein by either autophagy or proteasome.
Yes, by no means my field. What we found though with these kind of longer term but lower stress exposures. The heat shock proteins, you'll sometimes see an increase, sometimes you won't, particularly in the older adults. So we do evaluate them as well. The autophagy responses of just seem to be more sensitive as a marker of kind of cellular changes. But no, I agree, the heat shock protein is probably the better target.
Great, thank you. I think we're running a little bit late, so if that's okay, we'll move to the next presentation. But if you have more questions for Robert, please wait until the panel discussion. Thanks again, Robert. I'd now like to invite our second speaker, Sarah Sheard. Sarah is a cardiothoracic radiologist with an interest in sustainable healthcare. She is active in research into the environmental impact of imaging. She currently chairs the European Society of Radiology Sustainability Committee, where she has led the development of the Green Imaging Department Green ID certification scheme and introduced sustainability into the European training curriculum. So very interesting. Over to you, Sarah.
Thank you very much for the invitation to join you this afternoon. I think it feels like quite a big pivot from all the other topics that we've been looking at today. And it's actually the first time I've presented our sort of work and area of interest to a non-radiology audience. So I hope I'm sort of pitching it at the right level. And I sort of haven't really had an initial slide just talking about sustainable healthcare. So I'm just going to sort of quickly preface my first slide with the whole area and interest in sustainable healthcare. I think we've seen some talks today about the impact of climate change on patients' health, and the sustainable sort of healthcare movement as such is really looking at the sort of paradox that actually healthcare activities are hugely polluting, and as doctors and sort of healthcare professionals and scientists, they sort of have a most sort of responsibility to address that as a healthcare issue. There is sort of published, we have seen from lots of talks today that sort of climate change is potentially the biggest threat to human health, and I think that's the World Health Organization's line on the topic. But actually globally, healthcare activities contribute about 4% of global emissions. In Europe, that's more like 7 or 8%, and in the USA, that's up to 10%. So this needs addressing. We want to sort of reduce emissions across the board. So, sorry, I'm just going slides. So over the last few years, since I've started working on this topic for about 5 or 6 years, and there's really very little sort of going on in terms of research, we are starting to build a much more detailed picture of the environmental impact of imaging in particular. And we're sort of driven by, in the UK, we're driven by the NHS, which in 2021 published a paper on what sort of set out a target to be net zero by 2040 in various stages. And lots of different specialties have then had to sort of sit down and look at, well, if we were going to achieve that, what are actually the environmental impacts of our activities? So we've done that in imaging, and it's been quite a challenge because certainly at medical school we didn't learn how to do things like carbon footprinting and things. So it's been a very sort of rapid learning curve. So this is my first slide, just sort of a roughly life cycle analysis inspired diagram of what happens in imaging and how we can identify the different areas of sort of generating emissions. I don't quite know sort of roughly how much experience there is in the audience from a clinical sense, so I'll try and talk to it sort of quickly. But so what happens when a patient has an imaging test, so an X-ray or a CT scan or an MRI scan? Well, that referral usually comes from a clinician, be that the GP or from outpatients in the hospital or from the hospital ward. Somebody requests an imaging test out here. The patient then, if it's an outpatient, which most of our work is, the patient then has to travel to hospital via some means. We see, we have lots of central London hospitals, but I've reviewed a couple of submitted articles recently looking at some patients travelling for scans in sort of remote outposts in Canada, which is obviously a much more polluting activity. So the patient travels to the hospital. Inside the hospital, we have the hospital buildings and facilities which have to run and reduce emissions and other sort of environmental impacts. Inside the imaging department itself, we use a lot of power. We run scanners. We have to keep our rooms to the right temperature, so we use a lot of air conditioning. We have lots of ICT equipment. We use consumables if patients are being given IV contrast. We have lots of single-use plastic tubing. We also use iodinated contrast material, which has an environmental impact and downstream pollution impacts as well. Then when the patient has had their scan, that scan needs to be stored somewhere. And also we have the whole reporting room, which is usually very nicely air conditioned to an ambient temperature with lots of radiologists looking at scans, which on some big workstations that use lots of electricity. And then finally, when the radiologist has made a decision, we then have downstream impacts of imaging. So have we suggested they have another scan? Have we found incidental things that then need to be investigated further? So that's a journey through radiology and main sources of our emissions. There are some areas now that we beginning to understand very well because of lots of research that's been going on by colleagues around the world. So we actually know quite a lot about what goes on in the radiology department in terms of what power we're using, our consumables, our reporting. Data storage is an emerging area, and I'm going to talk a little bit more about that shortly. Patient travel is very interesting, and it's a bit flummoxing for us at the moment. But there was a recent study in America which estimated that 6.4% of healthcare-related emissions in the USA are due to patients travelling to healthcare facilities. And there's a group in Manchester, a radiotherapy group in Manchester, did a really nice study about patients travelling into hospitals for external beam radiotherapy. And it was quite nice because I think many of the different elements of their practice strongly reflect radiology. They had lots of outpatient travel, they have energy hungry machines, and so it relates quite closely. And they found that sort of 70 to 80% of emissions from a patient having a course of external beam radiotherapy were due to the patients traveling to the hospital. So we still haven't quite figured out how to look at that in radiology, but working on it. So firstly, let's just have a look at some of these areas in greater detail. Power consumption. So this is some colleagues in Switzerland from the University of Basel who have done a lot of work looking at power consumption in imaging. I think everything with a plug in their department has got a power meter on it. They've got an amazing dashboard looking at what energy is being used. And they've done this study about cost saving opportunities and energy saving opportunities in CT and MR. So this is the graph from the CT, and what the important thing that they've done in this study is to break down the time of, so the whole day, and also the energy consumption into the different power states of the machine. So I don't know if any clinicians in this room have sort of accompanied patients to the scanners for CT scans, or if people have had a CT scan themselves, they'll know that actually very short time, a matter of seconds, are actually the active scanning time. Much of the time is patients being put onto the table, patient details being entered into the scanner, and the table being moved around for positioning, and then afterwards the scanner then has to take its raw data and convert it into images and send them to PACS. So the net scan time is the actual few seconds when the patient is being scanned. So this is in terms of time that's happening and the amount of energy it's using. Active time includes the net time, so that's the time that the patient's in the room, basically from starting to put the patient details into the machine and plan the scan to when the images are sent off to PACS. And they have then generated or calculated an idle time, so all the time and all the power consumption from when the machine was switched on, taking away the active time. They've got idle time, and basically what they found was that 2/3 of the energy consumption from a CT scanner, and they've used 3 here. They've got their emergency scanner in the ER and then 2 other in and outpatient scanners, and 2/3 of the power consumption from those scanners was due to idle time, so when the machine was on but not being used. They did the same for their MRI scanners. It's quite a different picture because MR scanners take much longer to acquire their scan and they use a lot more energy. And interestingly here, they found that, I can't remember, a third of the energy consumption for MR is actually when the machine is off, switched off, because there's lots of background energy consumption because you have to keep it cool even when the machine's off because of the magnet. So very interesting look at the way we're inefficiently using power. I mean, I think it's different from MR, but certainly in CT, there's not really much excuse for using 2/3 of our power when the machinery is switched off. So mitigating this sort of unnecessary power consumption in CT and MR, a lot of it is actually behavioural. They talked about the sort of urban myth that it takes more energy to switch a machine back on than it does to just leave it running. Scheduling is important, and I think it's quite interesting as a sort of NHS employee thinking about sort of leaving a machine running during lunch break, and I'm not sure machines are ever not running during lunch break, but obviously in some countries they all go off for their nice lunch and just leave the machine switched on. But certainly efficiently using the machine so you're reducing the amount of idle time between scans is valuable. There's lots of work. The same team from Basel have just run a study trying a new software upgrade, which puts the machine into an ultra low energy idle mode, which they've designed with Siemens. And then new technologies such as low helium and helium-free MRI scanners, which will reduce the amount of power that's needed when the machine is not switched on. So we'll just have a quick look at interventional radiology because that's always quite pertinent to sort of neurointervention, although this is very sort of generalizable. This is a really good study that I go back to quite often by a team from New York, vascular interventionists, and they have this life cycle analysis. It's very similar to surgery, basically. The patient moves in through the radiology department, so they go to intake, which is basically anaesthetic room, procedure room, recovery. There's electricity, natural gas, anaesthesia, single-use supplies and linens coming in, and various different wastes coming out. And so they put this really nice detailed map together about the emissions sources in their interventional radiology department. And the sort of headline results from this study, they looked at a week of daytime procedures, so they didn't do anything out of hours. They were quite satisfied that it was normal, representative of their normal case mix they would encounter during the week. The study did not include looking at the emissions from post-operative care or from the patient travel to the hospital. But what they found, so this is the sort of emissions inventory. So the relative contribution to total greenhouse gas column on the far right, the heating, ventilation and air conditioning in their interventional radiology suites used almost 50% of power, or created almost 50% of the emissions from the whole department. That was rapidly followed by the single-use disposable equipment. So that's the manufacture, transportation of plastic items, dents, wires and things that they're using, which are single use. That was 41%. And actually the imaging equipment, which is lower, tends to be sort of X-ray fluoroscopy rather than an MRI scanner, but that was actually less than 3%. So now let's just have a quick look at data storage. So it's an emerging area, really. It's not often seen in radiology studies about our emissions because we just don't really know that much about it. So when a patient has a scan, the scanner takes the images that it's produced and sends them to a PAC system, so it's short for picture archiving and communication system. That can be stored on-site, off-site, or cloud-based, and all of these have different energy profiles. There are options for deep storage states, which are not commonly used, but they do consume less energy, but then obviously they're slower to access, so we just have to sort of weigh up the differences between how quickly we need to be able to look at images for patient safety. And at the moment in the UK, image retention policy, so how long we can keep them before deleting, is sort of roughly covered under the sort of patient records guidelines, but there's no sort of robust policy. So, I mean, certainly in our hospital, I know that we're not deleting any images, they're just being stored. So this is a study we did last year at Imperial, looking at the greenhouse gas emissions from long-term data storage in CT scans. So I haven't put a picture up, but I think hopefully many of you are familiar with what CT scans look like when they come across to a viewing screen. So in the olden days, when we had sort of quite basic PACS viewing software, the CT scanner actually itself would have to generate all the different planar images. So you usually get an axial image, and then it would generate a set of coronal images and a set of sagittal images and send those all across to storage. But in the last 10 years or so, it's quite standard now for PACS systems, so the radiology viewing system, to actually just be able to take one set of the axial images and just reconstruct those for you on the sort of viewing platform. So it's not necessary to store many different series. So we did a study looking at, we just took a cohort of endometrial cancer patients who will routinely have a baseline CT scan of their chest and abdomen and pelvis, so quite a big amount of data. And we combined with another site in Canada to look at how much unnecessary imaging was being stored, basically. And then we did a survey of some other sites just to find out what they were storing as well. And so we found that 17 out of 18 sites that we investigated were storing unnecessary images. We looked at the file sizes of what was being stored. So actually this 31% axial images is all you need now. That's all that's necessary. So actually 69% were these other reformats, which are totally unnecessary. And then we modelled some mitigations to see what impact that would have on the cumulative emissions from storing these for the next 20 years. So business as usual is this red line up there. So this is greenhouse gas emissions over 20 years. If we only stored the axial images, that is the M1 here. If we used cloud storage instead of on-site storage, that would be M2. And implementing a data retention policy, so with a defined period before they're either put into deep storage or deleted. And then if you combine them, that obviously has an even greater impact. So basically we found that if we only stored essential reformats, you could reduce the CT data storage emissions by 69%. And if you did all three of those, it'd be 89%. And I did a quick, I think so on-premises storage of all new UK endometrial cancer baseline studies over those 20 years would equate to the emissions from about 40 households. And that's just a very small group of patients with a defined condition. So, extrapolate that across the globe for all imaging, it's quite astounding. But what I've sort of come to realise over the last few years working with lots of sustainability colleagues in Europe, we sort of started off really so excited about looking at power consumption in imaging equipment and all these sort of other impacts that are happening in our department. But actually the spotlight's swinging around very rapidly to the issue of sort of growing imaging demand. And so I'm just going to skip over this, but we're just looking at sort of, we've looked at lots of things inside here, but what's going on at either end. And the big issue really for us in radiology is rising demand for imaging and low value imaging, because you can sort of save 30% of sort of emissions on doing a slightly different CT or using a CT scanner slightly differently. But if the imaging is growing, demand is growing exponentially, then sort of almost what's the point? So the World Health Organization said that there were about 3.6 billion imaging examinations performed annually, and they think that about 20 to 50% of these are low value, and demand is growing. This is the King's Fund chart from data from NHS England, which looked at the change in diagnostic tests, number of diagnostic tests performed between February 2020 and February 2024. CT scanning has gone up by 30% in England since 2020 in that time period. So tackling low value imaging is really a big priority in the whole radiology community. It's a priority for those of us who are interested in sustainable imaging. It's a big priority in the US because insurers don't really like paying for scans that aren't really necessary. You know, it's a huge financial cost and it has sort of access and equity issues as well. So low value imaging is basically imaging that is of little to no benefit to the patient because it either has a very low diagnostic yield or it doesn't usually change management significantly. So the fight back really is groups who are doing a lot of work on really clearly defining an evidence-based guidance about what studies should be done and shouldn't be done in certain contexts. So this is a group who've done a really big review. They've done all the different systems, neuro, on about studies that don't really need to are deemed low value. And I mean, the interesting thing is actually down here, they say don't do an X-ray, go straight to a CT. So it's always sort of, it's a lot of push to, if you are answering a clinical question which does need imaging, try and do the right test first, which means you won't have to go back to another one. There's also a lot of work on making on incidental findings. There's huge sort of working groups, especially in the US, looking at incidental findings on imaging and building a really strong evidence base when they need further evaluation. And then also looking at sort of follow-up imaging and whether patients sort of, again, a really clear evidence base about following up conditions and how frequently they should be having re-imaging and if it needs contrast, etc. So it's my last slide in handling time. But so one of the real big pushes, and it sort of feels like we've moved quite a long way away from climate change and sustainability, but actually clinical decision support tools which really integrate this evidence base for moving low value imaging and making it easy for clinicians to request studies with evidence of integrated guidance about what test is right to do at the time. So in conclusion, power consumption of imaging is very inefficient. We're starting to learn more about patient travel and data storage in relation to their imaging tests, and those are likely to be very big contributors. But if demand for imaging continues to grow like this, the marginal improvements we can make will be quickly lost. Thank you very much.
Thank you very much, Sarah. Thank you. That was so interesting. We have time for one question. We'll go first. It's on there. Thank you. Please wait for the mic to come.
Hi, thank you so much for your presentation. My name is Shui, and I am a sexual health doctor at Imperial at the moment. And I'm just curious to hear, like you talked about low value imaging, I guess from your experience or any literature, have you found any specialties that are more kind of prone to low value imaging in practice, and maybe like what part of it is like, I guess, defensive, like practice in medicine as well? Yeah, just curious to hear about your take on that.
Yeah, I think that's a really good question that I couldn't specifically say. I think it's interesting because a lot of imaging now is very strongly guideline driven. You know, cancer pathways will have very defined follow-up sort of intervals, etc. I just think there's a creep and there's a culture as imaging becomes more available, people are more likely to, you know, reach for it. I think there's been a big expansion of general practice being able to sort of refer directly for cross-sectional imaging, which in some cases is brilliant, but it just, the sense of availability, I think, has made it very easy for people to ask for it. And as radiologists, we haven't been, and in some cases, I think it's justified, you know, it does make things better, but now we're sort of having to backtrack and look more carefully about how we can gatekeep a bit better for the benefit of patients and for, you know, resources and the planet, which is going to be a big task.
Thank you very much. So if you have any more questions, please wait until the panel discussion. So our last speaker for today will join us online. Do we have Diarmid? Yes. Great. So our last speaker is Diarmid Campbell-Lendrum from the World Health Organization. Dr. Diarmid Campbell-Lendrum is the head of the Climate Change, Energy and Air Quality Unit at WHO. His training is on the ecology of infectious disease and public health, and he has worked on climate change and health for over 25 years. He has helped drive the expansion of WHO's program on this issue, which has now directly supported over 30 countries. Diarmid is author of over 100 papers on infectious diseases and on the health implications of global climate and environmental change. He's a member of the US National Academy of Medicine, a lead author of 3 reports of the Intergovernmental Panel on Climate Change, and of the first 2 health reports to the UN climate negotiations.
Thanks so much. So first off, thanks so much for inviting me to this conference. Apologies that I can't be there in person. Part of my contribution to trying to keep my carbon footprint down. And it's, to be honest, really quite humbling to be able to present in this meeting. I've been able to join just for the last hour or two and to follow the discussions. And as the introduction has made clear, I'm absolutely not a neuroscientist. I'm somebody who has specialized in climate change and health for a little over 25 years now, starting at a time when there were really maybe 10 people in the world who were working on this issue. And the reason I say this is humbling is that it's incredibly impressive to see these learned communities fully pick up the connection to climate change and to describe all of the connections to their own areas of work and what they are able to contribute to doing about it. And my presentation is going to be quite different, I think, to what you have heard before. It's going to probably sound quite generic or general or sort of high level because climate change is such a cross-cutting issue across health. What I will try and do is to try and get across how all of the excellent science and practice that you're discussing in your conference makes a connection to the overall effort to address the health implications of climate change and to basically contribute to addressing the climate crisis. And just as the previous speaker kindly referenced, just to emphasize the recognition that there now is of the climate crisis as a determinant of pretty much everything that affects human life on Earth, including health. So I think WHO first made that statement about climate change being potentially the greatest health threat of the 21st century in 2007. And over the intervening years, including through quite a lot of hard championing by climate change and health advocates, it has now been recognized as the threat that it really presents to human life. And that's the same whether you go to the World Health Assembly or if you travel to Davos and hear what the people in the World Economic Forum think about the threats facing the planet. There are a wide range of things to worry about in the world. Some of them are immediate risks, but if you look anywhere in a sort of a medium to long-term time frame, then most people recognize that the damage that we're doing to the natural environment, including to our climate system, are amongst the biggest challenges that we now face. And that's borne out by polls of the general public as well. And I've worked in this field long enough to have gone from talking about the impacts of climate change as a potential risk that we modeled to now being in the situation where these are observed impacts of the damage that we're doing to the climate system. So this slide is one of the summary slides from the last Intergovernmental Panel on Climate Change report. And we can see that across a wide range of ways in which climate change may potentially affect our health, we're already observing negative impacts in every part of the world. And that includes some of the domains that are being discussed in this conference, including non-communicable disease, mental health, and so on. So this is actually clearly now widely understood as a present impact. To try and do this job of trying to place everything that you're discussing in the kind of broader context that we see this from a public health point of view, I think it is really important to recognize that climate change, unusually for a health risk factor, doesn't just hit one disease or doesn't just work through one pathway. It works through a wide range of exposure pathways and impacts pretty much every health impact that you can think of. Pretty much every disease that you can think of is affected in one way or another by climate change. So it's just to point out that non-communicable diseases, mental and psychosocial health, they are on our list, but they're on our list because as one of many health impacts that are affected by climate change. Critically important, and we really need the specialist contributions of people who really know about each of these issues. But from our point of view as WHO, to put that in a broader public health context. And just to say that we have issues that are, I think, connected to or adjacent to ones that you're discussing in this conference. As I say, I'm completely not a specialist in this area. I do know enough to realize that mental health is not the same thing as brain health, but there, we see connections there. And this is an example of an issue that has really been emerging for us over probably the last 7 or 8 years. The appreciation and the stronger evidence base of the effect of climate change on mental health. I would say that when I started in this area about 25 years ago, we talk about extreme events, we talk about the effects on waterborne and vector-borne disease, maybe food security. We weren't talking about mental health, but I have probably not been to a climate change and health meeting in the last 7 or 8 years where the issue of mental health was not raised. So we continued to literally find new things to worry about in this field. And having said that, because this is such a cross-cutting issue, as WHO, with the limited direct capacity that we have, we tend not to go into a huge amount of detail on any one of these issues. But we do think it's really important in our convening and leadership role to lay out an agenda that is broad enough to encompass everything that needs to be done, and then, to be honest, to turn to the specialist communities that, such as the one represented in this room, to contribute to the specificities of any particular pathway. So this is just an example. We did a few years ago produce our first policy brief on the connection between climate change and mental health, and we're increasingly, I think, getting better at describing the linkages between climate change, brain health, mental health. And when we talk about climate change, we're talking about both the effects of a changing climate, but also the effects of what is driving the changing climate, which is basically pollution and largely the burning of fossil fuels. So as I say, this tends to be relatively sort of high-level stuff. It's more about the frameworks, more about putting across the headlines of the connections between climate change and these specific issues. But that is the kind of thing that WHO is probably best placed to do. We're less of a contributor to primary research. We're more of a synthesizer of research and a convener and trying to help to support and set the global agenda. And for example, this is our contribution specifically on mental health and climate change. I did also want to talk a little bit about what may be the largest connection between climate change and brain health, which is not through the weather itself, but through the other effects of burning of fossil fuels and the other unsustainable practices which are driving the climate crisis. So we point out that air pollution kills getting on for 7 million people every year. Other estimates are available, but they're sort of in that kind of order of magnitude. Almost all of those impacts are through non-communicable disease, and significant parts of that are, for example, through stroke. So when we're talking about the connections between climate change and brain health, we do think it's also important to talk about the ways in which the determinants of climate change also determine brain health. And again, to make this point that we see this holistically, even when we talk about the ways in which air pollution affects health, the different organs of the body or the different bodily systems. Brain health is on our list, but it's on our list along with many other things. And it's not to detract from the importance of brain health, and I'll get back to this in a minute. But it is to put into context. And but when we talk about interventions, we're often talking about interventions which will bring a broad range of health benefits, including, for example, in this case, brain health. But just to underline that point, that it is very clear on our agenda, these connections and the importance of brain health. If you look at our work on mental health, we are now pointing out that air pollution is a contributor to brain health and also to the impact also to mental health, and it's also clearly recognized as a risk factor, for example, for dementia. And I would say this is real progress for us. Previously, the main risk factors that were identified for most non-communicable diseases were individual lifestyle choice, if you like, risk factors, where now we're getting a better recognition that environmental risk factors are at least as important as many of these other more individual choices or more individual risk factors that are contributing to these conditions. And so, for example, if you look at our white paper on brain health, we are now highlighting the determinants of brain health, and not just at an individual level, they're also at a societal level, and therefore also at an environmental level. And air pollution is very high in that list of risk factors. So we want to talk about this not just as pointing out the scale of the issue and, as I say, the things that we need to worry about, but also in order to identify interventions that are either really effective for a specific risk factor or a specific pathway, such as the excellent presentation you were hearing a minute ago on the evidence for different interventions against heat stress, but also the kinds of interventions that may have multiple health benefits, such as the shift to clean energy systems, for example. And just I'll try and keep as close to time as possible, but just to emphasize how high WHO now has the climate change issue on its agenda. So in our current 5-year program of work, which goes by the unattractive title of the General Program of Work 14, GPW 14, WHO, and that's not just the agency, it's the 194 member states, now 193 member states. We only identify 6 strategic priorities across all global health. The first of those is climate change, and that is because of the wide range of impacts that climate change has on health. And this is both emphasizing the need to adapt to climate change to protect people's health from the risks of climate change, but also the health benefits that will come from promoting societies which have lower carbon emissions, therefore lower air pollution, more sustainable transport systems, and so on, but also the obligation that should be on the health sector to not emit any more carbon than it needs to in order to provide excellent health services. So the presentation that you've just heard immediately before this one. So our agenda encompasses all of that. And when we talk about climate change, we try not to set it up as a completely separate agenda from the everyday practice of health systems or individual health practitioners. And so we've described an operational framework for building climate resilient and now low carbon health systems, which talks about the core building blocks of health systems that most health systems people recognize, and then describe how climate change relates to health workforce. So health professionals should now be trained on climate change, including on low carbon practices, how it relates to service delivery. So ensuring service delivery methods are both resilient to climate risks and don't emit more carbon than they need to, for example. So we have these broad frameworks which are now very well recognized, I would say, by health systems around the globe, and they use this as an entry point to know where to feed in health protective or low carbon strategies. And just as a quick example of this, we support countries to develop national health adaptation plans for climate change. And then we monitor how well they're doing in developing good plans. And we can see that, for example, many more countries are now developing plans which are pretty comprehensive of health risks. So it has some of your favorites, hopefully, on there: non-communicable disease, mental health, and so on. So we're seeing improvements in that. But we also see that many of these plans highlight the problem, but they don't provide specific solutions. And so the kinds of things that I've been hearing about already in this conference, I can see how we would plug that directly into a recommendation for the kinds of things that should be included in the health action plan for specific non-communicable disease outcomes. And also to emphasize again that we're not just talking about protecting people's health from climate risks, we're also talking about policies and practices that can improve people's health, including brain health, at the same time as reducing the climate crisis. So we can point out, for example, the very strong evidence behind active transport, behind cleaner household energy, reducing air pollution, behind more sustainable and healthy diets, for example, as a contributor to reducing carbon emissions and improving health. Because I think it's important to remember that there's something like a 2/3 overlap between the sources of air pollution and the sources of fossil fuel emissions that are driving the climate crisis. So this is why we're so interested in going upstream and also advocating for these policies that occur in other sectors. We're also particularly interested in good case study examples. This is one close to where you're sitting at the moment. We're very interested in the evidence, for example, around the effectiveness of the ULEZ policy in London, or the changes that have taken place in Paris or other cities around the world in reducing carbon emissions, improving air quality, and improving health. And again, for us, brain health will be one of the categories of benefits that come out of this. So we provide the frameworks, we synthesize the evidence, and we also highlight good practice in this field. Getting to the last few slides now, to the extent that you follow international climate discussions, it's a painful business, but just to recognize that within the big climate discussions, including the conferences of the parties that happen every year, the last one being in Belém in Brazil, we're getting increased recognition of health and also some specific call outs to issues that relate to your area of work. So for example, mental health was highlighted as one of the big categories that should be advanced through the health agreement that was reached at the Belém COP at the end of last year. I'll skip quickly over these slides, but just to emphasize that WHO is extremely active now, not just in synthesizing evidence, but in actually supporting adaptation and, to a certain extent, healthy mitigation projects on the ground around the world. We're building a stronger and stronger coalition to do this. And here, again, a shout out to the UK, because the COP in Glasgow in 2021 was a real step forward, the first ever health initiative under a COP presidency. I had the pleasure of making a connection to the health community by being part of a cycle relay that went from Geneva to London to hand a letter and a report that was then carried by NHS doctors up to the COP in Glasgow. But that increased recognition of health within the COP negotiations has built up over time, and we've pushed it to build over time. And we now have something called the Alliance for Transformative Action on Climate and Health, which I think just welcomed its 106th member. So there is now strong political interest and a strong mechanism to take that forward. We have a wide range of tools which may be of interest to people in the audience to allow policymakers or practitioners or interested researchers to look at the health benefits of some of the policies that we think we should all be getting behind. We also have training courses on air pollution that again will make the connection back to mental health and also to brain health. So my final slide, just a few points to sum up. This is really top of the agenda for us now at WHO. We do really recognize this connection with brain health, neurological health, and we really do recognize the specialist expertise that is recognized in these communities. Listening to the previous presentations, we would never be in a position to tell anybody how to reduce carbon emissions from imaging in the neurosciences. That's what we need you for, to be honest. But we also, I would say, like to enlist your help in as part of the broader public health community, which is advocating for the wide range of policies which will improve brain health, but will also improve many other aspects of health, and also basically preserve a livable future for humanity. So thank you very much indeed for your attention, and I'm happy to stay online and participate in the discussion if possible. Thank you.
Thanks so much, Diarmid. Thank you very much. Such a rich presentation. It's great to hear that it's on top of the agenda. So we have time for a couple of questions. There's one there in the room. Please wait for the mic to arrive, and please introduce yourself.
Thanks. Hello, Tim Malone from the Royal Devon Exeter Hospital. Just wanted to ask you perhaps a difficult question about the elephant in the room. The WHO, you mentioned obviously that your numbers had decreased by 1. How big an effect has that actually having on what the capacity of what WHO can do, or have other countries actually stepped up to try and fill some of the economic gaps, that have been made as a result of decisions by certain world leaders?
Were you able to hear the question?
Yes, very, very well. Thank you. Yeah, I think the headlines of this are very well known. It's extremely regrettable that the US and possibly Argentina may be either have withdrawn or may be withdrawing from WHO. We don't think that is a good decision, and not done for good reasons. And that has clearly had a huge impact on WHO. It's something like a 20% reduction in our budget, which is a real cut, which has not been met by other member states, including because many member states are, again, unfortunately, moving away from development assistance and putting money into defence, to be perfectly frank. So it's a genuine decrease in capacity for WHO. I would say that on the climate change agenda, it has not made a big difference. We are actually entirely voluntary funded. It's money that we raise ourselves from particularly interested member states and other partners. And I would say that the political will behind this overall across all of our member states remains very strong. So again, I've been in this field for quite a long time, and I would say that the support for this area of work looks a little bit like the global temperature signal, in that it goes up and down a little bit, but the general trend is upwards. So we hope for better times in the future. There have been genuine impacts. People around the world are losing their lives because of the decrease in development assistance, but the evidence remains the same. Our values remain the same, and this is absolutely remaining part of our agenda.
Thank you very much for this. Can I please check if there are any questions online? No. If not, we can take one more question, one final question from the room. One? No? If not, I'd like to thank our speakers once again for this session. And we'll now move straight into a panel discussion. So we'd like to invite the panel members to come sit here at the front. Excellent. So thanks once more for the excellent presentations. So I would like to invite each one of you to reflect on what you have heard today. So if you could maybe keep it 1 minute, a couple of minutes each, if possible. So I'll start with Robert. Thank you.
Was just thinking in the last presentations, it's really great to have such a large group of people with such diverse backgrounds come and kind of discuss the challenges and emerging solutions in their fields. Really just highlights to me that we need this kind of cross-cutting interdisciplinary work to really explore all the avenues, and I don't think we can kind of address the problems from any single field.
Thank you very much. And yeah, please pass the microphone.
Yes, thank you very much. I think, yeah, the same for me. It was a pleasure being here and speaking also in the breaks to so many people from some diverse backgrounds and finding the connections to, yeah, what my work, where my work connects to other fields and perhaps the challenges that we might be able to tackle together. So yeah, that was really, really nice. And thanks to the organizers and thanks for the invitation.
Thank you, Valeria.
Thank you. Yes, so similarly, I was inspired by the multidisciplinary approach. I guess it's very much unique. From as a clinician, I guess what I take from today, maybe we need to change our mind setting. I don't think we do approach the patient quite proactively when it comes to sustainability and climate change, despite obviously the impact is quite significant. So I guess it needs to happen a change in our mind setting and maybe more proactively discuss this with patients. So it needs to become a part of the equation in the patient care, which is not happening at the moment. So I will take this message back to the team, definitely.
Yeah, thank you. Such an important point for practitioners here.
Yes, so for me, it was really also mind-opening because I'm used to going to conferences that are really more about tiny little nitty-gritty details of neurophysiology or circuit components in model organisms, and to see how much more complex, of course, the real world is, right? As discussed on many levels today, and still to, yeah, this reductionist approach, trying to think that we use in the lab, to see how that still can be useful to model or to extract data for that then can be also tested in more real world scenarios, and still also get at interesting mechanisms that can help to understand things better also in patients.
Yeah, thanks very much. I'm just going to echo what the panel have said. I think getting all these different people, all these different backgrounds coming together for the same thing. We're all interested in the effect of climate, heat, cold, etc. on people. There's so much we can do together and push science forward as a team. So,
thank you very much.
Thank you. Second last, so don't really have much new things to say. I'm just thinking that 10 years ago, I don't think a conference like this would have such broad representation from different disciplines, particularly in my home discipline, physiology. It felt as though we would go to our conference, very much like Jan was saying, we go to our very topic-specific conferences, speak to each other about the same things every year, and never really move any closer forward to some solutions that are scalable. And I think in order to do that, we need to interact with across the board when people are working on this. So that's really just my contribution there. Thank you.
Thank you.
Well, first, I agree with everything what I've said.
You can disagree if you like.
Yeah, I think this is very timely because we know from our data that heat is first and past neurological failure. This is the main target of the heat is the brain, and is more than just mental health, as the last speaker mentioned. Is a disease. Heat stroke is a neurological disease. Now, what I didn't mention in my talk is that 20 to 30% of the patients that survive heat stroke sustain brain damage that is permanent. with additional mortality up to 2 years, at least follow-up. Now, we have warning sign also. For example, a work from Taiwan looking at 78,000 patients who had heat-related illness. This is an insurance database. They follow them for several years, and they use a group control with four times sample. And they could demonstrate that there is an increased risk of dementia. So this is not a medical cohort, but it still is a warning sign. We know there is a work from the military in the US. They looked at 3,000 people who developed heat illness. And they compare them to young people, military also, but with who came to the hospital for appendectomy. And you see one single episode of heat illness increased the risk, 40% increased the risk of early death from cardiovascular disease, including either ischemic infarctions or ischemic heart disease, but also ischemic brain disease. So I think the focus, and this is why I think this meeting is important, because it brings together epidemiologists, clinicians, physiologists, biophysicists, and public health. It's what we need. The only way we can sort it out is that we have intra and transdisciplinary relationship. The last one, I spoke too much.
Yeah. No, please. And thank you so much. And Diarmid, if you can still hear us, would you also like to add your own reflections on what you heard today, if you'd like?
Yeah, thanks. Just quickly, I'll come at it maybe from the other side, just for variety, because it's been great to hear everybody recognize the importance of interdisciplinary research, the wide range of contributions that need to be made in order to address this issue, and I couldn't agree more. On the other hand, it's really important that these specialist technical disciplines are respected and make their contributions. I mean, it's quite easy for us in Geneva to sit here and say climate change is the greatest health threat of the 21st century. But if I want to know, if somebody wants to know, okay, but what do you do to protect garment workers in a non-air conditioned factory in Vietnam, then you need heat physiologists to do that. If you want to get to moderate and bring down the carbon emissions from any particular discipline in a large hospital, you need the people who actually are directly involved in those disciplines. So I think we do need to both recognize that we're just one contributor to this, but also to basically take pride in and look at the ways in which we can use our specialist knowledge to contribute the invaluable contributions that only that speciality can make.
Thank you very much. I mean, yeah, that's a crucial point. So my takeaway is, yeah, obviously inter-transdisciplinary collaboration, really important. I was also very impressed by the breadth and depth of the presentations today. And I guess, yeah, everyone's contributions are really important, and we're trying to produce something that is, yeah, bigger than the sum of its parts. So without further ado, I'd now like to open to the audience. Yeah. Oh, there are some online questions.
Well, maybe other people can put up their hands so that the roaming mics can get to you as well. But I will just start asking some of the online questions.
Yes, please. Yeah.
So I think I will kind of join some of these together. So someone asks about Dr. Bouchama's talk about Mecca. What proportion of the heat stroke patients are local to that geographical area? And then what proportion are visitors? So perhaps unexperienced of that level of heat. And I wondered if I could combine this to what Hannah and Ant were discussing. You're looking at adaptation using, for example, sauna or induced heat to kind of adapt to that ability to adapt to heat. But what about people that come from areas that are more tropical and experience heat for a lot of their lives? Is there kind of global data that compares these type of European or British populations to other populations? So maybe we can talk about those together.
Sorry, is it if the patient? The question is if the patient are local. Is what the question?
Yes. What proportion of patients are local versus visitors?
Well, easy, zero. Because the Saudi are adapted to heat and they live in air conditions. The problem is that the 2 million of people, more than 2 millions actually, that come from 180 countries of the world, and most of them are not adapted. And so we compared actually, using this time series, try to determine the minimum mortality temperature for the pilgrim versus the local. So the pilgrim, their MMT is around 23 degrees. The local people are 31.2 degrees. So the Saudi enjoy the heat. The lowest mortality is at the highest temperature. So they come to a desert. And when the pilgrimage is in the summer like now, it can reach up to 50 degrees. And because of the ritual, which actually exists before Islam, 1,000 years, is very strict. So they have to be outdoor. Some of the activities are outdoor, and this temperature, they are not adapted. So despite all these mitigation measures, you can never, you can reduce, but you cannot, make it zero. So, and especially that we demonstrated that actually the Mecca temperature is increasing more than the global average.
Thank you. I was just thinking it was an interesting first sentence you said that the Saudis are adapted to heat. They live in air conditioning. So it's kind of like, on the one hand, I think if you really live in air conditioning and if you really reduce indoor temperature to let's say the typical 21, 22 degrees Celsius, you're also going to have a hard time being okay in these extreme outdoor temperatures, right? But yeah, maybe I will hand you back the microphone after making a further comment. But I think indeed that, oh, we have another one, yeah. I think indeed that, of course, the risk for somebody who is not acclimatized to the local climate to have heat-related health issues is probably larger because of, the adaptations that we do see when somebody is regularly exposed to heat, and also like over a long time has been able to get used to these kind of extreme temperatures, and perhaps also has not only better physiological adaptation but also behavioral adaptation, because also they know better how to cope. So yeah, I don't know what your response would be.
Well, I think you're right. The air condition in our research center is so low that they had to put a heater and work with my jacket because it's too cold.
Yeah.
Now,
we are too freezing the whole day.
Whether the Saudi will lose their adaptations. They were Bedouin, the desert for several thousand years. They are very resistant to heat. And we're doing a work to see how is transmitted to the generations, to epigenetic. 25 discovering what's the mechanism will have national community. This work in Mecca was done 2 years ago. And the whole population in Mecca will come back. The MMT is 31.20, so they are still very adapted. But here's the interesting.
I to hold the mic close so that.
Here is the interesting point, because then Ollie Jay and then Rob work with this threshold, in lab, and they define threshold of heat tolerance. We ask the same question, but in general populations, in the real world. And this is this work in Mecca. So we saw that the MMT at 31.2, and we say, this is the most, the ultimate that humanity can reach, right? In adaptations. In addition, because they have become wealthy for the last century, so they have air conditioning everywhere. Yet we see at 38 degrees, we see the mortality start to increase. So there is a limit, real world limit to adaptations.
For sure that there's a limit. May I make one last comment?
Yes,
of course there's a limit, and I think also the work that we are doing is mostly directed, not let's say at outdoor workers or people that are already, maximally exposed and probably by that maximally acclimatized and also have a high risk in such scenarios. But I think it's important to look at the development of, also, let's say, Middle European countries where now more and more air conditionings are introduced because, of the availability, but also because of people obviously seeing this problem becoming larger and larger. And now we have to see how can we use those also in a energy efficient and sustainable way. And I think this idea of applying the same air conditioning set point globally was somewhere in the 70s in a thermal comfort research that then was translated into or that became an important part of indoor environmental standards, and nowadays this is applied everywhere. Whereas we do know from, for example, naturally ventilated buildings that don't have air conditioning, even in hot countries, people adapt very well and then also say that their neutral temperature or their preferred temperature is much higher than in countries or in countries where outdoor temperature is lower, but also in buildings where air conditioning is applied. So there is really, the possibility to use this adaptation, not necessarily where the extremes are very extreme and, for outdoor workers, but, for all the other people sitting indoors and being exposed to cold, like here today in this lecture hall, for example.
Saudi live in the desert. Like you actually Canadian to.
Please don't.
Yeah, thank you.
Yeah, I just want to add a point. There's actually really strong evidence of very strong acclimatization adaptation in the epidemiological literature. Was mentioned the minimum mortality temperature. This is just for those who this term might be new, this is the point at which the risk of all-cause mortality or cause-specific mortality is lowest. And some of the work actually we're doing with Josh Foster and Tom Matthews at King's College is showing that, and this isn't quite new, but we're kind of taking a little bit of a physiological lens on it, that there's almost a 1-to-1 scaling of the minimum mortality temperature and the summertime average wet bulb temperature. Minimum mortality temperature defined as wet bulb temperature. And so populations adapt very well to the conditions which they are typically exposed. But this, of course, could be physiologic. This could be public health response. This could be societal. But there's some really interesting data out of Joel Schwartz's lab at Harvard showing that if you track these temperature curves, we saw a few of them today, and you look at them month by month in the summer, you can actually see during the summer heating, that temperature curve shift right to higher temperatures and then shift back. So there's actually quite a bit of evidence that we do have the ability to adapt relatively quickly. Though the question now becomes is, what are the limits to these adaptation? There's obviously going to be a physiological and even physical wall. I'm not convinced we fully understand where that is, but this, I think, is the key for research is when there are conditions just so hot that any adaptation is just, it's not going to be enough.
There's still quite a lot of research there, isn't there? So I believe we have one more question online. Would you like to take? Yeah, the lady there at the back.
Hi.
Sorry, it was the lady first. There. Yeah, thank you. Sorry.
Yeah, thanks very much. I guess the takeaway is just how complicated this situation is, and trying to kind of summarize what the potential predicted impacts would be from, like, if you're a policymaker, if you're kind of taking a key message. It sounds like, we know that there is some evidence of adaptation at these different timescales in different populations. And there's also some papers I've seen in the mental health literature that seems to suggest over the last period of warming in the US, for instance, that suicide rates actually have been rising with rising temperatures in a way that shows actually no adaptation in this particular paper. So it's a complex picture. But if you were to summarize based on the evidence there is now, is there work kind of predicting as the temperatures rise, but also as the frequency of extremes rise, both within unseasonably like high minima, extreme heat waves, etc., what it will look like at a population level for the timescales of adaptation versus the timescales of these changes? Do you think that, you know, populations like in the UK, for instance, as it just gets warmer, that there is going to be some adaptation so that what we might predict based on the data now to be the increased morbidity, mortality burden will actually, you know, people would naturally adapt to some degree? And what happens with the kind of temporal change versus like the kind of rising baseline versus these kind of increased peaks, and also the way that people kind of go in and out of air conditioning, for instance? It seems like when you are exposed for a few days, you actually kind of, your heart rate lowers, you get healthier, but then you're also accumulating this kind of heat stress. So I'm just a little bit confused around the kind of the benefits of heat even over several days or over several hours versus the kind of accumulation of heat stress or these kind of quick changes from hot to cold and what that does. So I guess just on population average, what do you think is going to happen as sort of a warming world? And then what do we know about this kind of short versus like the timescales of these changes that are both harmful and adaptive?
And who would like to take this?
I can speak to the first couple of points. I don't think any of my answers are going to be overly satisfying. But yeah, I think it's a big question on how do we use the epidemiological data to project out. I think one of the biggest mistakes that's often made is assuming that our relationship between heat and mortality or any sort of health outcome today helps us predict what happens in the future, because we know that the shape of these curves do change over time, and they do even change depending on the populations you're looking at. I think another thing that we need to increasingly do is kind of split the way we think about heat into kind of these extreme heat waves and then the day-to-day heat. There was a presentation earlier that put the minimum mortality temperature, maybe it wasn't mortality, it was a hospitalizations or something, for the UK at about a 16-degree daily average temperature. I don't know, maybe the UK considers that hot. I'm Canadian, I don't really consider it that hot. But the vast majority of the burden of what we might call non-optimal temperatures, hot temperatures, actually occurs in conditions that we wouldn't consider all that heat stress. And so when we say things like, you know, certain indicators track or are reduced as we implement heat action plans, whereas others are not, I think it's because, or my guess is that we're getting good at responding to heat waves, but how we adapt to increasingly warm temperatures is not well thought out. And it's harder because this is, you know, this is building codes. This is more, I think, harder to implement responses. And then just, I think I'll pass it for the acclimatization. I just like to think of it though, an exercise. You know, you exercise, you start off slow, you build up your tolerance. But if you were to, you know, try to run a marathon tomorrow, at least if I try to run a marathon tomorrow, I'd be in pretty bad shape. So I think with anything, it's you know, wading in. And as Hannah mentioned, like figuring out how we can design protocols to slowly adapt to summer, at least to these warm temperatures. I think that's kind of an important area for future research.
I might just quickly just pick up on just the last strand of that conversation. When we're talking about adaptation, I think often we're kind of wrapping in a bunch of different things, right? So there's behavioral adaptation, there's structural adaptation, there's policy adaptation, and then there's also biological, physiological adaptation. And I think, and I don't know if this is wrapped up in maybe part of your question, but I think I often hear people talk about, well, we'll continue to adapt. As it gets hotter, we'll continue to adapt. And Rob touched on this a little earlier on in one of his responses, that there's a ceiling. There's a physiological ceiling to how much we can adapt. And then there's actually a physical ceiling as well, because it's really when it comes to heat exchange between the body and the surrounding environment, that's governed by physics and there are limits to it. And so I think often people are thinking that biologically we can keep adapting as it gets hotter, but that's not going to happen. And so once we've exhausted that ability, all we've got left then is other types of adaptation. and much of that will be quite carbon intensive, especially if it means more air conditioning, other kind of structural adaptation. So just wanted to kind of throw that in there because I think it's probably worth just keeping in mind that when we talk about adaptation, I think we do have to separate it out into the different types of adaptations because the limiting factors for those are quite different.
Thank you very much.
I can add the biological part to it, at least a little bit of science fiction, if you want. Saudi is adapted. They are 31.8 is the ideal MMT, and the Kuwaiti has a 32, which means that human populations exposed to be living in the desert over centuries acquire resistance or adaptation to heat. So this is a proof of concept that is possible, right? Now, how can we achieve that? And to achieve that, we need to understand the mechanism. I don't think this is genetic, although it's over the years. We are working on that to see if there is gene variant. Now we didn't discover anything. Gene variant that confer resistance. But I think is like plant, like some animals, all living species acquire resistance or adaptation through epigenetic changes. And actually, this adaptation to heat is a prerequisite to life in Earth. So this heat stress response is so conserved that is in a single cells before humanity, before it goes to multicellular organism and to human. So we're working in the epigenetic. I think it's the epigenetic, and it should not be difficult to identify it if we have the critical number of patients very quickly. Because the advantage of the epigenetic as well as the science fiction is that these are chemicals that change the gene expression. We are not modifying gene, so we can imagine that we can, because epigenetic by definition is peripheral. It comes from the Greek epi, and it's peripheral. So we can modify the parts that give us resistance. We can add the chemical there. This is not, it's done. We can. So we might imagine that in the future we can adapt voluntarily, scientifically, the populations.
Thank you all very much for this. I don't know if that answers your question. We have time for one more question. The gentleman at the back. Thank you.
Hi, Reza Damani from Exeter University. It's a generic question from the panelists. I know that NHS has committed itself to about 2040 to net zero. So that's very encouraging. I was just wondering whether the panelists' organizations have also committed themselves to some sort of net zero. And if it is the case, what is it? Just curious.
Would like to answer? Yes. Do you mind repeating it very quickly? It's about commitments of your organization.
Exactly.
Yeah. Anyone?
The University of Sydney has a sustainability policy, but they haven't committed to net zero, to my understanding. But maybe Diarmid's going to respond on behalf of the World Health Organization. Slightly more heft.
Awesome. Thank you. And Diarmid, would you like to come in, please?
Yeah, I would. WHO does actually have a commitment to becoming net zero by 2030. I have to say, this is something that we need to follow up on very actively. It was made on World Health Day 2 or 3 years ago when the theme was climate change, environment and health. In fact, we were holding joint seminars with NHS England, who had made that fantastic commitment to become net zero by their birthday, their 100th year anniversary. A lot of this can be done at below zero cost. We now find in health systems around the world, for example, that shifting to renewable energy sources actually saves money at the same time as cutting carbon emissions, but some of it can't. So it needs more than the commitment; it needs the implementation plan to go with it, and it needs to connect to people's everyday practice as well.
Yeah, thank you. Very important points. And I guess a reminder that climate change mitigation and adaptation should go hand in hand, and it's really important to quantify their health co-benefits. So we're running a little bit late, but we have a few announcements. So if that's okay, I'd like to thank the panel members for their insights and the audience for all their questions, and of course all the speakers and the previous chairs. So join me. Thank you. And I would also like to thank those who presented posters. So these are Ravi Shankara Belambali, Medina Gulsebi, Tim Malone, and Shivei Owi. And we would like to congratulate the two winners of the Best Poster Prize, which are Shivei Owi and Medina Gulsebi. So if they could come forward. We would like to invite them to collect a certificate indicating the planting of 10 trees for each of them in the UCL Grove. So congratulations. Well done. And just to say, I really enjoyed looking at the posters, very, very interesting studies, all of them. We would like to thank the sponsors of today's event, Epilepsy Society and Siemens Healthineers, for their generous donations that cover the cost of the conference. And of course, a big thank you to Sanjay, Professor Sanjay Sisodiya, who, as we know, has been a huge driving force for this work and was unfortunately unable to join us today. And of course, the organizing team for putting such a hard work into making this event happen. So many thanks, everyone. And over to you, Maurice, for some final comments.
Yeah, my final comment is we'd really appreciate your feedback on this event from the online audience and the in-person audience. You can scan this QR code to go to a feedback survey. I'll also email it out to you all this evening. So yeah, please give us your feedback to help us plan for next year's event. And finally, on behalf of all of the organising team, and especially Professor Sanjay Sisodiya, who would really have liked to have been here today, I want to say thank you all for coming. Thank you for joining online. Thank you also for our co-organisers, the Lancet Neurology, and all the helpers today. It's been a great event, and we look forward to welcoming you next year in May. A provisional date of Wednesday, the 12th of May. We will confirm that. We look forward to seeing you then. Thank you.